Welcome everyone to this last day of the Open Universe workshop. We are going to have still 2 days of Sciathon, but this is a closed activity for the in-person participants. So this is really the last day of our open event. And it's my pleasure to open the event with a presentation from Dr. Simonetta Di Pippo. Unfortunately, she had a family issue, a health issue in the family, to which she had to attend. So she cannot be here with us today, but she sent me a text with the content of her presentation, which I'll read on her behalf. So just to introduce the speaker, Simonetta Di Pippo is a former director of the United Nations Office for Outer Space Affairs and was a great supporter during the times of the preparation of the initiative within UNUSA to shape the initiative and to work towards it being successfully established. And she continues to be a great supporter of the initiative. So we are very happy that she will deliver this presentation through me reading the text, but that she is here with us in this first event. She is an astrophysicist from the University of La Sapienza in Italy, worked in the Italian Space Agency as well, and now teaches space economy at the prestigious Bocconi University in Milan. So to start her presentation, whose title is Leaving No One Behind in Space Science. So I'll read her text as she sent to me. Good morning, everyone. It's truly a privilege to open this year's Open Universe Symposium. Our team, Leaving No One Behind in Space Science, is more than just a headline. It is a commitment, a principle that we must place at the center of all our scientific and policy efforts. As we gather here today, let us remember the discoveries we make beyond our planet should serve everyone on it, because the sky may belong to no one, but the knowledge it holds belongs to all of us. Over the last several decades, space has become a vital frontier for innovation, technology, and data. Satellites help us monitor climate change, track natural disasters, support agriculture, and even facilitate internet access. Yet, access to these benefits is not equally distributed. It is where the 2030 Agenda for Sustainable Development and its 17 SDGs may drive us in shaping our actions. Many communities, particularly in the Global South, remain at the periphery of the space ecosystem. They lack the infrastructure, funding, or institutional support to fully engage with space data or research opportunities. What it tells us is stunning. It is not a reflection of capability or talent. It's a reflection of access. For this movie, let's embrace the concept of leaving no one behind. Let's see if I can play the movie. Vocês conseguem tocar o vídeo? Okay. So maybe there was a file that was not drafted or something using our computer. Anyway, space solutions may be helpful in helping the world to become a better one. The European Space Agency and the UN Office for Outer Space Affairs joined efforts to present a compendium of space-based solutions for the ones who know that space may help to improve the quality of their lives and for the ones who don't. It is a powerful example of leaving no one behind, opening up knowledge to everyone, everywhere. The UN Caucus is the multilateral body dealing with the peaceful uses of outer space. It is the place where all the countries can present proposals and have their voices heard, irrespective of their level of socio-economic development. A great place to start a conversation on how to bring science and space science in particular to everyone. This is where the Open Universe Initiative comes in. Launched under the umbrella of the United Nations Office for Outer Space Affairs, the Open Universe aims to democratize access to space science data. It's about making data not only open, but accessible, understandable, and usable by researchers, educators, and students around the globe. We are building platforms that allow someone with nothing more than a computer and an internet connection to dive into space data, conduct research, and make discoveries. This is how we level the playing field. This leads us to the Space 2030 agenda, adopted by the United Nations to guide the integration of space into sustainable development. This global strategy lays out a vision where space-based solutions support disaster risk reduction, climate monitoring, health and education, digital inclusion, and peace and security. It urges us to ensure that space contributes to all 17 Sustainable Development Goals. It also calls for greater cooperation, data sharing, and inclusivity. An open universe has a precise positioning in this strategy. An important role is also played by Firmamento in the framework of the Open Universe Initiative, which was developed at the New York University in Abu Dhabi. You'll hear a lot about it in the coming speeches this morning, so I'm not going to anticipate anything here, but it's my pleasure to underline that this shows a strong international collaboration and common efforts and goals around the globe on the matter. Let's not forget, the next breakthrough in space science might not come from a well-funded lab in a major city. It could come from a young girl in rural India, a student in Colombia, or a self-taught coder in Kenya, but only if they have access. Open Universe is about unlocking that potential, and by doing so, enriching the entire scientific community. Because talent is universal, opportunity is not. Our job is to close that gap. I'm excited to announce that these teams will be part of the conversation on May the 9th at the United Nations headquarters during the high-level event, Advancing Global Scientific Cooperation for Sustainable Development, Leveraging Quantum Science for a Resilient Future, in the framework of the UN declared International Year on Quantum Science. This event will celebrate 60 years of the UNESCO International Center for Theoretical Physics, and it will be an opportunity to link space, quantum science, and sustainability through the common thread of openness and resilience. I'm going to intervene on site, and I'll take the occasion to underline how citizen science is important to help increasing awareness about the open universe. Allow me, in fact, to underline that this goes hand in hand with the understanding that science, and in our case, space science, has to be brought at the center of any political and strategic decision. In this respect, I welcome the creation of the Group of Friends in New York in the framework of the UN System for Science on Action. I feel that an important step for the future could be to present our Open Universe initiative to them to help support the initiative inside the UN system. In September last year, the Summit of the Future took place, and it gave birth to a very important document approved by the General Assembly titled Pact for the Future. The main reason for the pact is to accelerate the accomplishment of the 17 SDGs, now that we are reaching the 2/3 of the entire path under the umbrella of the 2030 Agenda, which was supposed to deliver the completion of the goals by 2030. We are all running late, and this was partially expected, but let's accelerate. This is the motto of the pact. That same mission lies at the heart of the Inspire for Tomorrow Foundation, which I founded to turn inspiration into opportunity. Inspire for Tomorrow exists to bring space science into classrooms, into communities, into conversations. We aim to ignite curiosity in the minds of those who may never have imagined a place for themselves in the space sector. We do this through hands-on educational programs, international partnerships, mentorships and fellowships, and I believe that anyone, anywhere, can be part of the future of space. The main goal is to accelerate the path for the future using STEM, digital cooperation, AI, quantum, and space, which is a challenging task. What matters most now is turning these policies into real, measurable action. And we must expand access to open space data tools, translate technical content into local languages, fund training for researchers in developing countries, and encourage global scientific networks where all voices are heard. The principles of Space 2030, the 2030 Agenda, and Pacts for the Future must live not only in documents, but in labs, classrooms, and code bases around the world. And so the Inspire for Tomorrow Foundation does with its programs and projects. None of this can happen in isolation. We need strong partnerships across institutions, sectors, and borders. We need governments to support open access mandates. We need the private sector to adopt inclusive licensing and infrastructure policies. We need universities to share knowledge, not gatekeep it. Most of all, in fact, we need to build trust. Trust that data will be used ethically and that collaboration will be mutual and respectful. But we need to reach people locally too. So while the Inspire for Tomorrow Foundation is incorporated in the US, we have already established an Italian legal entity as a branch, which will be located in Palazzo Carpano, a historical building in the center of Turin in northern Italy. We have plans to expand further because open science requires open minds, reaching different places to strive. So stay tuned. We presented the Inspire for Tomorrow Foundation on the 5th of February to the UN in New York at an event organized in the framework of the ECOSOC Partnership Forum. Why? Because as we look toward the future, we must recognize that space is no longer a siloed discipline. It overlaps with artificial intelligence, quantum computing, Earth observation, and planetary science. We are in a moment of convergence, and if we want the benefits of this convergence to reach everyone, we must build infrastructure that is interoperable, open source, and inclusive. In addition, education is our greatest launchpad. It is not enough to inspire. We must teach, train, mentor, equip. That's why Inspire for Tomorrow is creating educational modules for teachers, summer camps for students, and training for early career scientists. These are the building blocks of a truly open space ecosystem, and it may become also a platform for Open Universe to amplify its impact and its results. Let us never forget, behind every satellite image, behind every data point is a story of human ingenuity, of exploration, of hope. And when we open the universe to others, we are inviting them to write their chapter in that story. In closing, the Open Universe is not only a technical mission, it's a moral one. Let us build a future where the tools of space serve all of humanity, where talent is nurtured everywhere, where no voice is left out, and where the stars guide us, not to divide, but to unite. Thank you, and let's continue the journey together. So I thank Simonetta for this very inspiring speech. And now we move to the next speaker of the day, going into the scientific topics that are on the basis of the works that we are doing these days with the Open Universe tools, which is AGNs and lasers. Okay, so our technicians managed to get the video to work, the video that was on the third slide of the presentation. So they're going to show it now, and then we follow with the next presentation. Thank you.
To vulnerability. 1. Discrimination, inequity on basis of assumed identity or status. 2. Demographic, exclusion based on location. 3. Socioeconomic, inequity due to education, economy, income, recession, extreme poverty. 4. Governance, exclusion due to law, policy, and access in governing system. 5. fragility, vulnerability due to climate, conflict, pandemics, etc. For example, if we look closely at the socioeconomic driver, we see that families living in extreme poverty may lack access to health, food, education, a job, and much more. In another example, fragility is a driver, which includes crises such as COVID-19, armed conflict, and climate change. The 2030 Agenda for Sustainable Development includes a pledge to leave no one behind. Governments across the globe committed to this in paragraph 4, which says, as we embark on this great collective journey, we pledge that no one will be left behind. Recognizing that the dignity of the human person is fundamental, we wish to see the goals and targets met for all nations and peoples, and for all segments of society. And we will endeavor to reach the furthest behind first. There are many different vulnerable groups. How can I promote meaningful engagement of vulnerable groups living in extreme poverty and prolonged crises? Inform, consult, involve, collaborate, empower. How do I measure success? 1. Build respect. 2. Partner with others. 3. Empower marginalized. 4. Build capacity. 5. Promote solidarity. 6. Be the voice. Leave no one behind means that all stakeholders have a role to play to ensure that the furthest behind achieve progress in the 2030 Agenda. What action will you take?
Great. So this will be also posted on our webpage and YouTube channel. Okay, I'll make sure I give you the link. Okay, so now, Ranieri, please.
I know that here we have high school students, undergrad students, master students, professors, researchers, and I want to pass useful information for all of you. So let's see if we can manage that. And please feel free to make any question you want. Okay, so let's start with what is an AGN, what is an active galactic nuclei. And I start by citing the what's in a name, which is the famous Paolo Padovani review on the topic. And AGNs, in very few words, are supermassive black holes in the center of galaxies that are swallowing a disk of gas. And when they swallow this gas, the disk emits radiation. And eventually we also have a non-thermal jet. Non-thermal will be clear in the next in the next slides. And the emission from active galactic nuclei typically can cover up to 20 orders of magnitude in frequency. So they can come from the radio all the way up to the gamma rays. Here we have a very known picture. Actually, it's a composite picture of the Centaurus A active galactic nucleus, which is relatively near the Milky Way. So we have the optical image that you can see the galaxy and a patch of dust. And we have the jets that are not in the optical. The jet is a composite of radio and X-ray emission. So this is the general picture of what an AGN looks like. but let's try to go deeper into the details. So the observations of AGN date back to the beginning of the 20th century. They started actually around 1910, 1920, more or less. But people were observing them without understanding what they were observing. They knew there was something weird with those stars, in quotes, that they were observing. So more or less in the 40s, Carl Seifert, this American astronomer, identified this particular kind of galaxy where for short exposures, it looked like a star. He was detecting only the core of the galaxy, but for longer exposures, he could see the extended emission of the galaxy. So, and this was very unusual. So he was finding galaxies with an extremely bright core, and he could not explain that at the time. And in the subsequent years, people started taking spectra of cores like that. And they realized that these spectra were mainly divided in two classes. What we call the now Seifert 1, after Carl Seifert, which we see broad emission lines. You can see these broad emission lines in the spectrum. And the type 2 Seifert, where we don't see these broad emission lines, but in any case, we see a very bright core. This difference between the classes will be clear for you, hopefully clearer for you in the next slides. But in general terms, the spectra of active galactic nuclei are very different from normal galaxies. So here, for instance, I show you in the top two spectra of active galactic nuclei. On the left is a quasar, so we have these very broad lines. And on the right, you have a low luminosity AGN that I will also go into more details in the next slides. So in the low luminosity AGN, we can detect some very high emission lines. And you see that, for instance, the oxygen 3 line is quite high if compared with the hydrogen beta line, which is basically invisible in this spectrum here. So we have ionized material like oxygen 3 emitting a lot of radiation, while the hydrogen is not emitting that much. While in normal galaxies, like in the bottom panels, we have a lot of hydrogen emission if we have a spiral galaxy, which typically presents a lot of star formation, or we basically have no emission lines when you have a elliptical galaxy. These galaxies are very poor in gas, and they typically don't form stars in a reasonable rate. Okay, before proceeding, we have to discuss a little bit about a historical problem in astronomy. So we tend to classify things before we understand them. So we start observing these objects in the sky like that had very particular properties, these nuclei, and we start classifying them as liners, Seiferts, quasars, radio galaxies. This is a morphological classification, and blazars, and we can subdivide these classifications and even more. And but at the end, most of these, not all of them, most of these are manifestations of the same phenomena, just viewed by different angles. But this will be clear in a moment. But here we have a lot of degeneracy, a lot of redundancy in these definitions. For instance, Seiferts are basically radio quiet quasars. They are low powerful quasars. And in any case, astronomers came up with a tool that is very useful to at least separate what is an active galactic nucleus from a normal galaxy. For instance, this diagram here is called the PPT diagram, where we take the line radius. You see there on the y-axis, you see the oxygen 3 over H beta that you could see here, for instance, on the top right corner. We have a very strong oxygen emission and a very weak H beta. And we also have a quite strong nitrogen 2 emission and relatively small H alpha. So in this, in this plot here, that object on the right would fall on the right of this this dividing line. While if we take the ratio of the lines for the star forming galaxy in the bottom left, it would fall in this green part. So at least we have a tool that we can safely use to separate normal galaxies from AGNs. But the AGNs per se, there is a lot of degeneracy between the classifications. Okay, so in the 90s, people put this all of these observations together, and they come up with the unified AGN model. In this model, we the main problem with the different observations that we had was the inclination of the AGN with respect to our line of sight. So we have a black hole in the middle, we have a disk, and we have a dust torus. So if let's start from the bottom, which is for the radio quiet, so they play the AGNs that have no radio emission. So if we look to the black hole at this angle, a large angle, we have a Siffert 1. This is because we can see the core of the AGN. So if you remember, it's better if I come back. So Siffert 1s, they have broad emission lines, while Siffert 2 have only thin emission lines. So for a Siffert 1, we see the broad lines because we are seeing the core of the AGN, where the gas that goes in one side of the blazar and comes up in the other side, orbiting the black hole, will suffer from Doppler shift, and this Doppler shift will make the line larger. For Siffert 2, we are looking at the galaxy more or less at the we have more or less an edge-on view. So the dust torus blocks our view to the core, so we cannot see these broad lines. We are seeing only the narrower lines that are coming from regions that are beyond the dust torus. Besides this geometric point of view, we have also the presence or not of a non-thermal jet. This jet is we observe it because it emits synchrotron radiation, which is radiation coming from electrons, is spiraling in a magnetic field. So this is not present in all of the AGNs, but in the AGNs that we see them, the classifications change a little bit. So typically, if they have you see in a moment a classical accretion disk that we call Shakura-Sunayev, if they have this disk and they have the jet, we call them we can call them a quasar, depending on the inclination, or if the jet is pointing to our face, we call it a blazar. Okay, we have I'm going to discuss two accretion regimes here. The Shakura-Sunayev, which is this thin disk. I will give you more details in a moment, and the Ryaf. However, there is another accretion regime called the slim disk, which is very useful as well. However, it's I think these both are the most important ones. Okay, so to test this model of AGN unification, it would be very nice if we could see through the dust. So imagine we have a Siffert 2. So we are blocked by this absorber, by the dust. It would be very nice if we could see through this dust and check if we could see the broad lines through the dust. And this is exactly what happens when we use spectropolarimetry. I'm not going into details of spectropolarimetry, but it's a way that allows us to see through the dust. And then we have the Siffert 2 galaxy, NGC 1068, that we see in the top spectrum only narrow lines. So we have only narrow lines. If we look through the dust, then the broad lines appear. And also the spectrum becomes bluer, becomes brighter in the blue side of the spectrum, which is a clear indication that through the dust we can see the accretion disk. So this is one of the main results that supports the unification model. And one thing that is misleading about this image here, this is everybody that works with AGN knows an image like that. But one thing that is misleading here is that the thickness of the dust torus is quite small here. We know that this is the torus is very large on the average. And we know that because of the abundance ratio of Seyfert 1 and Seyfert 2 galaxies. So we see that Seyfert 1 galaxies, they are 1/3 all the Seyferts that we observe. So if we assume that the AGNs are randomly oriented, then it means that the obscurer, the dust, is covering 2/3 of the angular of the solid angle of the AGN. So actually, in this image here, the dust torus should occupy a much larger space. Okay, so let's go into a bit more of detail on the narrow line region and the broad line region. So the narrow line region for which we see the Seyfert 2, for instance, this emission is not coming from the center, from the accretion disk, really, from close to the black hole. This is coming from outside of the dust torus. So, for instance, here we have the NGC 5728. This is a Seyfert 2 galaxy. So here we have a zoom in the core with the Hubble Space Telescope and an oxygen 3 filter. This means that we take, you can see this higher line here. We take a filter in the Hubble telescope that allows only this line of emission to pass. So it's not, it cuts everything else. So when we observe with Hubble, we see these two cones of emission. Here in the center, we have the black hole in the accretion disk, but we cannot see it because it's blocked by the dust torus. The dust torus here is in this direction. Okay, so we see these two cones of radiation that come from the gas that is ionized and excited by the black hole, and then re-emits radiation that we can see. Okay, but we cannot see exactly the core. And while the broad line region is inside the dust torus, this is an image of the dust torus of NGC 4261, and inside the torus is the broad line region. The accretion disk is inside that bright dot in the center. However, we don't have resolution to actually see the disk. In this particular case, is not a classical disk. It's not a Shakura-Sunyaev, it's a RYF. But I will get into details later. And we can use these broad lines also to measure the mass of the black hole, actually to estimate the mass of the black hole, because measure is a quite strong word for what we can do with the broad lines. Okay, so let's discuss a little bit about accretion disks. Let's start with the classical view. This is the Shakura-Sunyaev disk. It's geometrically thin and optically thick disk. So it's thin. Geometrically, it seems like the Saturn rings. They are not the same thing. They are not the same thing. But geometrically, they look very similar. And this disk, it will touch the event horizon of the black hole or not, depending on the rotation of the black hole. So in the middle here, we have a static black hole, a black hole that is not rotating. So we see that we have the accretion disk and we have this gap before the gas reaches the black hole. This gap happens because in order to orbit the black hole inside this gap, a particle has to be faster than light. This is not possible, so the particle cannot keep the orbit, and it follows a ballistic trajectory up to the event horizon. Okay, if we have a black hole that rotates in the same direction as the rotation of the disk can touch the surface of the event horizon in an extreme case when the rotation is the maximum possible, or this gap can be much larger if the disk rotates in one direction and the black hole rotates in the other. So this this kind of disk is known as the cold disk. Even if the temperatures in the inner parts of the disk can reach 10,000 to 10 million kelvins. These are known as cold disk, and you understand in a moment why. So here we have what we call a pseudo black body emission. If you are familiar with black body emission, we have a constant temperature and a radiation curve that emerges from it. Here we don't have a constant temperature. For every ring of this disk, we have a different temperature, with the highest temperatures being in the inner part of the disk. So at the end, we have a pseudo black body emission. And for supermassive black holes, this peaks in the ultraviolet. So we expect that black holes accreting in this system have a very broad, a very huge ultraviolet emission that we call the big blue bump. Okay, so let's continue with the cold disk. So we don't need to go into the math here, but it's actually if you did the calculus, it's quite straightforward to follow this. But the interesting thing here that I want to call your attention is that the temperature here in the bottom, as a function of the radius of the accretion disk, it goes inversely proportional to the mass of the black hole. This is quite, for me at least, is quite anti-intuitive. And so this means that the larger is the mass of the black hole, the colder is the disk. So for supermassive black holes, I just told you that the peak emission is in the ultraviolet. If you go to stellar mass black holes, the peak emission can reach the soft X-rays. They are much hotter if the mass of the black hole is smaller. So the temperature falls with the square root of the mass of the black hole. Okay, this before showing you the physics of these plots, I have to explain what we are seeing here. This is what we call a spectral energy distribution. So we have basically the flux of energy in the vertical axis as a function of the frequency of the radiation that we are observing. So we see that for frequencies that are around 10 to 15 to 16, which are frequencies of ultraviolet radiation, for 3 classes of AGNs, all of these classes accreting with the disks that I just described, the Shakura-Sunayev, they have this bump. Can you see, no? So we have this emission here, and then we have a bump around 10 to 15, 10 to 16. This is the so-called big blue bump, and this emission comes from the accretion disk in the ultraviolet. Exactly what I just described, okay? While for the other accretion system that I'm going to discuss, we don't see this bump. We see actually a fall. Oh, no, we don't have this ultraviolet emission. This happens for AGNs in very low accretion rates that we call them RIAFs. I'll describe them now. So I want to come back here to show you the first sentence there. So Shakura-Sunayev is a geometrically thin but optically thick. With optically thick, it means that it's not transparent to radiation, okay? While the RIAF is exactly the opposite. So we have a geometrically thick, so the disk is large, and it's optically thin. The disk is translucent, it's transparent to the radiation that its particles are emitting. And the emission of radiation in this is actually very inefficient. We don't have friction anymore. In this case here, we have a very low density environment, so we don't have friction and between the gas particles. So it's very hard to change energies, especially for the ions. For the electrons, it's easier. And something really impressive, at least for me, it's impressive, happens in these disks, that at the end we have two temperatures plasma. So we have the electrons that irradiate more easily, it's energy, so they cool down much faster, and the protons that cannot cool down, they basically don't cool. So the protons here, they can reach the virial temperature, which is this means that the gravitational potential, the gravitational energy actually of a particle, it's comparable to its thermal energy. So if we make the ratio between this, it has to be more or less the same, must be 1. If we isolate the temperature, we see that for a supermassive black hole, we can arrive to 1 trillion Kelvin. So that's why I say that the previous disk was cold. So it was cold with respect to this one. And so this is the RIAF, and this is the disk that causes this drop, this orange line here. Okay, so now that we discussed a little bit about the disks, let's take an overview of jets. I like these proportionality relations because even if you don't know the physics that took you to that point, at least you can see on what parameters a given phenomenon depends. So the jet power given by P jet here is proportional to the spin of the black hole given by A. So the faster is the black hole, the most powerful is the jet. Depends on the surrounding magnetic field and on the black hole mass. Michele Doro showed you an image similar to this one in his presentation on Monday, I think. And here we can see the galaxy in the optical in the center. This is a galaxy. It has more than 100,000 light years in diameter. Okay, this is huge. And you see that the radio jets, they can go much beyond the galaxy. They are really powerful, and in this case, really collimated. And with my first contact with this kind of thing, as a student, I was always thinking, how can we have such huge magnetic fields coherent, extended over such large scales? But after a while, I discovered that these magnetic fields are actually very small. Just the distances that we are talking are so huge that they play an effect in any case. To give you an idea, the magnetic field on Earth's surface is about half a Gauss, 1 Gauss, more or less. Here we are talking about things that are 1 million times weaker than that. So we have typically very weak magnetic fields. And the intensity actually can change a lot between where you are. So closer to the black hole, it's much stronger. Okay, now this is the part that I'm not sure if I should present, but here things are becoming more complicated. This emission from the jets here are seen in radio, although the galaxy and the stars that we are seeing are an optical image. The jets were imaged in radio. However, now we are going to the gamma ray domain, so I can arrive to the blazars. The radio emission in these jets is emitted by electrons. We have this is synchrotron emission, which is emission from a charged particle going around in a magnetic field. Every time you have an accelerated charged particle, you have radiation, emission of radiation. And this emission is in the radio, which is very low energy radiation. This emission, this radio emission can be upscattered by the same electrons that are emitting the synchrotron radiation. It can be upscattered to the gamma rays. So the frequency changes like that. So the final frequency of the photon depends on the original frequency, and this gamma factor is squared. This is the Lorentz factor of the electrons in the jet. So if you have a Lorentz factor of 10, you have a 400 times more energetic photon in the output. So this process can upscatter radio and optical infrared photons to the gamma ray domain. Okay, however, and I say that this part was complicated. There's another phenomenon in place here, which is the relativistic beaming. While the radio emission, we see it, we can see it from this perspective, from this 90 degrees angle. For gamma rays is a bit different. There are some cases where you can see something similar to that in gamma rays, but typically it's they are very rare. So the gamma rays, they are emitted preferentially in the jet directions due to this phenomenon called the gravitational beaming. So the gamma ray photons are upscattered only in the direction of the jet. Okay, so to see a galaxy in gamma rays is much easier if instead of being like that, the jet is pointing in our direction. Okay. Okay, and there are also other ways of producing gamma rays. This, for instance, if you remember the RIAF, this kind of this thick disk, I told you that the temperature arrived to 1 trillion Kelvin. You can imagine that the speed of these particles in this high temperature gas is very high. It's so high, in fact, that we can expect proton-proton collisions and the formation of neutral pions. So for a RIAF disk, we can have proton-proton collisions forming neutron pions in a fraction of a second decays on a pair of gamma rays. And then we have here again the spectral energy distribution, so the energy as a function of the frequency. And for the RIAF, we have synchrotron peak, inverse Compton peak. Inverse Compton is this process here that I described that's a bit complicated. So we have a synchrotron peak, inverse Compton peak, inverse Compton again. We have two inverse Compton, and then a Bremystrolov peak. And at the end, we have this rise, which is the gamma ray emission coming from pion decay. Just to make it clear, this is expected. We never observed the pion decay emission from AGN. Okay, so for actually, I think that for students and even for research, it's very interesting to have this insight here, because people think that this gamma ray emission starts at the rest energy of the pion. So it has to be at least the rest energy over 2 of the neutron pion to start the emission. But actually, it has to start at much higher energies. So here, there is a threshold of 280 mega electron volts, which is much higher than the neutron pion energy. Otherwise, you cannot conserve energy and momentum in the interactions. Okay, so this is a sky map made in gamma rays. We did this in São Paulo a few years ago. And maybe the lights here are not the best, but maybe you can even see here some blue dots. Several blue dots here, and also some reddish dots. These blue dots in gamma rays, they are BLX. The colors here, they represent the energy of this gamma ray. So bluer sources represent harder gamma rays. Okay, so we have BLX and we have flat spectrum radio quasars. These are two different kinds of blazars, and blazar is an AGN with a jet when the jet is pointing at our face. So these are general terms. There can be exceptions, but in general, BLX, they accrete in the RIAF system, so they're thick, disk, and transparent. And they while the flat spectrum radio quasars, they emit, they have a Shakura-Sunyaev disk. In the optical, the BLX are quite famous in the optical because they are called featureless. So they have no lines. Maybe the featureless is not the appropriate word because not having lines is a feature. But here we have the spectrum of BLAC and flat spectrum radio quasars. Both of them are very strong gamma ray emitters. And they present a very high variability. So if you observe it at one night, in the next night, it can already have a very different flux. And you can, do you know what's a redshift? You that, for instance, you that do high school, do you know what's a redshift? The redshift of a galaxy. But the undergrads, you know, Vitor, you know what's a redshift? Okay. A redshift is in general words is a way that we use to measure the distance to the galaxies. So, but we need the emission lines to do that because we know how these emission lines behave on lab on Earth, and we see some difference when we observe this in space. And by fixing these differences, we can realize how distant one galaxy is from us. And we can do that easily for a flat spectrum radio quasars, but for BLX, you can imagine it's a nightmare. It's very hard to do. But scientists come up with clever things. Okay, this is again a spectral energy distribution. So we have energy as a function of the frequency of the photons. So here you can see that it spans 20 orders of magnitude, as I said in the beginning. And for blazars, the spectral energy distributions are very have this very strong characteristic of presenting two bumps. So you have this bump called by synchrotron emission from the jets, and the second bump peaking in gamma rays. There are some particularities, but it's a bit complicated, I think. Okay, so there is another interesting phenomenon that makes blazars even more complicated, especially BLX, which is the extragalactic background light absorption. You can think that maybe if you have a flashlight and turn it on in the space, the light will propagate forever because it's vacuum. But it's not exactly like that. And especially in the gamma ray domain, the universe is opaque to gamma rays. The universe is not transparent, it's not translucent to gamma rays. Okay, the gamma rays, they get absorbed by the universe. And this happens in this interaction that we call the gamma-gamma interaction, when photons interact with other photons. So the higher is the energy of the photon, the higher is the probability of this interaction. So if we have one TeV, imagine here in the y-axis, we have a one TeV photon. It cannot travel distances much longer than 0.1 redshift. You can understand redshift as a distance here. So these photons are absorbed by extragalactic background light photons. Okay, the universe is opaque to gamma rays, to very high energy gamma rays. And this makes BLX useless tools for doing cosmology. Flat spectrum radio quasars, you can use a bit more easily because they have a gamma ray energy peak at lower energies if compared to BLX. And this, if you remember this kind of plot here, the spectral energy distribution, we have two peaks. So this kind of absorption gives some problems in the gamma ray part of this ACD. So we have a huge, if the target is very far, let's say redshift 0.5, we can observe a huge absorption of these gamma rays. If you know the distance to the galaxy, you can fix it. So if the galaxy is a flat spectrum radio quasar, you can measure the lines and the redshift, and you can take the distance, so you can fix it. If it's a BLAC, how can you do that? If it's a BLAC, you like that, and you cannot estimate the distance. You cannot fix your observations. But there are some ways to recover the distance of a BLAC, and one of the clever ways that I found in literature, actually, it's my previous supervisor, this one here. He was trying to find the distance of BLACs observing the environment of BLACs. So we know that most of the BLACs, they are in galaxy clusters. So if you observe the distance of the other galaxies in the cluster, and if you assume, and this is the strong part, if you assume that the BLAC you're observing belongs to the cluster, you can infer the distance to the BLAC. But there is this catch. There is this assumption that, okay, maybe it's a background object, much farther away, but this is one of the cleverest ways to measure the distance to BLACs at the moment. Okay, on the morphology, we have these two classifications: the Fanaroff relay 1 and Fanaroff relay 2 galaxies, and these relate absolutely well with BLACs. I spoke about BLAC is the one without lines in the spectrum, and flat spectrum radio quasar is the one with the lines. So here, the Fanaroff relay, this one in the left, if the jet is pointing in our direction, it's a flat spectrum radio quasar, while the Fanaroff relay that has this jet brighter in the center instead of the edges, if pointing in our direction, is a BLAC. How am I on time? Oh, okay. Okay, so I told you about this phenomena here, the absorption of gamma rays. But for you that are experienced researchers, I know that every time that we find a phenomenon that depends on the previous phenomena. This is the case here. So when these gamma rays interact with photons in the universe, when they are traveling, they form a pair of electron-positron. Okay, they form a pair of particles. That gamma ray disappeared. We lost that gamma ray, but we have this pair of electron-positron. This pair of electron-positron, it can, just as the gamma ray production emission I showed you before, they can upscatter soft photons to the gamma ray domain again. So these resulting gamma rays have a much lower energy than the original one. But there is a clever way to measure the magnetic field of the extragalactic medium. So if there is a magnetic field, this was never measured. So we have an emission from a blazar, the gamma ray is absorbed and becomes an electron-positron pair. If there is a magnetic field in the intergalactic medium, this pair will separate, and eventually it can or not, it can upscatter another photon to the gamma ray domain. So we could see it coming from another direction. So we expect to see this gamma ray halos around the BLACs. It was never measured, actually. It was people tried a lot, but they didn't succeed. And depending on the magnetic field of the extragalactic medium, these halos are much broader. If the magnetic field is strong, the halos are much broader. Okay, but this was never observed. But it's a very clever way of measuring a magnetic field in the extragalactic medium. And this also causes delayed light curves. Imagine that we have a flare in gamma rays. If the the photons from the blazer will follow this straight line trajectory, but the photons coming from the halo will have to follow a much larger trajectory. So we expect to see a flare and an echo of this flare in lower energies due to this emission. I'm very close to conclude my presentation, but let's talk a little bit about blazer colors. This work on the left was done by Italians, and they call this la bistecca, a costella. And this is a very clever way to identify blazars in gamma rays, the counterpart of blazars in gamma rays. On Monday, Michele Doro presented something like that, a work that he did with students in Venice or Padova. And they were looking for the counterparts of gamma ray sources. So this white ellipse here is the uncertainty region of a gamma ray source, because we have a very low resolution in gamma rays. The telescoping gamma rays, they do not give a zoom. They basically point where the photon is coming. So the resolution is much poorer. So this is the uncertainty region for a point-like gamma ray source. We have a lot of infrared sources inside there. So in principle, we don't know which one of these sources is responsible for the gamma ray emission. However, if we measure the colors, the infrared colors of these sources, we can have a very valuable hint, because the blazars, they concentrate in this strip here. We have two color diagrams for the blazars. So they concentrate in this strip here and in this strip here, in these two different infrared colors diagrams. However, the one in the left is more powerful. So if we measure the colors of all of these infrared sources, if they fall in the strip, more like in the blazer strip, it's more likely that we can identify the counterpart of the gamma ray source, because most of the sources inside here for sure are thermal sources, while these particular colors are colors of non-thermal emission that come from blazars. So this is a very powerful way of identifying associating the counterparts to the gamma ray sources. We also observe a lot of galaxies with blazer activity, but they are not exactly blazars. They are something in the middle. So here we have the spectrum of a BZG, which is a blazer polluted with galaxy spectrum. So we have a elliptical galaxy spectrum, everything normal. But when we arrive at the Gaussian break, we have this flattened profile that we would expect it to drop more intensely. So we can. This is something that we can compute, and it's typically it escapes the knowledge of a lot of people. Okay, so we also have outflows. I don't know especially for PhD students and master students. If you are going to measure the redshift of an AGN, you have to measure using the low ionization lines, like hydrogen lines. If you use the high ionization lines, you have a risk that because the highly ionized material is very close to the black hole, where we expect to have very strong winds. So you can see the vertical lines there. This is the systematic redshift of the galaxy measured based on H alpha and H beta. And you see the carbon 4 line, for instance, is much shifted to the blue side of the spectrum. So we have this blue shift. So in a single spectrum of a galaxy, we can measure several different redshifts. So we have to be very careful with that. But these are strong indicators of outflows, of winds coming from right the core of the AGN. So the higher is the ionization of the line, the closer to the black hole this radiation is being emitted, and then the closer is the blue shift compared to the systemic redshift of the galaxy. And finally, there is also a very clever way to measure the rotation of the black holes. And this is done especially in X-rays, where we can observe the distortions in the iron K alpha lines. So due to relativistic beaming, Doppler shift and gravitational redshift, a line that should be more or less like a Gaussian, it becomes something like that. And this is a measurement of the line. So we can, using the distortions in the line, we can access the rotation of a black hole. And that's a lot of information, I know. Please feel free to make the questions you want. And as a summary, we reviewed the unified model of AGNs. We see that there are two types of accretion. Actually, there are more, but we discussed two types of accretion. These are the main ones. We have compelling evidence for the stars in AGN, and we can even see through them if we use the correct technique. We give a brief review about AGN jets, about the gamma ray emissions. This part in particular is very exciting for me because it's my field. We see that the SCDs, the spectral energy distributions, have those two bumps. And we saw the difference between flat spectrum radio quasars and BNLACs. And that's all I have to show you. But feel free to make me questions.
There were questions. Thank you so much for the presentation. I really like it. I've never studied a lot of AGNs, and today it's make everything very clear to me. So I have some questions. I can ask others like in the copy because it's a lot, but the main question is, I was looking in some AGN catalogs at Fermilat, and I saw that the AGN are from us in a distance of about 100 megaparsecs. Are they all this far away from us, or this varies, and why they are so far away? And the second question is, I saw some active galaxies like NGC 1365 that can also be classified as starburst galaxies. Is this true? We can classify some galaxies as both starburst and active.
Okay. Let's go for the first question first. Let me see if I understood your question. You're asking if about the distances.
Yeah,
to these blazers.
Always like 100 megaparsecs of other.
No. The distance actually vary a lot, and we detect most of the blazers that we detect, especially in Fermi, because Fermi is not that sensitive. In gamma rays, it's a monster, but compared to other instruments, it's not that sensitive. So by far, most of the blazers that we observe are in the local universe. Redshift is 0.05, for instance, and then the deeper you go in the universe, the lower is the amount of blazers that we are able to detect with Fermi. And the second question was if a galaxy could be classified as both starburst and AGN, right? And this can happen, but it's very hard to put this in a catalog. So if you are doing a catalog of AGN, you are not doing that. Even if your galaxy contains both characteristics, it's for a catalog where you have thousands of sources. If you have one mistake, it will be negligible in the population study. So it can happen, but it's not the standard means of classification. So you have a dedicated study for that.
So it's possible to find like some specific galaxies in both starburst catalog and the AGN catalog?
You can find.
Okay.
Yes. However, please be aware that there is a very well-defined difference between these two phenomena, because the star formation, it happens in the galaxy and not in the nucleus of the galaxy. So if the galaxy is very close to us, we can separate, we can take the spectrum of the core and the spectrum of the disk of the galaxy. Okay, if the galaxy is farther away, it's much harder to do that. So we can have everything mixed up in the same spectrum.
Question, and then maybe we can follow over coffee. I think it's first, otherwise we are late to the next. Ah, okay, so would you like to?
No, Renier, just an opinion from you, because I'm not an expert from the beginning from Blazar. I normally focus on other things in gamma ray astronomy, but I worked a lot with Paolo and colleagues. I find that we have a lot of data, okay, and we will have even more and even more precise data, but in several tens of years, we haven't gotten to understand these guys for several reasons. Sparse data set, but also something that you didn't mention, they also vary in flux. So yeah, so it's very complex because we cannot be there to measure everything, okay? So we have the physics of the phenomena that help us in a certain sense to try to see some trends. But even for Blazar, no, in which you are kind of outshined by the intensity. So do you think, as long as we start to accumulate more and more data, we can make the solution, find a solution with, say, our minds and calculation, or will the AI or neural networks will be better in seeing patterns that we cannot see because we cannot make solution on the acceleration mechanisms that give rise to the jets and the variation of the jets?
Okay, so to find the solutions for the acceleration, I think that in the era of CTA, we have a much better perspective, because just as you said, Blazar vary a lot. So the shorter are the observations of the Blazar, the better we can constrain the models. And in the CTA era, with a very large sensitivity, I think that we will be able to constrain much better the models. Up to now, we don't know if it's leptonic or hadronic. No, the best scenarios for AGNs. Maybe the leptonic is more famous, but the hadronic is also very competitive. What was the other question? Okay.
But the thing that I find really interesting is how you distinguish between oxygen radiation and hydrogen radiation. I work with the World Water Community, and obviously we study hydrogen interactions more than anything else. And the thing that we find or have found particularly interesting is that hydrogen doesn't need a physical form to interact with anything. So we're starting to understand how protons and hydrogen could be the same thing. But what's really interesting with your work is how you already distinguish between star formations and blazars, and which galaxies are making stars and which galaxies aren't making stars, and how hydrogen definitely is a player in that game, but it's really nice to see how you're looking at oxygen, and when oxygen is radiating, it sounds like that's the star formation, no? Or it's the opposite.
Actually, this is oxygen 3. So it's unfortunately a nomenclature of astronomy that oxygen 3 means that the oxygen is twice ionized. Yes. So to have oxygen 3, we need a ionizing source. So the thermal emissions from the stars cannot ionize oxygen to twice. Huh? Yeah, yes.
The next speaker is online. So thank you very much, Ranieri. It was a great presentation on the topic of the activities we are going to do next. And it's my pleasure now to welcome Mike Peel from Imperial College. Mike, you're connected. Excellent.
Hello.
Hi. Thanks for being with us. And Mike's going to talk a bit more in depth about the dark and quiet skies that we already heard some things about on Monday. And this, as some of you have already seen, is an important topic which we would like to make the people participating and following this event aware of. And maybe there is some interaction in the future that Open Universe and the Dark and Quiet Skies initiative can do to raise awareness and to work with citizen sciences towards solving or addressing some of the issues on this front. So, Mike, thank you very much.
Thanks. It's good to know you've already heard some of this already, but I'm going to give an overview of kind of the optical and the radio impacts of satellite constellations. It would be really good to see Brazil more engaged in this topic, so I really look forward to seeing that. So space is really changing rapidly at the moment because there are huge numbers of satellites being launched, particularly into low Earth orbit. So if you look at the filings for requests for operating satellites in orbit, there's plans for over 1 million satellites by the 2030s, of which maybe 50,000 or 100,000 will actually be launched, which sounds like a lot, and that is between 1957 and 2019, there were about 5,000 satellites launched in total. That's throughout a whole of the space race, and there's another 5,000 since then already, and there's going to be 50 or 100,000 more coming. And this has potential big impacts on optical, radio astronomy, just enjoyment of the night sky because you can see these by eye, and a whole lot of complications with space traffic management and space debris concerns. And if you look at the, so this is going back to the beginning of the space, so back to Sputnik in 1957 until now, you can see how the number of active satellites have grown in green. There's been a steady increase in the number of dead satellites and lots of leftovers and debris. You can see some big jumps in the debris, which is when there's been weapons tests or collisions between the satellites. But you can see that does go down over time as they re-enter the atmosphere. But you can see this huge increase here with the number of active satellites, which is mostly due to Starlink. So low Earth orbit communication satellites launched by SpaceX. And that trend is just going to keep on going up. Every time I give this presentation, I have to do another plot with a different Y scale just because of the numbers increasing so quickly. And it's not just Starlink, and they're the one that's up there at the moment with 7,000 satellites. There's also OneWeb, which has launched about 650 satellites, and they're going to be launching Generation 2 soon. But now it's been demonstrated to be possible to launch that many satellites and to have a global communications network. Other companies also want to get into the action. So Amazon Kuiper have launched 2 satellites so far, and there's many, many more coming. I think they want about 3,000 or 4,000. AST Space Mobile, I'll show some of their satellites a bit later because they're really interesting. They're really big. They've launched 6 so far. There's another 200 of those expected. Qianfan and Guowang in China are also launching. They've got about 100 satellites between them at the moment, but they want tens of thousands of satellites in the near future. Starlink wants another 35,000 soon. So is really ramping up as everyone wants to launch their own satellite constellation. Europe wants their own. Some countries in Africa as well have proposed their own constellations. So it's really becoming a competitive environment and a big concern for astronomy. This is because they have a big optical impact, so on the dark skies. This is not a Photoshopped image. This is a real image taken by Max Alexander in Wales in the UK. So this is a megalithic cairn at the bottom. And with a long exposure with a standard camera, you start seeing all of these patterns of satellites going above. And you can see some of these are really bright. I don't know if you can see up there, there's the Pleiades, which is one of the constellations you can see in the Northern Hemisphere um, quite clearly by the human eye. And you can see that the satellites are much brighter than that. And there's many other, unfortunately, Orion isn't there, which is one you can see from the south as well. But these are really bright and make a dramatic impact on the night sky for everyone. The problem is that satellites are reflective. So if you get them, particularly in low Earth orbit, you can highlight if they're at dawn or dusk when the sun is just below the horizon, they still get illuminated because they're about 500 kilometers above the Earth, and they reflect that sunlight back down to Earth. So you particularly see them at morning and evening, but you can also see some of them if they're higher up all the way through the night, or if you get a lot of Earthshine. Um, they reflect in really complicated ways. It depends on the materials they're made from, the angle they're reflecting at, but they can be really bright. And brighter than magnitude 7 is going to be visible with a human eye unaided. So that's kind of the recommended limit. We want them to be fainter so you can't see them with a human eye. And that mitigates the worst for optical telescopes as well. There's various consequences that can be caused by this. So this is an image from DECAM, and you can see this is a train of Starlink satellites. So when they launch these, they launch about 40 at once, and they slowly raise them in orbit together. So you see these trains of satellites that go across the sky, and this is when they pass through an astronomical observation. And you can see there's a lot of data that's been lost here in the observation, but you can still do some things around it. The problem is if there's going to be many more of these in the future, then these streaks will be everywhere and you can't do much anymore. There's particular cases like near-Earth asteroids they're quite close to the sun, so you want to observe them in twilight, either before the sun, just after the sun sets or before the sun rises, which is exactly the same time that satellites are going to be most bright. So there's a real risk there that we could miss something, an asteroid which could collide with the Earth in the future. There's issues with variable stars. If you're looking at how stars vary in the sky and you get satellites in your data, you can just lose data which tells you what variability is going on. There's more subtle effects like if you're looking for lensing by gravity of distant objects, you can get subtle distortions because of the satellites passing by. You can get impacts from spectroscopy if you're doing a 30-second or 30-minute exposure of a particular object because you want to measure the spectrum, it's very faint. If a satellite comes through, then you get reflected sunlight coming in, or maybe reflected Earthlight as well. And it makes your spectrum a mess, and you have to disentangle that. And there's even the risk that if it's a really bright satellite, it can actually damage the optics of a telescope and the CCD itself. This affects all different types of telescopes. So these are all in very remote locations, so they're away from light pollution from the Earth, but you can't escape the light from the sky. So it depends on the type of telescope you've got, whether you're looking at a very small part of the sky or very wide angle. So small field of views can have about 10% of images affected by at the end of astronomical twilight. If it's something wider angle, you're looking at a bigger part of the sky, you get more satellites coming in, so about half can be affected. And the super wide field, so the Rubin Observatory, which is going to start observing later this year, we expect all image frames for that to be affected during twilight and many frames even during the whole of the night, just because of these reflections from the satellites. These satellites can be very bright, and there's many different types of them as well. So we're trying to understand how the different satellites emit. So Starlink in particular has gone through about 4 different generations now. This is listing 3 of them, and you can see these magnitudes are about 4 or 5. The optical magnitude system is kind of inverse, so the higher the number, the fainter it is. So we need it to be below seventh magnitude in this. And so these are all very bright. Even when they tried painting one of the satellites black, it helped, but it didn't make it as black as it needed to be. Um, and they're going to be starting to launch bigger ones soon. So you may have seen they're trying to launch the Starship, which is a much bigger rocket than Falcon 9, and that will enable bigger Starlink satellites to be launched, which will make them naturally brighter as well. One of the things that we often hear when we're talking about this is, well, just put your telescopes in space, which makes it a lot more complicated, a lot more expensive. If something breaks, you can't send a student to go fix it so easily, unfortunately. So you have to make sure that they're really robust telescopes, really expensive, and you can only do a few of them. But if you put them in low Earth orbit, like the Hubble Space Telescope is, then you'll still see satellites above or in the direction of observations. And you can see some of these here. So these are actual data from Hubble. And you can see some of it's a really big area, which is where the satellite's very close, it's out of focus. But you can see others further away, which are appearing as streaks. And you can even see this one is tumbling a bit, so you can see variability as it goes along. And you can also get fun things like it's curving because of the movement of the satellite, movement of the telescope relative to satellite. If you go to Lagrange point 2, like James Webb Telescope does, there's no problem. But anything in low Earth orbit, you still have to deal with satellites. I mentioned before the AST Space Mobile satellites. So these are really large telescopes. This is actually a picture of one. So there's humans for scale at the back. So this is 8 by 8 meters. It's a phased array, so it's aimed at communicating directly with mobile phones without any modification to the mobile phone, which means you need a really big phased array to do that, a big antenna to detect the signal and to transmit. And that makes it very optically bright. So this is actually a picture of it in orbit using a telescope. You can see it's got a space body. You can see the whole of the phased array there. So we've been doing observations of this within CPS, and this is the magnitude here. So we're aiming for magnitude 7 down here, and it's all the way up at plus, well, negative magnitudes. So minus 0.2, I think, was the brightest it can be. And that's basically brighter than any apart from the top 10 stars in the sky. It's something you really obviously see when it's going above now. There's also fun things like the launch vehicle adapter for this, and they just ejected that into space and left it orbiting. That's also really bright. And it was untracked as well. We didn't know where it was in the sky. And there's various other things we don't know about these, but while we've been studying this, they've built and deployed 5 more, the Bluebirds, and they're planning for even bigger ones in the future. And you can see these are basically white satellites, so they're not really mitigating at all, which is a shame. There's always new types of satellites which are being launched, and we need to understand them each time. So the Starlink, there's the version 2 minis, direct to cell in particular. So now AST have demonstrated you can communicate directly with a cell phone. Starlink are also doing that. So they've lowered their satellites, they've made them bigger to put extra antennas on them to communicate with cell phones, and that's made them brighter as well. So these are coming out to about 4, maybe 5 at the faintest. I mentioned the Bluebirds. This is a bit outdated, but they're basically as bright as Blue Walker 3 was. There's also other things like NASA launched a AC3, which is a solar sail demo, and it started tumbling in orbit. So that meant it rapidly varied between 0 and 8, depending on which angle it was at. So there's complicated things going on there as well. The reason we're worried about the brightness is because when you look at it with a telescope, it becomes really, really bright. So this is with an 8.4-meter telescope, the Rubin Observatory. These are simulations showing what it would look like in the CCDs. So if it's the recommendation level, so the magnitude 7, you see this bright streak appearing. And you can remove that. You can get the data from elsewhere. You can still see it's really bright. With the current Starlinks, it's much brighter, and you see these rippling effects across the CCD as well. So you lose a lot more of the data. And if it's something like Blue Walker 3, then it saturates the whole CCD. You can't do anything with this. You just have to throw it away and hope you haven't damaged the CCDs at the same time. So that's why we need it to be magnitude 7 or fainter. So that's on the optical side. There's also a big impact on radio telescopes. So radio telescopes, again, they're observing from very remote locations, so they can get away from all man-made interference, but you can't escape the satellites. And the satellites are actively using radio communications as downlinks. So we've got some protection in the radio, which is these yellow. So this is the whole of the frequency range. And these yellow bits, you can spot them, are the radio astronomy reserve band. So these are very narrow. They're designed for spectral lines where you can't do the science anywhere else. You have to do it at that frequency. So you get a bit of protection there, but you need to basically observe much wider frequencies to get very faint astronomical objects we're normally working with in radio astronomy. So that means we have to work around all of these other transmissions. It's often called interference, but technically it's not because it's legally allowed, but it's still affecting radio observations. Satellites have got a really long history of being an issue for radio astronomy. There's this nice example of West Forward back in the 1960s that wanted to launch 480,000, million small dipoles so they could reflect 8 gigahertz signals back down towards Earth. This is before satellites really became commonplace. So their idea was they want to communicate long distance, and this was a way to do that. And that was stopped because of a global outcry saying we can't do this. But some of those dipoles are still up there. They're kind of clustered together, still in orbit. There's constellations like the Iridium satellite constellations been operating since the 90s, probably actually before that. And that works at 1.6 gigahertz, right next to a protected band for radio astronomy for OH measurements. And it transmits in that frequency as well. So you get interference in a protected band, and there's nothing that can be done about that. And most of these satellite constellations are transmitting around 12 gigahertz. You can just see how many there are across the sky at any given time. This is the elevation at a telescope. And you can just see, this is geostationary, but you can see all of these low Earth orbit satellites everywhere. So we're still really trying to understand what the impact is going to be with these. So we know they're doing active 10 to 20 gigahertz transmissions. I can show you some of the data we've got for that so far. They're talking about 40 gigahertz. They're talking about 120 to 180 gigahertz. So it's really filling up the high spectrum frequencies. And you can see this is an example. You can observe these with a simple satellite dish. So if you just take one of those with a low noise barometer, which is a standard thing to use for receiving TV, and put a hack RF digitizer, which is a few $100s, and a Raspberry Pi computer on the back end, you can sweep through the frequency range and you can measure these. So this is what we did here in the UK. And you can see these are the satellites passing over between 11 and 12 gigahertz. And you can just see how variable they are and how broadband they are. There's sometimes where it's completely clear, sometimes where you've got lots of interference. So even with simple satellite dishes, you can do interesting things here to understand things. If you go to bigger telescopes, and this is actually a 2-meter telescope, so it's not huge with radio astronomy, where you can have up to 100 meters. But this is showing before in 2014, where you've got geostationary satellites. This is from Tenerife with the Coyote telescope at 10 to 14 gigahertz. So we lost that band there. We couldn't observe it at all there, but we could observe in the rest of the sky. Apart from side lobes, so light coming into the side of a telescope from the satellite, and reflecting to the receiver, which gave some emissions out here, which we removed by putting a baffle onto the telescope. But if you look now at the sky, so this was data from last year, you still got the geostationary. There's more geostationary satellites up there. I think this is the moon off to the side. But you can see all of these other features, and that's all the Starlink satellites. And you can see these are really bright. They're as bright as the moon, bright as the sun often. And they're everywhere in the sky. It makes it a lot more complicated to disentangle. There's also effects at low frequencies. So LOFAR is a array of low frequency antennas in Netherlands and across Europe. So they have a number of different antennas on one site. And when you see when you've got a Starlink satellite going over, you see a signal appearing in all of these receivers, which you shouldn't do. And if you look at so this is a waterfall plot, time versus frequency. You can see at certain times when there's a satellite above, you get this broadband emission coming in. And there's another one there. And this is completely unexpected. It's basically the buzz that you get from any electronics. So the clocks, the switching power supplies, things like that in the electronics, they just randomly transmit radiation. It's broadband. It's not a permitted band, and SpaceX was not actually expecting this. So they're trying to reduce this. You can put it in basically in a Faraday cage, so put a metal shield around it to avoid this. But with the next generation, Gen 2s, they actually became brighter with this emission, so it's not working so far, and that could affect you basically get a low frequency buzz all the way around the Earth for low frequency telescopes. It's not great. You also get thermal emission from these. So these are basically 300 Kelvin black bodies in space. They can be heated because they've got electronics on board that can just be passive radiating. So this is measurements with the South Pole Telescope, which can't see most satellites, but can see some of the ones in polar orbit, basically. So the Indian Space Agency launched the LVM-3 recently, and this is a 4 by 30 meter rocket body that was left in space and was just tumbling in space. Um, and you detect this really clearly in South Pole Telescope. So this scale here is in Jansky. It's about 15 Jansky on average, and the sensitivity of this telescope is about 15 millijansky. So there's 3 orders of magnitude 10, a factor of 1,000 sensitivity here. So you can't even see uncertainties on this. And you can see it's tumbling as well because it's not constant. And we know that Starlink satellites are also thermally bright, so they're about a Jansky. And again, if these are everywhere, then they're going to start interacting with cosmic micro background telescopes and similar. So there's a lot of problems here, and we're trying to figure out ways of mitigating it. So the simplest thing is launch fewer satellites, which is probably not going to happen because these are very commercially relevant nowadays, and they're doing a lot of good work with communicating to people who wouldn't otherwise be able to get broadband internet around the world. But you can do things like coating, so you can try to reflect the light in different ways. There was VisorSat that put visors on the Starlink satellites to catch the reflections and reflect them away from the Earth. They're no longer doing that. They've gone to Bragg coatings to try to diffuse it more when it's leaving. You can do things like that on the satellites. You can tilt the satellites so they're at the right angles, so attitude control to minimize reflections. You can put steerable radio beams on, so you can try to not illuminate radio telescopes. And you can try to control this unintended emission as well. So we're asking satellite operators to do that. With the telescopes, we need to do more observing planning, so we try to avoid the satellites when we can. That's tricky because we don't exactly know where they are. So optical telescopes have arc minute resolution, but we normally know where a satellite is to about 3 or 5 arc minutes on the sky. So you can try to dodge it, but you may not be successful. If you can predict when it's going to pass, you can close the telescope shutter when it's going overhead to try to save some of those longer observations. But in general, we need more resilient receivers. We need to try to stimulate this, try to understand things. We're going to need to redo observations because there'll be a lot which is lost because we get satellites in the way. And there's a lot of post-processing needed, all of which takes up time, which is money, basically. So it's tricky. So we've got the astronomy community's response to these issues was to set up the Center for the Protection of Dark and Quiet Sky from Satellite Constellation Interference, or CPS, which is part of the International Astronomical Union. So this is co-hosted by the SKA Observatory, which is a radio observatory in the UK, and Noir Lab, which is a US optical observatory. And we've got about 400 members now, kind of ranging across a whole range of astronomers, observers, people in industry, policy experts, lawyers, government officials, all working together to try to address these issues systematically. And we're divided roughly into 4 hubs. So we've got SAT Hub, which is one I co-lead with colleagues in the US, and that is observing and trying to understand the impact, so measure the brightness of the satellites, and refine their positions, try to understand the positions better, and develop software which can support observations. We've got Policy Hub, which is engaging in policy and trying to get laws changed so that it can better deal with the consequences of the satellites. We've got community engagement, which is looking at the effect on everyone else around the world, particularly indigenous cultures and those that just enjoy the night sky. to try to understand the impact on them. And we have industry and technology, which is aimed at getting the industry and technology people to actually, all the satellite operators to talk to each other and share things at work so they can adopt that across all the different satellites rather than having silos of information, some doing better than others. Try to share that information, which doesn't normally happen in that area. I'm not sure how much time I've got because I think you're due for a break now. I'm hoping I can go on for about 10 more minutes, if that's okay.
Yes, of course.
Okay, great, thank you. So I mentioned briefly SatHub. So we're really trying to do the observations and analyze the observations and try to quantify them. So we've got a mix of astronomers, amateurs, and others engaged in this hub. We're doing open source software development. So yeah, I've got it on the next slide. So having data repositories, places you can put information, and try to organize different groups to do observations and research projects on satellite constellations and really understand what's going on better. So one thing we did is Nature publication looking at Blue Walker 3, where we got a wide range of different observers around the Earth to all look at the Blue Walker 3 satellite and measure how bright it was over time, particularly when they were unfolding the satellite with all of its phased array when it became a lot brighter. And that was quite a nice paper for showing the impact, and that was some of the plots I was showing you earlier. We're doing a bunch of other observing campaigns on different satellites at the moment. We always welcome new observers to help out with that. We've developed a SatChecker satellite position prediction service. So you can say, I want to know where the satellite will be at any time, given time, and it will give you the most accurate position for it that we can get at the moment. You can also now say, I'm going to be observing this field of view on the sky. Which satellites will pass through that when I'm doing my observations, and it will give you the list of the satellites and the timings for them now. So that can be useful for predicting when they will be, for either deliberately observing them or for avoiding them. We've also just been launching the Satellite Constellation Observation Repository, or SCORE, and this is to try to collate all the observations of satellites together. Because we've got the dedicated observations, which we want to have in this repository. We've also got, well, there's a lot of accidental observations that happen of the satellites. We want to comb through of those, or get people to comb through them, and report the brightnesses of all the satellites in there and put them into its repository, and then look at them in a systematic way. So we can say, how bright is this particular satellite over time, and do plots and understand the statistics of the satellites. This is being funded at the moment in the US by NSF SwiftSat, in particular to try to have an active satellite avoidance service. And we're also doing impact modeling on radio astronomy and coordinating. We're trying to get different stakeholders to coordinate mitigation efforts and say, well, this one is mitigating best, please use that, rather than these other approaches that aren't working so well. I mentioned already, Interesting Technology Hub is trying to get the different industry communities to talk to each other, also to share best practices and tools, and all satellite stakeholders are welcome to join that. Community engagement is particularly organizing, bridging between all the different stakeholders. And one particular thing it's done is a SATCOM 101 video series. So this is a series of 8 learning modules that you can access online. There's a QR code here. I think you'll get these slides afterwards. I recommend them for understanding this in more detail. You go through all the different aspects of satellite constellations in relatively short videos, and I think they're translated into Portuguese now, or will be soon. So do recommend having a look at them. And then Policy Hub is looking at the policy things that we can put in place. So in particular, just raising awareness when policy is being made of what astronomy needs to try to reduce the impact. And trying to coordinate the engagement by national astronomical societies and observatories in this area. And the aim is to have better regulation in place and coordinate spectrum management processes, and also look at the future of what's going to be coming up. A bit more on that in particular. So one relevant committee is, or particularly relevant, is the United Nations Committee on Peaceful Uses of Outer Space, UN COPUS. And there's now a dark and quiet skies agenda item for that standing agenda item, so it's being continually discussed. And there's a group of friends that are really advocating in that area, promoting awareness, discussing the implications and the approaches that can be done. This does include Brazil, so thank you very much for being engaged there, and I hope to see more from there in the future. There's also so radio astronomy is regulated by the International Telecommunication Union, which has been in existence since beginning of radio communications, basically. And there's various discussions going on in that. They work on 3-year cycles, so the next one is in 2027. And there's various studies going on to understand how do you protect a radio observatory from satellites? If it's got a radio quiet zone, can you enforce that above the Earth, or is it just really local? What's happening at high frequencies, because there's lots of other threats coming in with car radars and things like that as well at these high frequencies. So we really need to understand that. And there's also the issue of the moon. So if we can't do observations from Earth, one of the natural locations to do them from is the far side of the moon, which is always facing away from the Earth, so it's always shielded. And that would be great if you can get the telescopes there and maintain them there. But you also need to make sure that the radio communications there aren't at the same frequencies. So they have to be different frequencies required by law to make sure we can still do the observations from there. So that's an important area that's really being looked at in the future. And there's also the unintended emission seen by LOFAR and others that we're trying to understand and better quantify. There's various national regulations coming in place. So the US currently imposes coordination between satellite operators and National Science Foundation in order to obtain a license. And that helps the US facilities in particular mitigate the impacts, but doesn't necessarily apply globally. There's issues in South Africa that want licensing conditions for operators there. There's ongoing discussions about it, but that's because of the square kilometre array being based there, also in Australia. And there's various efforts. This links in generally with space sustainability. So there's the Zero Debris Charter, which the European Space Agency's led, and a booklet recently published, which includes dark and quiet skies. There's various other space sustainability initiatives going on, which dark and quiet skies connects with. So there's a huge number of satellites being launched. These, I hope, have convinced you that they have a significant impact on optical submillimeter, which is a thermal emission, and radio astronomy. And we're trying to work within CPS to quantify their impact. We really need to get more satellite brightness observations in SCORE. So if you've observed a satellite, please do give us some data there, and we can help you do that as well. There's various policy approaches underway, and if you can get involved in those, please do. The situation in the US at the moment is rather bleak, particularly because of Elon Musk and his engagement in high-level politics in the US, which he's also the founder of SpaceX and Starlink. So that's going to have all sorts of complications in the future. The solutions here really need to be global rather than just in the US, just in the UK or anywhere specific. And it's really crucial that the global majority views are heard. So please do step up and engage with this topic wherever you can. If you are interested, please do join CPS. It's free. We've got a Slack channel with active discussions going on. We have regular meetings you can be invited to, a whole seminar series now as well within SATUB. And you're welcome to participate in those. And I am complete. Thanks for listening. Any questions?
Thanks, Mike. So this is really interesting. I have one quick question. We don't have time for many more because we are entering to coffee and we have a remote speaker after. Do you have any capacity building, citizen science activities related to the dark and quiet skies? Have you been thinking of developing those? How is your interaction with the greater public, and how can the greater public contribute, apart from perhaps the observations that you mentioned, no, that can contribute with observation?
It's something we've been thinking about. There's the issue that astronomy data is really complicated in different ways from different telescopes. So it would be really nice if we get into a citizen science project where you can look at the brightness and try to characterize it that way. We haven't got there yet. One I'm aware of is the Unistellar network of optical telescopes. So these are small telescopes you can buy for a few thousand US dollars that you can then use in different places. And they've got a coordinated observation campaign there to get data in. And we're still looking at ways we can better engage people with this. If you have any ideas, we'd really appreciate them.
Yes, I think it's something that perhaps in Brazil, given that Brazil is part of the group of friends and there are people involved like Tanya, who spoke on Monday. Maybe we can think of something to engage this citizen science and capacity building activities with dark and quiet skies. So I guess let's be in touch about that.
It'd be great. My email address is down there. If you join CPS, you're on the Slack, you can engage with conversations. Yeah, welcome any engagement here.
Thank you. Thank you very much. And let me point out that Marcelo and Marcos were the responsibles for the translation of the videos that you showed or you mentioned in Portuguese. So they are
Perfect.
participating in the day and the translation is
Obrigado.
available. Let's see if we can upload them somewhere also for the public.
That'd be great. Thank you.
Good. Thank you. And let's go for coffee before coming. Thank you. Can you try to switch on the screen, Fabian, and maybe try to share your screen?
Sure.
So-
Hi.
Hi. Everything is working good. So let's just give a couple of minutes and then we start.
Sure.
Thanks. Good. So Fabian, please, I think you can start. Thank you very much.
Thank you very much. And thanks for the possibility to present here. And yeah, just let me say that we are very happy to be part of the Open Universe community and initiative. And I'll try to give you a quick overview on introduction on time domain and transient multi-messenger astronomy. And then just give you a very brief introduction to what our platform is. But mainly, there are many slides in the backup, and I hope you get access to them soon, so you can go through them and have your own tutorial at your own pace to study the various features of our platform. So this is the development team, so the core team that is running Astro Colibri and trying to improve it over time. We are mainly based in Paris-Saclay, which is outside Paris, France, funded by the university and various national and European research projects. So Astro Colibri is a research platform meant for professional astronomers, but as you will see, it's open to everybody, and therefore we invite everybody to use it and join the community. So this is probably one of the rare talks where we actually invite people to take out their cell phones and have a look at them and go to the app stores and search for Astro Colibri because our platform is available on both smartphone platforms, so Android and iOS. It's free. You can have a look and play with it either during the talk or afterwards. We are also running the platform on the web. So there's a central website, astro-colibri.science, where you'll find links, and astro-colibri.com or .org and some others bring you to a web interface. I'll come back to that at the very end. But just feel free to search Astro Colibri in your app store and have a look. So what are we doing? We are providing an app and a platform for real-time follow-up of transient sources, transient astrophysical sources. What are these? So this is basically everything, every astrophysical phenomenon which appears at the sky at a certain location at a random point in time, and then fades away, typically rapidly from seconds to days to weeks to months. These are typically very explosive and energetic phenomena, exploding stars, thermal nuclear explosions on the surface of stars like novae, gamma ray bursts, outbursts in other galaxies, fast radio bursts, these very millisecond pulses seen in the radio domain, and many others. So it's a wide range of underlying physical phenomena that we just classify as transient sources. We study them in the electromagnetic domain, so the traditional astronomy, but in all wavelengths, so from the radio to the optical to the X-rays to the highest energy gamma rays. but since a few years also with additional cosmic messengers, high energy neutrinos, which are fundamental particles, cosmic rays, which comprise electrons and protons and nuclear particles, and gravitational waves, these distortions of space-time that also can inform us about these violent phenomena. And combining all these informations gives us rise to a new field that we call multi-messenger and multi-wavelength astronomy. We do this combination of these various messengers basically to study the same phenomena from many different perspectives. So we try to gather the complete information or complete picture of that phenomena in different wavelengths from different angles, which then allows a better understanding, theoretical modeling of the underlying processes, and therefore we can learn really something about these phenomena. So there's a few examples here. So I stated that we have these phenomena occurring in the universe, but the question is how do we learn about them? So how do we detect them? How do we observe them? And there are two basically distinct categories of observatories to help us doing that. And they operate again in the whole wavelength range. A few examples are given here. On the ground, from the radio to the visible to the highest energy gamma rays, and in space covering basically the same wavelength ranges. And these are observatories that survey the whole sky basically every day, every night, to see if there's new sources, new emissions that have been popped up, or existing emissions have faded away, etc. So these are all sky surveys that detect new transient phenomena. Typically, as they have to scan the whole sky, they do so with relatively low resolution in both the positioning and then the detailed energy measurements, for example. But we can study these sources then in more detail, with pointed observatories. So these have a much smaller field of view, are dedicated to a very limited region of the sky, covering again the full range of the energy spectrum or the wavelength spectrum. But these observatories can then provide additional information, much more precise information about the characterization of each of these detected phenomena. So how I mentioned that most of these phenomena fade away quite rapidly. The question is how fast do they do that? So there here is, for example, an optical emission associated to gamma ray bursts. So these are massive stars at the end of their life that explode. There's a jet being formed, giving rise to gamma rays. That's why their name comes from. But then this emission is also seen in optical wavelengths. And you see that not sure if you can read the scale down there. So the time scales are a few hours and a few days, right? So these fade away very rapidly after the explosion. Therefore, we have to get the word out about these new detections and then get observers around the world on this target very rapidly to catch them. This is not the case for all of these sources. Supernovae explosions, for example, which are also more spherical, isotropic explosions of massive stars, rise rather rapidly within a few days and then fade away on timescales that cover weeks, maybe months. So there, the aim is, of course, to catch this very interesting early phase, but then also to continue observations for a very long period of time to get a handle on this fading emission. That fades differently in different color bands, for example. And then the comparison of these different evolutions can inform us about the intrinsic physics going on there. And this is also a very nice example for citizen science, because typically these long campaigns where you study a single source for an extended period of time are very difficult to do with professional large-scale observatories, because the time on these instruments is very competitive, and therefore it's very hard to actually run these very extensive campaigns. And observatories run by citizen scientists and amateur astronomers can complement these observations very nicely. So then the summary is, so we want to study these transient phenomena, these violent explosions. So we need to know where to point our telescopes, and we do that quite rapidly, because the faster we are on target, the more we learn about the full evolution of these phenomena. And that's where Astro Colibri comes into play, where we try to improve this whole process going on. So how does this work in real life? This detection follow-up scenario. So you have one of these various scenarios or phenomena exploding in the universe at a random time in a random location, emitting photons, gravitational waves, neutrinos, all kinds of cosmic messengers. As I mentioned, these are then detected by these large field of view instruments operating day and night. These are then emitting alerts. So these are short notices telling the astrophysical community globally what and where something was detected. These alerts and these informations go through a variety of different streams, what we call brokers. So these are computing systems that distribute these alerts in real time and or as fast as possible. Most of the large-scale professional observatories listen to these alert streams, receive them, filter them, process them, and then often react automatically on them. So if there's a high-profile alert, a very interesting event being detected, most of the professional observatories stop any ongoing observations, move their telescope to this target position, and start follow-up observations to learn more about this study. But of course, most of these, or many of these follow-up observations are also done manually, where you have astronomers in the loop sifting through this list of new detections and deciding which ones are most interesting. But going through this list is quite tedious, and it keeps a huge range of astronomers outside, because amateur astronomers and even less the general public doesn't have access to these streams, to these brokers, to these data formats. They're typically not meant to be human readable. These are XML files, JSON files in formats that are meant for machines, so for computers running at the professional observatories. And often they're not even publicly accessible to the interested public. And of course, there's a whole wealth of additional platforms built by the astrophysical community over the years that provides a large range of additional information from all kinds of measurements, archival data, catalogs, archival images, etc. That can be accessed, but you have to know where to find all these platforms. You have to search then in these catalogs. You have to find the right coordinates associated to the current region of the sky that you are studying. So that makes this whole process quite tedious and not so user-friendly. And that was the starting point a couple of years ago to implement AstroColibri, where we now have a platform that collects all the information from all sources and all observatories around the world in a single database, in a single platform, and you don't have to listen to 5 or more of them in parallel. We use this platform also to provide a user-friendly interface to all this information. So passing the information from this structured machine-readable data into a more human-friendly interface. And then point back out to the community into these existing platforms, but directly to the event or the region in the sky or the time range of interest. So you don't have to recopy coordinates, have to research for the same information again. With one click, you end up at the relevant information, and therefore facilitate this whole process. And of course, the platform then is also customizable. So as we have a wealth of information of very different phenomena, GRBs, gravitational waves, neutrinos, supernovae, fast radio bursts. Not all of them are interested for everybody. Not everybody can detect a high energy neutrino because you need a cubic kilometer instrument at the South Pole. So there are, of course, customization. You can filter the events and the alerts to your needs. And the interesting part is, as I mentioned, the platform is running on modern technology. So we have smartphones. Smartphone can receive notifications. So you can add notifications to your phone app and then be alerted by certain streams of phenomena, new detections as soon as they happen. Therefore, you get, after a few seconds after the satellite has detected a new gamma ray burst, you get a notification, and you always stay up to date and can follow what the professional community is actually doing on a day-to-day basis. These informations are also updated regularly, so more measurements, more data is being taken on these events, so you get improved information, and all this is being pushed to you in real time, so you don't have to search for it manually. So just to conclude this, as I mentioned, we provide all this information in an app, in a front end. So there's a web interface at astro-colibri.com that I invite you to have a look. So you have a list of latest detections in time ordered. You also have the timeline of these events up there. You can select time ranges. You can play with that to see how many supernovae are detected every week, every month, every year. You have a sky map that you can customize where you see where on the sky they are. If the things are detected in the northern hemisphere and you have a telescope in Brazil, this is probably not so interesting. You can immediately see all the details of the events. You can get this long list of these external URLs and links to these external platforms where you can play with them, see what you learn about them. You get the direct link, for example, to Aladdin and ESA Sky, where you get an archival image of, for example, the host galaxy of a certain supernova, etc. The exact same information and the exact same functionality, as I mentioned several times, is available on your smartphone. So you can have access to that on the go in a very user-friendly way, and therefore always stay up to date of the new detections in the transient sky. Underlying all that is a computing interface called an API. The documentation is on our main website, so astro-colibri.science, where you find documentation about how to access our databases. We have example, Jupyter notebooks that you can go interactively in your browser directly to see how you query for certain types of events in our databases, how you can calculate visibility plots, how you can filter these events, and for example, get only one type of source phenomena, etc. And I forgot to say it, all this is of course free. The API access needs a user account, so you can just sign up with your email address, and then you have a user ID and can access the full functionality for free as well. Again, the apps are available in the app stores for free. I just mentioned these notifications where you can get real-time information about new events. So if you are in the main screen of the app where you see the list of latest events and the sky map, you have a menu icon at the top right that brings you to a whole list of additional customization and setup configurations. One of them is these notifications. We have a whole list of detailed notifications that you can subscribe to, interesting events. For example, if you are interested in gravitational waves, if you're interested in gamma ray bursts, in supernova explosions, in neutrinos, etc., etc. I just invite you to subscribe to as many of them as possible at the beginning, and then you'll see that the sky is really quite active, and that you're rapidly overwhelmed with information, but then you can deactivate them over time, and if you're not interested anymore. A fun integration is also you can connect that to your smart home. So if you have connected light bulbs, for example, you can make them flash and go off with each new detection. If your partner at home likes that. So there are all kinds of ways where we try to improve the making the community and also professional astronomers, for example, who are in the control room of a major observatory, that they don't miss an important event that they may want to observe. Let me finish with a few words on the community. So I mentioned that this is a platform that is meant for primarily for astronomers, but equally important is the amateur and the global community. One way to get in touch and be involved there is through our discussion forum. So you find these icons in our interfaces, or you go directly to forum.astro-colibri.science, where we have a forum with various subcategories where we announce interesting new events, where we discuss new phenomena, news from the time domain astrophysics community, where we also compile a weekly list of interesting targets jointly with a French amateur astronomy network called RAPAS. Its head is connected, Thierry Daven. I see him on the Zoom today. So jointly with these amateur astronomy networks, we are trying to coordinate the most interesting observations, trying to also get feedback. We can read in the observations taken by amateur astronomers into the same interface as we do for the professional observatories, for example. Then again, astro-colibri.science is the main website where you find all kinds of documentation, where you find the links to both app stores, to the web interface, to the API, as I said, to all the documentation. We also have a YouTube channel with a range of tutorials which go more into the details of various aspects of the platform and help you to get started. Last but not least, we are running a series of workshops which are again, dedicated to both the professional and the amateur astronomy communities, where people brainstorm first about the science and then the technologies we need to use, need to improve to facilitate these observations, and then actually work on precise small projects to improve the field or the AstroColibri platform. The next one is coming up in October. Most of the discussions will happen in person, but there's also an opportunity to join remotely. I invite everybody just to sign up, especially for the remote participation. There's of course no limitations. There's no registration fee for either of them. You find all the details on this link. And of course, all the talks from the past workshops, which give you a nice introduction and overview of time domain astrophysics and the various platforms, are available on our YouTube channel. So I stop here. I think, or I hope that AstroColibri is an easy to use interface to time domain and transient astronomy. Again, you can get these notifications for every event that you're interested in. You can be in the loop. You can learn step by step what these events are. There are short descriptions for all of them, summarizing the phenomena, summarizing the detection. So over time, if you look at these informations, you learn more and more what these phenomena are, what these observatories are, etc. You get all the information for each detection in one place. And again, it's built by and for the community. So we're very happy to get new ideas, feedback from you. Also outreach activities. If you have a telescope, a network, an amateur astronomy network that you want to connect more deeply with us, feel free to reach out. And again, it can be an excellent learning tool to get used to a time domain and transient phenomena. And I stop here and thank you very much, and hope for questions and comments. Thank you.
Or that you have YouTube tutorials. I think that this is really the way to go. Thank you for the presentation. This very nice software. We are a little bit behind the schedule, but if you have one very quick question, we can do it. No. Okay. So thank you, Fabian again. And next, let's move to the next presenter, which is Paolo Giammi.
Hello, I assume that you can hear me.
Very well.
Okay, thank you very much. So I will be continuing on a similar topic by describing something that we call firmamento, which is, we say it's a new concept, and you will see why it is a new concept platform. So available online, also on the phone as well, to discover, analyze the multi-frequency, multi-messenger astrophysical sources using discovering algorithms, machine learning tools, and AI. It was developed within the vision of Open Universe, and therefore it aims to support scientists, students, and citizen scientists. In other words, we try to make it as easy as possible so that people who, without specific training in astronomy, can benefit of it and maybe even do some research, as we will see later. So Firmamento, you can find it here, Firmamento, NYU AD, NYU EDU. As you can see from the background picture, it's a creature of the desert. It was mostly developed NYU and in Abu Dhabi, the New York University in Abu Dhabi, by myself and some students and some collaborators. So what does it do? It gives access to open data, otherwise it will not be possible. But what we're trying to do is to cover the entire possibilities, that is the imaging, spectra, and time domain. Also, we have AI tools to help people to go through the system and learn maybe the theory behind it. Okay, let's start with the imaging domain, which is covered by the great Aladdin tool from Strasbourg. It was adapted to Firmamento with this interface. In this case, it's just you see the UNY's images in color, but you can click and change it very quickly. Go to the UV emission here. This is a ERAS X-ray data published a few months ago.
Are you trying to share slides with us?
Sorry.
We cannot see your.
Sorry about that. I'm really sorry about that. That should be better.
Now it is much better.
Okay, I'm sorry about that. I was convinced it was already on. Okay, sorry, I'll start again very quickly. So Firmamento is just a new concept platform to discover, analyze multi-frequency sources. It was developed within the vision of open universe, and for that reason, we try to support scientists, but not only, also students, citizen scientists, in principle, everyone. Now, this is what I was assuming that you were seeing before. It's some the desertic view. This is the desert around Abu Dhabi when some students went out at night observing the sky. You can find Firmamento here, Firmamento NYU AD, NYU EDU. So it's something supported by New York University in Abu Dhabi. As I was saying, we're trying to cover all the domains of astronomy and make it as easy as possible to get data. And we try to get the most up-to-date, the most complete, the deepest data available, that is available, openly available. So this is just a few examples. UV data. This is from the survey of UNWISE, which is a kind of 5 years of WISE satellite. As you can see, it's quite deep. Then we can, I hope, okay. We go to Galaxy, which is a UV. Then we go to X-rays from the ERAS-1 survey, which was published a few months ago. And then we go to something that we're trying to do in the next couple of days. This is an image of Swift image of the M31 Andromeda galaxy. Just as an example, this is what we want to ask people to do. We have tools to analyze Swift data and build HIPS images. And then at the end, all those data will be published online, and that would be a product of the people participating into this workshop. Okay, this is the same image as before, but in color. Before it was a grayscale, deeper, but this is in color. The red source is a soft source. The other source is less soft. So you can distinguish between sources with different spectrum directly from the image. And this is what we want to do. All the software is set up. We're waiting for people to get engaged on this from tomorrow. Okay, then we go to the, there are many more surveys available. Just to name a few, it's the RAX, low energy, mid energy, and high energy. The EMU survey at 1 gigahertz, essentially, as I was saying, UNWISE, there's Panstar, DAISY in the optical, Galax, and many surveys in the X-rays, as you can see there. So, and you can flip from one or the other very quickly. Let's go to the energy domain. The energy domain, it's if you're an astrophysicist, energy, the spectra are the things that allow you to understand well the physics behind it. The image is interesting. The energy distribution gives you more information. We think our system of generating SEDs it's one of the best available. Perhaps generates the best SEDs on the market, let's say, online. This is an example of Markarian 421. You can see there are 76,000 Swift plus NuStar flux measurements. Those are coming from papers that we wrote. We basically analyzed all the data that were available at that time in the Swift and NuStar satellites, and we put them online, and they're available on the virtual observatory, so anyone in principle can use it. We used Firmamento to reach those data. And the same is in the gamma ray. In the Rexa, Kian has been analyzing in great detail the light curves of Fermi gamma ray data, and all of those points are available here. In this case, there are 700 Fermi lab measurements. So when you generate an SED like this one, the system downloads, like as you see on the left, it calls many different databases around the world, and whenever there is some data on that particular position, the light is green, and it gives you the people who actually publish those data with the reference. It downloads the data, which are coming from many different formats. The formats are homogenized. The data are dereddened for the absorption in the galaxy, and then the SED is built for you. Okay, so but that's not it. Once you have an SED, you may want to understand what is telling us. So some crucial parameters are how strong is your source, and where is the maximum? What is the maximum, the energy at where the maximum emission is radiated? So we have, after getting the data, we also have machine learning tools like BLAST. There are a couple of papers, Glauc et al. And Kirsch et al. And myself. We trained the system with many hundreds of blazars, and it gives you the position of the peak and the intensity of the peak. We also have another method, which is not machine learning, but it's an algorithm. It's based basically on the slope of the infrared data of those stripes there. If you take the average slope and it points to the right or points to the left, it tells you where the peak is located. You can calibrate it, and this is another way of estimating the peak of the SED and intensity of the peak. So this is what I was trying to say before. We make it easy. You just click, you get the data, but it's not just that. You can characterize the data. You get the peak and intensity and so on. Okay, then we move to the time domain. This is OJ127. It's a blazar. We've been talking. We had a talk about blazars before. One of the things that was repeated a few times was blazars are very variables. In fact, apart from explosive events, blazars are the most variable sources in the universe. And they're variable everywhere, but in the radio here, not so, maybe a factor 2 or 3, but not so much. As you go to the infrared, and you start seeing quite a bit of variability, maybe a factor 10 or so. And then in the X-ray, there's enormous variability there, also in the gamma ray. Is it boring? Is it always the same? And not at all. If you look on the right, the 4.6 micron neo-wise data, which is this point, this frequency here, it goes up and down here. The peak is here. Now, neo-wise produces 1 or 2 measurements every 6 months or so. So the light curve is very sparse. Nevertheless, it tells you over a few years time scale how much the source can vary. In the X-ray, we have all this data here that we analyze, as I said before. There is a very huge flare here. Very nice. You go from 0.2 to factor 5 or 6 here. And if you go down to the blue lines, the blue light curves, you see that there's a huge variability in the gamma ray as well. But the light curves in the gamma ray is very, very different from the X-ray and from the UV. So each frequency, each energy band tells you a different story, and you have to try to put everything together into a theory. That's a challenge. Okay, this is one way of showing all the domains in the same place, in the same page. You can put all of them. So you basically retrieve the SD here on the top left, and then you click on add the ZTF data. ZTF stands for Tricky Transient Facility data. And then you click on refresh, and the system goes off and retrieves the data. You see here a lot of variability in the G band and the G filter, sorry. And the optical image superposed with the arrow circles in the X-rays, which are blue, and the arrow circle in the gamma rays, which are light pink or so. Okay, so all three domain at the same time. Then the other possibility is to use tables and define samples and things like that. So if you go to data access, you can get a lot of tables. In this case, you can go to high energy catalogs. There's a TEVCAT, very famous, Nahazo catalog, the latest Nahazo catalog, Fermi for AGN, DR4, other Fermi catalogs, the list of ice cube tracks, and Agile second Agile catalog. And you can click on one of those, and then you can get all the data that you've seen before. If you want to load your table, then you can use import user table. How do you do that? There are two ways of doing that. The easiest is the one at the bottom. You just upload an ASCII file with a few parameters. One is the name, then the right ascension and declination, a position in the sky, and just a comment. And at that point, you can click and you get the SED image and so on. There are other ways. If you don't know exactly the position, like in the gamma rays, for instance, but also even more so in neutrinos, where the uncertainty in the position is much larger. So you have to specify not only the name and the position of the best position, but also you have to specify how big the field of view where you're looking should be, and then the major, minor parameter of an ellipse, of an elliptical error region, and the rotation angle, and of course the comment. If you do that, then the system can do something for you as well. And this particular something is called looking into trying to get the counterpart. As we saw before, the error region in this case is this ellipse here. There are many optical sources in there. There's one X-ray source here in the blue, and there's one little source of radio in the red or so. And we have one tool that we call ERCI. That's the error region counterpart identifier. What it does is it goes off and gets about data from about 50 catalogs, and then it calculates some kind of structure SED. And it looks at all the gradients. It looks at the slope between the optical and X-ray, the infrared and X-ray, the radio X-ray, W1 and W2 in the X-rays, and many other things, slope in the gamma and so on. Takes into account of all of this information. If the source is extended, if there is a host galaxy, all that lot of information is then tried to put together by this algorithm, and then it tells you, hey, for me, you have a possible candidate here. And if you have more than one, there is a table, and you can click on each object of the table. And then you can do, again, as before, you can look at the SED and so on. And it also gives you the position of the peak, the intensity of the peak. It actually, there is a tool, a machine learning tool, that tells you if the SED looks like that of a blazar, of a QSO, of an X-ray binary, or a certain number of possible categories that we train the system on. Okay, this is an example of it's an easy example. There is this kind of orange small arrow circle and a smaller blue, and the red one as radio. The orange one is Euro Zeta. This is cluster of galaxies, as you can see. for E rosita, the error circle is very small, so it's easy. Sometimes it's not so easy, but in this case, it's particularly easy. So this is just to say that you can have very large error circle, but also can be small, and then the system tells you, in this case, it says the X-ray extended. Okay, this is the example, the other example, the opposite example. The whitish ellipse, there's one here, another one much bigger, from the IceCube list of tracks that have been published. In this case, the error region is very large, as you can see, so it will be very difficult to find a possible counterpart, also because we don't know really what are the counterparts of high energy neutrinos. Nevertheless, the system plots you on a image, and it gives you the position of interesting sources there, just in case something is maybe flaring or so. In this case, maybe we could coordinate with astrocolibri to see which one of those sources may be flaring at that point, and bingo. But so far, no bingo yet. Okay, so this is another thing that nobody has. And this is something we realized a few, maybe a year and a half ago, by calibrating on the table, on the list of blazar detected in very high energies in the TEVCAT, and taking into account of the upper limits published by the Veritas people, we sort of calibrated the system. So we also derived an algorithm that which appears here. So you have your SED, you have the peak and so on. Then you can click here, VHA detectability. It asks you for the redshift, of course, as we heard before. At a very high energy, photons have sometimes a hard time to go through the universe because they hit other photons that disappear. So there is a absorption. So the capability of being observed, the possibility of being observed by a certain object depends on the distance the photons have to travel through the universe. So redshift is one parameter. There are some other hidden parameters we take into account. And then according to our calibration, that gives you the probability that this source can be detected by the current imaging atmospheric Cherenkov telescopes, 26%. This is an object that comes from the TEVCAT. So it was in fact observed. So 26%, it means that maybe one time it was observed, it was detected. And then the probability for that it could be detected in a kind of a extragalactic survey from CTAO, 71%, and the probability of detection with a deep CTAO exposure is essentially 100%. I don't dare writing 100%, so I say more than 95%. So this is a kind of a tool that's useful for people working in the very high energy to see if a source can be detected if you trust my algorithm. But we'll see. Okay, so we've been using this tool that I more or less described to do some science. And there are two ongoing firmamental projects. One of them has been basically finished. We submitted a paper. It's a reanalysis of the Fermi 4FGL DR4 catalogs. And then the other one is the Blazar ERAS survey of X-ray sources. So what we did, we ran the ELSI tool, that's the tool that looks into the error ellipses to see if there is a plausible counterpart. We run those that on all the 5660 Fermi 4HGL DR4 gamma ray sources with above the galactic plane. We want to avoid the galactic plane where it's a bit of a mess. And on 1500 ERAS radio matching X-ray sources in the ERAS. Okay, so the output was loaded on Firmamento, and a number of people have been clicking and looking, including a number of students, some of them with zero previous knowledge of astrophysics. They never been training. Others have been working with us a little bit. So the idea is to have something that can be done not only by scientists, but also by people who have no training, but they can anyway contribute to do some science. Okay, so this is what we did. This is the easiest case. So we have a nice ellipse, a lot of optical sources. The yellow thing is the yellow circle is the position of the source as proposed by the Fermi team. And our system tells the source number 1, which coincides with the same. So we agree. If you look at the SED, it's something like that, which is reasonable. The peak is at 14.4, and the intensity at peak is minus 12.1, somewhere here. It takes the average value. So this is the easiest case, which happens in more than 85% of the cases. So in more than 85% of the cases, our tool agrees with what the Fermi team said. What about the other 15%? There are things like this. This is the arrow circles, a lot of optical candidates. We have one candidate. The Fermi team didn't find anything. This is the SED. We believe the SED is very consistent with that of a blazer. So we think this is a plausible counterpart. So we started counting these things. And how many did we find? 415 of new cases. So if you take into account that the Fermi catalog, the 4FGL and the 4LAC DR3, there are about 1,200 unidentified, still unidentified gamma ray sources out of 7,000 altogether. So we managed to identify 1/3 of them, which is quite a result. Take into account that many of these identifications were done by students as well. Okay, so other cases. There are cases where the team proposes this source here. If you look at the SED in the radio, it's very flat, but then it goes off a bit, like in a gigahertz peak source. There is no data in the optical and the infrared, it's too faint, and the gamma ray is fairly flat. We found an alternative blazer here with an SED, which is very nicely matches the gamma ray, because the peak is here, and when the peak is around 16 or so, you should expect fairly flat gamma ray spectrum, which is exactly what it is. The relative intensity is fine, so we believe our counterpart is a better counterpart than the one that was there before. How many of these things that happen? I'm fighting with the system, sorry. 62 cases. So 415 plus 62 cases, we sort of adding information to what was already published. Okay, so then we go through the BRERAS survey. Okay, so this is done by myself together with some friends at the Brera Observatory in Milan. All of us have very long experience in blazers, so we decided we have a beautiful survey available. Why don't we do what we've been doing from the 1990s and try to understand some of the open questions that are still open? So we've been checking 1,500 or so. We've been looking for the quality, for what kind of nature the sources are within the X-ray arrow circle. In this case, it's an HPL. That's a blazer with a peak in the high energy. This is a Cepheid galaxy. Maybe this is a cluster, a Cepheid, and so on. So we went through them. We checked very thoroughly the redshift because it's important for the luminosity function. And in the end, we start doing some science, and the easiest thing you can do in cosmology, that's what we want to do, is to build the so-called log-n log-s. So we saw how many sources are there in the sky at this flux or different fluxes. If the universe were just Euclidean, that is a flat with a population of sources that have a constant density, then you would expect this line with the slope 1.5, which is called the Euclidean slope. Of course, the universe is not flat. It shrinks as you go back, and so you should expect it to bend over. But we know, and that was a puzzle, objects of this kind, HBLs, which are almost all of them are beer lax, they tend to flatten off, and to the point that the cosmological evolution was determined as flat, as a negative. That is, as you go back in time, increase the redshift, the density of these objects decreases. There are less and less as you go far away. Either the density decreases or the luminosity decreases. Okay, so this is very nice, and it goes down to a fairly low flux. If you want to compare to what was known before, you do this, and this was the previous log n log s, and clearly you can see the improvement using a much better survey than was used in the past. So this is again quite a nice result that has been done by using Firmamento. These are the guys that have been working with us with the gamma ray data. High students at that time, now they're in the university. And they were quite good, and they helped us, and some of them are also participating in this latest version that we just submitted. On the right, well, there's also some Italian here. We're saying that this is from Zaia, which is the president of the region where they come from, and near Venice, in Veneto. They say you're very good, very good, very good. So only to say that it got to the attention of the politicians as well. And up is those people, and myself up here, Michele Doro up there, and other people. You may recognize Ulysses there. Oops. Sorry. Let's go back. And that was at a workshop. This is Ravda Al-Manzouri. She helped us a lot there in New York University. It was, as I was saying, a meeting we had in Abu Dhabi a couple of years ago. Okay, so this is more or less all. If you want to know more, there are a couple of papers. There's a Firmamento paper on the Astronomical Journal, and another one that it's basically something that I wrote as after a talk I gave in Milan. It's just the proceedings. It's in press. You can find the preprint in the archive. Okay, this is more or less all. Thank you for listening, and if you have questions, please ask.
Thank you very much, Paolo. Do we have questions for Paolo? We have time for a quick question. No? Ah, perfect.
Hello, Paolo. My name's Jamie Conway, and I'm interested with the platforms that I've been looking at, particularly how yours appears to be in development. And I think it could be a very interesting thing to include citizen science with in terms of developers, because the most attractive platform I think that I've seen so far was the last one.
Astro Colibri, yeah.
Astro Colibri, yeah, and the most effective so far was the Aladdin. I love the way that Ada, we met Ada. We met a French lady who's working with a number of different platforms, and the way she put it together was just magical. I can imagine it over several different screens. What I find most interesting is the development of Astro Colibri. I think that would be very well accepted by an easy learning community, let's say, where yours, Firmamento, seems to be moving much more into an academic realm. So my question really is how fast would you need? Let's say I got a group of 5,000 volunteers together. What percentage of those volunteers would you need developing the database to make it more like Astro Colibri, and then compacting it so that we can use it across various platforms such as our favorite French lady introduced us to the other day. What sort of peopleage do you think you would require, and what sort of time do you think we would need to achieve it in before 2030, so that we can use it as a really powerful platform? Thank you.
Yeah, thank you for the question. Firmamentus is developed basically on a best effort basis. We were not really funded. We are hosted at the university in Abu Dhabi. They have some money to pay students, and I helped us quite a lot to write this. I most is maybe utopical, but as you said, you had the impression that this is mostly aimed at a professional scientist. Well, in one day, I think, and this is the vision, anyone can be a professional scientist. Maybe not professional in the sense that he gets money, but maybe he can get excited, and at home he can do science. We know that if you provide the tools, then people can make a lot of discovery. We know very well that most of the discoveries are serendipitous. So you just happen to, you bump into something interesting, you realize it's interesting, and that's a discovery. And the efficiency in this process depends on how many people look around and find something interesting. So the more people can use it, the more interesting discoveries can be made. The next step is to go to a different, maybe not orthogonal, but a different direction to help people use this system, maybe all of them put together, and that's artificial intelligence. We are working on integrating artificial intelligence to suggest and also machine learning, automatic systems that are reliable to help people do what they would like to do, but they don't have the training to do that. So maybe AI, which is we already have some prototype, can tell you what's the theory behind, but it can also help you in going through the system, and maybe you can propose some little experiments to do, and then it can guide you. You retrieve the data, and then we have, for instance, one machine learning tool that was done by postdoc, actually PhD students in Abu Dhabi, a machine learning tool that tells you what kind of distribution, that you've retrieved it is. Is it a blazar? Is it an X-ray binary? Is it something else? So some tools to help you doing, maybe having fun one day doing real science. So that's the idea. Whether we'll be able to do something complete by 2030 depends on whether how much resources we get. We know we have a lot of friends. Well, we have some friends. We are within the Open Universe, which actually started in 2015. I was one of the original proposers. So if we get some resources, we have plenty of ideas. I think we can do a good job and go a little bit down the road to my long-term view of allowing everybody not only to get the data, but to be able to do some science. A real scientist, not a citizen scientist. Citizen scientists, at least as you define them, some people who participate to a project, but the project has been defined by real scientists. A normal scientist without training could be able to define their own science, maybe with the help of artificial intelligence. And we'll see if it works.
That's great, thank you. Just finally, how many different languages do you hope to present your platform in? Because I obviously would be presenting it in Brazil, so I would hope to do it in Portuguese, but I may need to teach people English to use the platform. Is that correct?
That's absolutely right. And One of the things we need to do is to have the platform in many different languages, and you can do that very easily with AI. You can do a translation on the fly. That's one of the things we want to do.
Okay, thank you, Paolo. I just have a very quick comment because you are doing associations of lasers with the gamma ray sources. You are doing a lot of that, and I don't know if you are familiar with a tool called Easy Fermi. That I think that you can use it in this context as well from the gamma ray part. So you can improve the uncertainty regions, for instance, to facilitate the association. And this Fermi can be used even for students that are not familiar with science. In just a matter of clicks, you can use Fermilab data, and the results are robust and can even be published with no problem. So I think that Easy Fermi is something that can go in synergies with Firmamento.
Yeah, absolutely. Thank you. I will check that for sure. Thank you.
Thank you, Paolo. Now we are moving to the next presentation. It's Leandro, which will give us a hands-on section on Firmamento. Thank you very much, Paolo. Okay, if you have your laptops, you can follow the presentation with your laptops.
Hello, everyone. I'm Leandro. I'm a postdoc at NYU Abu Dhabi, and I recently started working with the Firmamento group. And so for what regards today, I will show you what you can actually do with this tool. Well, Paolo already introduced a lot of use cases and possibilities of things you can do. But if we go more practical, let's say, the actual use case that's very has been used for, and you already see that, is for blazars. Why that? Because blazars are these, as Ranieri showed you earlier, they are a very particular object, and they are not easily seen from everywhere, right? So, and so you need more data, meaning you want to check out all the wavelengths altogether. So for instance, if we go to known blazars here, what you can do, sorry. Okay. So let's just pick one, for instance, just to have a look. And then, when you do pick, it will select it, and then the SED here will show you the flux of the photons as a function of their energy, which is what is important in order to discriminate them. So, yeah, I'm. You can see here that we are on the website over there, right? So, for instance, okay, let's try another one. Just okay. Now we see these SCD here, and but of course if you are a citizen scientist, you of course cannot tell much about this, right? Because like what does it even mean? But we know that for blazars, if you go here, these are just a bit below. It's on top here, right? All right. Okay. So sorry. Okay. So coming back to us. So again, if you are citizen scientists, you maybe cannot really tell something about this plot, right? So this is why here there is this plot that this, of course it's not real data. This is just to have an idea for you on how the data is supposed to behave in case you have a blazar, right? And then you go here and you can say, okay, more or less is similar, right? If you compare it, for instance, to the red curve, say, okay. Of course, I choose specifically an actual blazar. So, I mean, this is very easy to identify. If you, when you will be doing by yourself, we will have way harder cases. So, and then you can help. For instance, let's say we want to try if these can be HBL. I don't know. And these can help you to check if this is more or less behavior. Sorry, redshift. I should like. Yes. So for one sec. Okay. So you can 1 second and be coming back. So and you can see that more or less it fits, right? Because in fact, this the blazar, which is on the red curve, which is HBL type. So I mean, this can tell you that you can see quite clearly that it's a blazar, right? And yeah, sorry, you were asking about you, uh, Jamie, right? So, well, yeah, in principle, sorry, No, sorry. You said something about the redshift, right? Yeah. Yeah. I agree. But for these, also, yeah. The thing is, like depending on the redshift, this curve will change because the redshift will change the wavelength of the photon that comes from the object, in this case a blazar, right? So this will change how the curve will behave. But for okay, if it's like if you want to understand better what a redshift is, then okay, you can learn about it and everything. But anyway, it's reported. Usually, it's reported here, or there is an instrument for in here to get the redshift measurement, because these measurements are obtained in other ways, and so let's say for this case is mostly just a number, let's say, that tells you more or less what the distance is, right? So okay, okay. So okay, this was sorry. If you, for instance, in this case, you can use the get redshift button here, and you get that from the 5BZ catalog is 0. So you can use this number for the plotting that you see there. So now, if we want to, okay, let's move to another type of blazars, which are known, and they were discovered with the Firmamento by the students of Venice. So now, if we want to pick one of these, for instance, what will happen? Just to keep you posted, so I'm using these blazars that were discovered with Firmamento only because to make a point about how you can use it, and how you can be how it's important to use such a tool, let's say. So again, now if again, let's start with redshift this time. It will take a bit of time because it has to go into all the catalogs and check what's happening, and they give us 0.32. So now we can have a look here. Oh, sorry. So if we look at if we look at, for instance, at these green and red lines, what you would say that is the one that, I mean, is the one that fit most? The green one, the red one, or none? What do you say? Red one. Okay. So let's start with this HBL template, right? We know redshift from the other the number that that we got before, 0.32. Let's start with the scale factor of 0.1. I don't know. Anyway, this scale factor will change the value on the on the spectrum, right? So should be just a scale factor. Well, I'm not sure actually. Maybe Paolo can.
Yes, it is a scale factor between the real spectrum of Markarian 501 and this one. Markarian 501 is very bright, so the scale factor has to be small. It looks like it's got stuck here. Just to clarify what happened before, you said the redshift was 0. That doesn't mean that the redshift is really 0. It means that the optical spectrum of the source is completely featureless, as it happens in blazars, in some blazars in BLX. So it only means that we don't know, because the optical spectrum is completely dominated by non-thermal radiation.
Okay.
Okay, maybe you can go back and then try to, instead of Markarian 501, use the giant elliptical galaxy template. But I don't know why it got stuck.
Let's try to refresh it.
Okay. Click on the giant elliptical galaxy there. The second one and the second.
Sorry?
Giant elliptical. Yeah, that one. And then say ratio 0.32. Okay, try again. Hopefully it will come back.
Yeah.
It doesn't look it's working. I think it's the data has been.
This is this is to have you to show on the plot like what type of blazer would look like on the.
Okay. I think the data on the cloud has been corrupted. If you go force run, maybe if you go force run and get sated, then you regenerate it.
Yeah, maybe it's better.
So you can show them what happens here. The system goes around and it checks many catalogs.
Yeah, so yeah, when you generates catalog, of course, sorry, when it generates the image, it takes some time, of course, because it has to go all the way and check online in every other catalog and see. So it's takes a bit of time, but yeah, there's
Data coming from 100 different catalogs around the world.
well, no, because the search in the catalogs is made from the server, which is NYU AD. So that's depend on the connection that there is at NYU Abu Dhabi, not on the one of your computer. Yeah, that connects to the other. It's not okay. Okay.
Yeah, click on something else and then on giant elliptical.
No, I didn't understand.
Yeah. 0.32.
Sorry?
The redshift, it was 0.32, right?
Yeah.
Maybe you can also show, if you click on ASCII or a CSV down, you can show the data.
Yeah. Sorry, what's your question again?
Okay, now you see the expected emission from a host galaxy at a ratio of 0.32, which matches perfectly the data.
Okay.
One would be too much. One would be, you're just overplotting the, that's okay. Markov 501, which would be, okay, so you have to go down by a factor of 100 or so, 0.01, something like that. So those lines represent the flux emitted by the famous galaxy Markarian 501.
Sorry, Paolo, just a second. The scale factor, it seems, is almost, you can think of it like a zoom, where we're trying to overlay the
Yes.
data.
Okay, so you see here, it's really good. Yes,
There, isn't it?
So Jamie, it's more like how high is how this orange line will be plotted on top of
yeah,
the.
well, if you, just to clarify this, if you go up and then go up and then you type Markarian 501, go up. And okay, and then you click a user input on top. And then type Markarian 501, MRK 501, MRK 501,
5.1.
501, 501.
So it uses
I don't know.
Alicia apparently. Okay.
Try again, data access, MRK 501. It's a famous, very famous object. Wait a few seconds. No, it's not working.
So this morning there were some technical problem with the servers at NYUAD. I thought they were fixed, but probably they are not. So
Okay, now.
yeah, I confirm probably. Okay, so maybe we'll. I will check the situation with the server, but I think for this hands-on, we should stop. And then, sorry, Deep. Oh yeah, of course, yeah. So on the moment we can only access the UI. So what we can see, we can see from the UI are these sorry, this list of blazars that you have here, which has of course, these are the non-blazars which are taken from catalogs of blazars. Sorry, the blazars from the catalogs. Then there are some blazars that we are not 100% sure they are, but they could be, and then they end up in blazar candidates. These are the blazars that were discovered with the Firmamento, with the students from Venice. And here you can see some of the catalogs. So you want to, for instance, access to some particular catalog, which could be, for instance, I don't know, Lazo, which is an instrument in Tibet.
Use Fermi for HVL, that's better. Fermi, said that one, yeah.
Yeah, and we can take any source. And for instance, we want to check some optical survey.
Daisy is the best. You can zoom up.
So, and you can check, like, for instance, the sources in the catalogs, like where they are, and you can go around and explore, even if you want to. And yeah, these are more catalogs you can go on. For instance, the Messier or and, all of the one that are listed here. You can select any of them and then choose any source again. Yeah.
So what type of source in this platform? Just blazars, IGN, and unknown source, or there are other types?
You mean here? So
Yeah, Platform.
maybe Paolo can confirm this, but
Yeah.
we all
Well, any multi-wavelength source can be used here. This is the full FGL catalog, which has mostly Blazar, but also supernova remnant pulsars and other types of sources. Now the server has gone down. If you go to other catalogs, it should be okay. Other catalogs on top or to the right. As you and you go M51, for instance, you can show.
On the platform, is there anywhere that I can show people where there are tutorials? Maybe
sorry.
tutorial layout, maybe?
Yeah, well,
Um,
we have generated tutorials in YouTube. It's not ready yet, but they will appear very
Okay,
soon.
Yeah.
that would be a good thing to be able to
Yeah,
direct,
yeah,
so they don't leave your website, if you know what I mean. What we have to do, we have to have a secondary window that opens up to keep them on Firmamento. Otherwise, they're going to move straight to another website. I tell you that right now.
yeah, yeah.
Thank you for your feedback. And okay, so sorry for again for the technical issues that we had with the server.
I checked it. So the problem is in Rome, where the name server is down at the moment.
Okay.
That happens.
Sorry, and yeah. Thank you again for following, even though we couldn't manage to do actual blazars. Let's say we cannot actually see new blazars, but you can try again and try again at your home and see, maybe you will see something.
Maybe one day.
Yes, of
Okay,
course.
now it's working actually. Mercalli 501 appears. Maybe you want to show that.
Sorry.
So if you go back, if you have 1 minute, I don't know. If you go back and you type MRK 501 there, exactly there in the window. No. User input, MRK 501, and wait a second. Okay, now you click down, and then you get set data. And you should see the Markarian 501, very bright source. And now if you click on the Markarian 501 down there, where you were doing before. No. Before with the orange lines.
Sorry. Here. Okay.
Now you do Markarian 501, just to Markarian 501. To the right. To the right.
Okay.
No, to the right. No.
No,
Markarian
I'm
501.
just Paolo now. Okay. You mean?
No,
Sorry.
I mean MKN 501 there.
I'm getting lost.
Click on
Oh, okay. Yeah.
okay, good. Now redshift 0.03 and scaling factor 1.
Okay.
Now scaling factor 1 means okay, refresh.
Now let's see.
You're just showing this. Unless the data is
Yeah, sorry,
What
we,
happened like before? Okay, it's doing it. Okay, now you see what it means, that yellow things. It's the envelope of the minimum and maximum emission from this blazer. So when you have a scaling factor of 0.1, it means that you are reproducing the shape of this emission scaled down by factor 0.1. That's the meaning of the scaling factor.
sorry. Yeah. No, 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 no. No, no, these are the,
Those lines, they just define the envelope, the minimum and maximum emission from this source, right? So since you're applying it to the same source, mechanic 501, then the scaling factor is 1. For another source, you need to have another scaling factor because most of the times will be smaller. The intensity, this is a very bright source. Okay,
yeah.
So basically the scale factor is setting the normalization and then the redshift, right?
yes, the scaling factor is just a normalization up and down, and the redshift changes a bit the scale on the left or the right. As you may notice, the label on the x-axis is frequency new in the observer frame. In the local frame, it would be scaled by 1 plus z, simply by how much the frequencies are shifted due to the expansion of the universe and by redshift.
So basically in these templates that you have here, you have the different blazars, typical blazars that you know, and then you are scaling them. Basically you have the templates at redshift 0, and then when we set the redshift to the source that we want, the flux is being redshifted at that redshift.
Yes, it's shifted by 1 plus z, which is not much. If the redshift is 1, then the shift is a factor of 2, which is on this scale, it's only a little bit, not too much. But to be precise, you have to do it, especially if you want to fit the galaxy. If you see that bump at around 10 to the 14, actually, Leandro, if you zoom up maybe the image, you can see that there is a galaxy there. Zoom up a bit. Okay, you see there is an extended emission. You click on Pan Star on the right. Yeah, on the. Okay, you can see that this is a very nice, bright, giant elliptical galaxy. This one is shown on the energy side. If you now click on giant elliptical on the left side, giant elliptical, and then you just say refresh, you will see where the shape, what you see extended on the right, how will appear on the left in the energy domain. Now we've seen, okay, it takes a few seconds because there are thousands. Okay, you can see that the reddish line matches very well that bump. That bump there corresponds exactly to the galaxy. And when you want to characterize the emission from a blazer, you have to remove the flux from the galaxy or from other source that is not related to the jets, like a blue bump, the emission from the accretion disk or so. And all of those things are in there, the blue bump, the giant elliptical, they're there for you to see if it's there or not. So to disentangle the emission due to the host galaxy or the accretion disk from the emission in the jet, which is all the rest.
So basically this is helping us to modeling the source,
Absolutely,
right?
absolutely, yes. Absolutely. Leandro, if you click on get data, maybe you can show ASCII, just ASCII there, down, down, down. No, down, sorry. Go up
Oh, sorry. Okay.
No, no.
I'm
Go
not,
to the bottom.
but
Yeah,
yeah, but I didn't understand.
go to the bottom. Okay, not too much. Okay, now ASCII. Click on ASCII.
Ah,
Okay, and these are all the data points there. Each one with a reference.
yeah. So you can even download the data and play with it for instance, using Python or
Uh,
any other programming language or software you want. This is simple CSV. These are all the data points.
Yeah, and it tells you from which catalog they're coming from. So XMM, VLA, XMM SLU survey, ROSA, WJ-CAT, 2XPS, and there's plenty of data at many different frequencies in infrared wires. You can see there's detection on the upper limits, pan-stars, HST, Guy-Star catalog, UVOT. UVOT is the ultraviolet and optical telescope on board of Swift. Okay, so there's millions and millions of data points in there.
Yeah, exactly.
And if you show the results from BLAST, this is the peak of estimated by the BLAST machine learning. It tells you that the peak is 16.4. It's the average. You can see that as it was said this morning, these objects are very variable, but not only in intensity, also in energy. You can see that the peak, when it's very low, the intensity is to the left. When the intensity is very high, the peak is too much higher. Here you get the average peak. So there are tools to characterize what you're getting. The data was retrieved for you from 100 different places, homogenized, plotting for you. You can find out what intensity, peak intensity is. You can find out if there is a contribution from the host galaxy. From the blue bump, you can compare with other laser 3C279, Arcade 501, and so on. And
Sorry.
if you click on VHA detectability,
Yes. So what
okay,
power thing is that there are also tools that actual scientists can use to do all the calculation and analysis for, I mean, for more things that are way above the citizen scientists.
yes, but as I was trying to say before, one day if somebody really gets excited about this and can learn, maybe with the help of AI, then anyone can do science here. Because all the tools are there. But we need to train people or to attract people. And in principle, you can reach anyone on the planet because internet is everywhere. So the potential is really there. And then there are also things that are very specific for scientists, like in this case, if you want to know if you're like Ulysses, you want to know if his SWIGO instrument will detect the source, then you click on there and you have an estimate of that.
Okay. So,
Sorry for my intrusion.
okay, I think our time is over at this point. So again, sorry for the issues with for the technical issues that we were having with the server. And thank you. If you have any question, please ask me.
Okay, thank you very much, Leandro. If we have only a very quick question we can do now because we are a bit late on the program. Okay, so I'm pretty sure people have a lot of doubts about Firmamento, especially because of the interactions that we had here. And of course, you have Leandro to interact until the end of this event.
Yeah, of course, I'll be here.
Thank you. Thank you very much, Leandro. Thank you very much, Paolo.
So now we're going to have a presentation about the last of the tools that we would like to introduce to you in the context of the Open Universe Initiative and in the context of this workshop. This is a very interesting tool dedicated. Now it's the science, yes, but yeah. So dedicated to the modeling of blazars, which is a kind of astrophysical source which was already introduced to you. And this is very interesting. It's very sophisticated, very rich from the physical point of view. Involves machine learning, so it's really on the front of what we can do in scientific terms with all this amount of data. So it's a bit perhaps more scientific and research oriented than previous tools, but it still is extremely useful, and I think it will be of the interest to everyone. Narek is from ICRA and Armenia. He's a long-time collaborator of CBPF. Since 10 years ago, he's been coming here. It was a long time since you didn't come. So it's good to have you, and also big collaborator of all the colleagues behind the Open Universe. And so you first do a scientific introduction and then immediately continue with the presentation of the Markarian tool. Thanks, Narek.
Okay, well, thank you very much, Ulysses, for this very nice introduction, and of course for the invitation, because it's always a pleasure to come back to CBPF and to come back to Rio. So as Ulysses mentions, my presentation is two parts. So the first, I will continue the journey that we started this morning about blazars, because this morning we presented the structure, different components, but I'll try to go more deep in details to see how this emission comes. Of course, I'll try to use some simple definition, etc., to attract more people. And after this talk, there will be the demonstration how these theoretical things that I'm describing is implemented online in our tool, so everyone can use it. So the first presentation is called Exploring Blazars in the Data-Rich Era. So this is the... Yeah, but there is some... What is this? I mean, in my laptop is different slide, there is that. So I'm sharing my desktop, so you see data is not changing, it's stable. So maybe the guy can help us. Okay, now it works. Not showing my screen, I don't know why. No. I have the cable. I have the cable, Ulysses. If you want, you can connect the projector to my computer. I mean, what to try? Here is different, here is different. So you see, that is the first page is not moving. Here is moving. You see. Should we connect with the adapter? Share. Let me put everything. Oh, yes. Maybe I was my mistake. So yes. So this is sorry for these technical issues, but sometimes it happens. So this is the structure of my presentation. So I will start with what are blazars. Of course, this morning we had a very nice introduction, so for historical parts, etc. But I will try to convert to speak about something else. I will explain why blazars are interesting, some multi-wavelength observation of blazars, multi-messenger observations, what could be this origin, some unresolved issues, and how we can find a solution within neural networks. And of course, I will make some conclusion. And on this right side here, you can see this beautiful image, which is generated by artificial intelligence, which showing the blazar, which is all with beauty. Of course, this is a fake picture, but still it's beautiful to see this, what the AI can now. So I will start from this definition of jetted and non-jetted AGNs. So on the top here, you see this beautiful image of the galaxy, which is practically does not have a jet. So this morning was explained that the jet is that something you have some structure that is going out from the central nuclear part of the galaxy. So in this below this picture, you see the galaxy, which is jetted galaxy. So there is this structure that is going out from here and extends in the space. Sometimes it could be very collimated up to kiloparsec, and even some very distant one. There are some studies that go to megaparsec scales. So from the beauty point of view, I mean, I agree that this image is much more beautiful. You can even have a poster in your room because it's very beautiful. But let's say from the emission point of view, why we are more interested in blazars, why we care about more blazars. Because if you plot the flux, let's say, or depending on the frequency, and you see that the black line, which is shown here, is the most emission that we observe from this non-jetted AGL. So mostly this is a thermal origin emission. It's very narrow. You see the black line over here. But if you look the jetted AGNs, like subclass, which are blazars, for example, you see that this emission is very broad. So it goes from radio to high and very high energy gamma ray bands. So from theoretical point of view, of course, it's more interesting when you study these objects that you have more data than the objects that have very small observational data. So if you look, this has been mentioned so this morning, but if you look, blazars, very common definition of blazars in any textbook, that these are the quasars which have relativistic jet that is pointing into the observers or is making very close direction to the observer line of sight. So this is the classical definition. So in reality, so blazar that we see something very point-like, you see that there is kind of emission here, while, I mean, if it is not to direction of the observer, you see this double lobe structure, let's say, originating from the center. So if you compare, if you take all the catalogs were presented during this week as well, no? If you take all the catalogs, all the possible blazar-like sources, you can reach the number like 6,000, which is, if you compare with the number of the total galaxies that we know that is between 100 and 200 billions, this is very, very small fraction. I mean, so then the question is why this small number of the sources are so interesting that there are entire communities and observations trying to understand these sources. So here I list some of the reasons that why I think that blazars are interesting, but of course you can continue this list as much as you want because there are so many things to say about blazars. So the first thing that for me is very interesting is that they are the most powerful non-explosive sources in the universe. So it means that their biometric luminosity could be more than even 10 to 49. There is some message on the Zoom. I cannot read because it's in Portuguese. So the biometric luminosity can be up to 49. So this emission that originates from this relativistic jet is Doppler amplified. So in the observer frame, you see more enhanced emission. It means that you can detect these sources at even very high redshift. So these jets are produced from supermassive black holes. So supermassive, I mean 10 to 8, 10 to 9 mass, solar mass, etc. So kind of, if you study these objects, you have indirect investigation of these supermassive black holes. The emission of this object is changing in time, is variable. As I mentioned, the emission goes from radio to very high energy gamma ray bands. So in all the electromagnetic window, there is in some band like optical, radio, and very recently, so in X-ray band, you see this polarization, but this emission is polarized. And of course, one of the interesting points is so that these sources are kind of associated with neutrinos. So these are interesting for messenger observations. So one of the most interesting feature of this object is the variability. So their emission is changing over time. There is a very nice presentation of what means the variability from this reference over here that you can see. So this is the sky position of blazar. So each dot here is a blazar. So this is the sun that is moving over time, and each dot is a blazar. So what means the variability? Look, the sizes of the dots, they change over time. So sometimes you see that this is extremely bright, sometimes it disappear, etc. So this is the nature of blazar. Sometimes you can observe them, they are really crazy flaring, very bright, etc. But in some periods, they just disappear. So the sources are not in the sky anymore appear. Right? So this is in the gamma ray band, but what is true that this variability is not only in the gamma ray band, but also in all the electromagnetic spectrum. So here on the left side is the light curves in different bands changing over time. Here is the spectrum. So you see that in almost all bands, you have the changes of the emission spectrum, and this is changing in time. So it means that if you observe some blazar in one period, maybe in next period, if you observe, you see completely different behavior. So this makes them kind of interesting more because it's not a steady object that you just study once and you have a clear picture. So they are always changing in time. And of course, this changes also affects the way that they appear in the sky. So this is a case which we study with Paolo Giomi, and this is why we call it the strange case of this object. So this is a very strange object, and so if you look in all the sky surveys in the past, even in the RAS surveys in 1990s, there was no observation of the source. So this source didn't exist at all. So no one knew that there is this kind of object. So I mean, from 2016, starting from 2017, the source was started to be bright in the gamma ray band, then in the X-ray band also. So you see that it was a very active emission state in the gamma ray X-ray band, then again goes down and disappears again, the source. So this is why we introduced this term calling like transient blazars with Paolo Giomi. So maybe there are some population of the blazars that still are not, we cannot see them because of this type of the things, because sometimes they are bright and we don't see, but this brightening was so strong that if you compare the X-ray emission of this object, which is in gray, with one of the brightest X-ray source in the sky, which is Markarian 541, shown with the yellow here, you see that the amplitude of the variability is no comparison with Markarian. So this was really one of the brightest X-ray sources in the sky in that time. So this is more evident if you look at this animation, which shows the emission of this source before it was active and during the activity. So you see the time is changing. You see that there is some emission, very bright emission. It's really strongly emitting in different wavelengths, these kind of very bright objects in the gamma ray, X-ray, optical, in all the bands. So this is when the activity happens. Then it drops and the source again disappears. So this is a very transient nature. So with Paolo, we believe that there are a number of these kind of sources that sometimes they appear, but we don't have these all sky surveys. So this is why we don't observe them very frequently. But very likely the number of the blazars that we are considering could be much more because of this transient nature of these sources. Yes, but with Paolo had some ways to check in the infrared band to find. He has some examples that we need to really check, but we didn't have time to check. But maybe we will have some more examples of this type of. For these sources, yes, it was the. Right now, I don't know because recently I didn't follow these things, but it disappeared. So it gamma ray emission disappeared. So maybe we are sure with Paolo that there will be more examples of these kind of sources. We should work on that direction to propose more candidates of this type, but this is highly possible that you would have some population of the blazars that we don't see because they are not permanently very bright, and just by chance, if you have some X-ray, I mean, you have some all sky monitoring, you can find them. You know? So this is also another plot that I took from, I mean, this diagram I took from Paolo. So this is an astrophysical messenger. So right now, how we get the information from the astrophysical sources is using these four messengers. So gravitational waves, photons, cosmic rays, and neutrinos. If you put them in one single frequency window, this is very interesting because you go from 10 to minus 16 hertz up to 10 to 30, so 50 orders of magnitude of window. Of course, we don't have an object that has been observed in all of these bands, but imagine in the future how interesting it will be if you will have a single object with this amount of data ranging from very small frequencies to the high frequencies. So in this diagram, one of the most common messengers, which are photons. So photons is the light. The light that we are seeing is made of the photons of different energies. So in these messengers, if you look the most common one, which are the photons, and if you put the spectrum of the blazars that you are observing, it goes from radio to high and very energy gamma ray band. So very, very, very wide range of frequencies here. And this is you saw even this morning from Firmamento, etc., that this is the very typical spectrum of these sources. So you have this rich data. So one peak is at low energies, another peak is in the high energy. So you have this double peak structure, and this is very common properties of these sources. So the question is, from theoretical point of view, what is the origin of this double peak structure? So what is producing this emission? Because ultimately your goal is to understand not the data. I mean, you observe the data to do the physics. So you want to understand the physical, what it means that you have this data, what it gives to you. So let's move to from the theoretical point of view, what this means. So this is a sketch showing the black hole, the accretion disk, this is the torus, this is the broadline region, and this is the jets. So according to the theories, there are two main theories. The main is divided by the particles that they are starting the emission, okay? So the theory leptons, it means that the emission comes from the electrons. So according to this theory, you have this compact region inside the jet. Why compact? Because we see the variability. So if you see that it's changing over the time, the emission region cannot be larger than this variability that you see. So in this compact region, you have some acceleration of or injection of the electrons, very energetic electrons, and you are producing these double picket structures. So in this case, you have these electrons that are injected here, and the first peak over here that you observe is to the synchrotron radiation of the electron. So in the magnetic field, these electrons are circulating, producing the radiation, and this is called a synchrotron radiation. So this first peak is due to the synchrotron radiation. The second peak comes from the interaction of the same electrons with the photons. So this is called inverse Compton scattering. So you are producing the second bulk. So this is the general theory how you are observing these emissions. So of course, this is a very simplified picture that I showed you. This describes the general situation, but of course, there are more complicated cases. So for example, for the same source, you can observe two different states which the data are completely different. So the red is extreme state, this is the quiet state, and you see that the emission is totally different. So it means that maybe two different components of the jet are contributing, or there is even more complicated things that we don't know, or even if you look, depending on the location of your emission region, different external photons from the torus or from broadline region can upscatter inside your jet, and they can produce this very energy emission. So these are very complicated scenarios when you have a one zone, double zone, or etc., or depending on the location, which component is dominating. So even for the same source, is if you observe, if you look historical data of your object. So this is one object called BLAC, and if you look, this is the photon index in the X-ray band during one flaring period. This is during another flaring period. So you clearly see that there is different tendency. So in this case, when the source goes bright, so it is very bright in the X-ray band, the photon index becomes harder. So it means that more energetic photons are present. But in the contrary, there is a flaring period for the same source, but another time when the tendency is different. So you go bright, but your photon index is different. From the physical point of view, there is a lot of meaning here because this is a traditional behavior. You have the first component, then you have the second component that is explaining here. But during this very strange flaring activity, you have another component that is contributing. So my idea to show that even if we say that we know the model, we know how it comes, the things could be very complicated. So it is not very simple. You need to have a very different approaches, a different way to explain your data. Even for a single source, the same mechanism sometimes can be good. In other parts, times it couldn't work. So these are very complex objects to study. So if we come back to this astronomical messengers window, so we see that there is this neutrino window. So very recently, from 2017, 2018, this window also is opened for the blazar observation. So if you put here, so along this data that we have here, we can get information also from this window that is coming from the neutrino observation. So again, the question is how you observe this neutrino, how you produce. Because if you go the traditional leptonic scenario that I described before with electrons, you never produce very high energy neutrinos. So you need to have a protons that are accelerated inside your jet. So again, what is happening, you have this compact region, is now instead of having single electron injection, you have both electron and protons that are injected in your emission region. And these particles are interacting, producing your data that you are observing here. So again, the first peak comes from the synchrotron radiation of the electrons, while the high energy peak here is due to the proton emission. And the processes here are much more complicated than were with the electrons. So just to demonstrate how it works here, you have the jet of blazar, whereas the protons are accelerating. Then you have some low energy photons, which is interacting with your protons. You produce these neutral and charged pions, which themselves, they interact, they produce, they decay, they produce the photons, which are not going out from the emission region. Then themselves, they interact, they produce electron-positron pairs and so on. So, and neutrinos are coming from this channel of charged pions. So this scenario is much, much more complicated than with one electron. So this is why in the community, a lot of people, they don't like these hadronic scenarios because this is very complicated, is truly very non-linear, so you cannot really understand. I mean, from the leptonics things, you can see that there is an increase of the flux and you can interpret how this increase happens. But for the hadronic cases, this is very complicated because we have the cascade, and to develop this kind of codes is actually very complicated because it requires a lot of calculations, etc., etc. But what is good, because now when you have your data, you have your model, and you try to constrain your model parameters, you don't have only this electromagnetic component here, but you have the information also from neutrinos. So it means that from the physical point of view, you can put more constraints on your parameters. So this is better for your modeling because you can understand better which kind of processes are happening in your sources. So you can change your model until you explain this electromagnetic data, plus you can have the explanation of the neutrinos, and this is why it is very important. So to demonstrate how important and how interesting it is, I just want to show one case which was super interesting for me. So these are the gamma ray sky map with these circles, that ellipses that you see here. These are the directions. I mean, there is no statistical claim here. It's just the presentation of the arrival direction of the neutrino events with the gamma ray sky map. And sometimes these neutrinos come from the direction of the blazars. So of course, the first one was this famous Texas 0506 object, which was like a boom in 2017. It was the first time there was a neutrino from this direction. So it was really a lot of groups, a lot of people were working on this source to understand what is the origin. But since then, there are several different examples when there are some neutrinos observed from the direction of the blazars. I'm not going to describe or discuss all of them, but for me, it's very interesting this particular case, which is PEGI 0755, which is the source, which is to me, one of the most interesting one. So let's demonstrate what was going on with this object. So this is in 2021, December 8th, from the neutrino instrument in South Pole iScoop, there was an alert that there is a neutrino observation with energy of 172 TeV. So from the energetic point of view, 172 TeV is not an extraordinary high, because there were even neutrinos with higher energies, okay? So what is interesting here, after this announcement by iScoop collaboration, there were other three neutrino detectors that they reported from the same direction of the sky. There are these neutrino events detected, although with different energies. So in neutrino astrophysics, we work only with one event. So this was the first case when three different instruments independently reported neutrino from the same direction of the sky, which was already a big news, because I mean, you have only one event, one instrument, suddenly you have several instruments that they're claiming the observation. So this is why with Paolo Giomi, Paolo Padovani, etc., and my colleague Damian, Sakis, and everyone, we start to look what is happening actually there. No? So this is the sky region where this neutrino was observed. And if you look very closely, On the border where this uncertainty region is, there is a source, big I 0735. So we start to look what is happening with this object. Let's see if there is anything interesting here. This is the light curve of this object in different, light curve means the flux in different times. So what was the flux in this day, next day, etc., all per observation, okay? So on top is the gamma ray flux. This is the X-ray flux. This is the optical UV flux. So if you see, there is nothing interesting here. There is nothing, I mean, it's very small flaring activities here, which is normal because we are dealing with blazars. So we know that blazars show some kind of flares or etc. But this is before the neutrinos were observed. So with the red line, we show the time when the neutrinos were observed. So you see that in all the bands that I mentioned, the source was quiet, was nothing happening. Suddenly, when the neutrinos were observed, there is this huge jump of the emission in all the bands, from gamma ray, X-ray. So if you zoom this part, you see that in X-ray band, it was so bright that you could see so the variability between different swift observations. So this was clearly something was ongoing with this object because we don't have enough, no change in past 20 years or so. Suddenly you have a neutrinos that are coming from this object, and from electromagnetic point of view, you have a like burst of emission. So definitely there was some hadronic processes going on, and this is why it led to the neutrino and this flare in the gamma ray band. So of course, with the colleagues, we study what could be the origin. We propose some models, theory, how you can explain both neutrinos and gamma rays. So up to now, I was trying to demonstrate that there are a lot of observations, there are multi-messenger observations, etc. So we still understand something about these objects. But if you put the global pictures, there are many, many unresolved issues. So here I try to list some of the important unresolved issues. These are very fundamental problems for blazar research. So even about the launching, collimation, and propagation of the jet is unknown. So it is unknown the structure, the composition of this jet, the structure of magnetic field, how this jet changes in time and energetics, what is the particle acceleration mechanism, what is the origin of the flares, I mean, imagine you need to have some physical process that produces flares that are lasting 1 week or some minutes. So the physics is totally different, etc. So these are all very fundamental questions which we still don't understand about blazars. And this is a part of a puzzle, and this puzzle is blazar. So you need to put all of these puzzles together to try to understand what is blazars in reality, what is the dominant mechanism, what is the process. So of course, in astrophysics, the only way to do that is to use the data. So you should have the data, and you should have the physical modeling. So the data is the backbone of any study that we do. So you have the data, you can test some theories, etc. But of course, equally important is the physical model. So you have the data, you observe, but you have to be able to explain this data as well. So this is where these two components, the data and the modeling, are speaking to each other. So they inform each other. So you have observing the data, you see how the data is changing in time, then you are able to explain with your model or etc. These two things are totally connected. So you have high quality data, very good models, then you can understand your objects better. So these two are very connected. So now I will not speak about data because this will be the next presentation. Where to find the data. So the question is where to find the data, which model to use. So these are two basic questions. So you need to know which data and which model. So this part, I will not speak about this. This will be the next presentation. Now I'll try to concentrate on the models. So which model to use, where to get these models. So here I'll try to give you the feeling how we use the neural networks to improve the models. No? So for this, I want to, what is the current status of the models? Okay, so there are many different codes, there are different models, there are different approaches. So how it works, you select, you have the source that you want to understand, okay? There are two models, leptonic or hadronic. So usually what you do, you select two different or different payloads of the same object, and you say, okay, this is my active state, this is my quiescent state. You try to apply these models, and you try to get some initial estimates. You try to understand you try to deduce some critical information about your physical parameters of the jet or etc. etc. But if you just make a very beautiful plot, which is this 3D plot of the data, so this is the same ACD, so the flux frequency, but here you can put it at time. So now our data is so good quality that you don't see only 1, 2 periods, but you see how this data is changing over time. So the question, if you have 1 or 2 periods and you model this, is it enough to understand these objects? And of course, the question is no, because the data is more rich and you have more information that contains in the data. And already the quality and the quantity of the data is so good that you can understand much more about these things. So we should forget about this easy 1-2 period modeling, and we can go more advanced. So more advanced, what means that you need, since these are changing variable sources, it means that you need to really do a good job to select the data. So as soon as you are able to select the simultaneous data, then as many as you can have available, so not 1, 2, but as many as you can have, then you can apply your model and to fit your data. What means the fitting is fitting, you have to statistically be able to compare your model with your data. So get to see this, from the statistical point of view, for which parameters you have the best explanation of your data. This is what is the fitting. So fitting basically is this. You have different parameters for your model. You have your data. You change these parameters so much that you try to get some explanation of your data. And from statistical point of view, you try to judge which parameters is the best is explaining your data. So this is the method, the technique to use. But there are some problems here. What is the problem is, if you want to do real good fit and you have a code that is numerical code that take into account the injection, cooling, every interaction of the particles, then for one computation, so let's say in a very simple case, which is an SEC and external Compton emission, these numerical codes are usually not so fast. So it is like 30 seconds. If you think of the time, 30 seconds is nice because you put the parameters, you push the button, 30 seconds, you get an answer, okay? But if you want to do the fit, if you want to do real fit and you want to look your all parameter space, if you do this Bayesian inference, you need to compute this 10 to 4, 10 to 5 times. So if you do an exercise, you multiply 30 seconds with 10 to 4 and 10 to 5 times, you see that you are dealing with a very long time. So the fit could take, for leptonic cases, I mean, if you do in a single computer, etc., it takes like tens of days. I'm not speaking about the hadronic models, which are more longer. So 90 seconds, it means that you can wait up to 100 days to finish one fit. So this is not the only problem. The problem, like, you can use resources to make this kind of computation, which are not reusable. So you have one source, one period, you make 100 days of simulation, then you have to throw out this data because you cannot use it for another sources. So here where the machine learning is coming into the game, and machine learning can really help us. So let me to demonstrate how with machine learning we solve this problem. So this is one example for one model. So this is the self-synchrotron Compton model where you see all the model free parameters. So there are 7 parameters that are free. So for all of these parameters, we consider very realistic physical limits. So I know from physical point of view that this Doppler boosting factor should be from 3 to 50, emission region size from this to his, and I consider a very wide range of the parameters. Then when I consider this very wide range of the parameters, I try to generate some parameter sample. So parameter sample means that you have multidimensional data sets. There are some statistical methods, how you choose some parameters that you try to cover all your parameter range. These are Latin hypercube sampling, etc., etc. So there are some statistical methods. You select some parameters samplings and you pass it to your numerical code. In our case, we use the Soprano numerical code, which was developed in my group in collaboration with Damian, which is now in Israel. So this is our code. So you selected the parameters, the parameter space that you are interested. So in this case, 2 million of parameter space. We passed this to Soprano code and we computed the output. So for each of the input parameters, we have the input parameter and corresponding ACD. So then we have the information that for these parameters, this is the corresponding radiation. For this, etc. Then what you do, you take your initial parameters, these generated spectra, you pass to the neural network. So in the neural network, in this case, input parameter is this model parameters, like 7. Output is the spectrum. So you are trying to teach your neural network to learn what means for these parameters, which is the spectrum, for this parameter, which is the spectrum. And as soon as you do this, then you can have the data, you can pass to the fitting tool and you can model your data. You don't need to run your code anymore. So the neural network is replacing your numerical code. In our case, we use the convolutional neural networks. I'm not going too much into the details. I think you can find a lot of information about convolutional neural networks. So these were good for image analysis, but then it was very useful for the time series analysis, etc. So this is the structure of the network. So this is the input parameters. There are hidden layers which are connecting together, and the output. This is the structure of the network that we use it in our case, but I don't think I need to go to details to say how many layers, etc. we have. This is something that we can discuss if you are interested. So this I want to demonstrate by this, which was made by Damian, what means learning in this case. So here, these two are the spectrum, an SCC spectrum. Here is the layers, and this is the loss function. So this is, we just did for 1% of the total database. So 1% from the 2 million. This is not the final result. This is just demonstration, because sometimes people, they have difficulty to understand what means the learning. So what means the learning here, you see this, the point is the network. So the network tries to change so much the connection, the layers, to try to find a good description of the spectrum that you have. Of course, there is some disagreement here, but remember that this is just 1% of the data set. So in 2 million of data sets, this agreement is much better. There is no disagreement or etc. So in the end, what is doing, your model is finding, after moving these epochs, is finding the description of your spectrum. And this is just showing how, for different parameters, how well your trained network explains your data. And this is the workflow. But one of the key important points here is, you remember I told you, if you run the numerical code, it takes 30 seconds. Now, when you run the neural network for the same parameter space, it takes 0.04 seconds. So like 1,000 times you are faster. So it means that you can do real, very nice fitting. And this is what we did actually. So this is a source marker 421. And you see that this is the data and this is the model. And we have very nice modeling. This is the parameters. You can see it for the posterior distribution of etc. So this is very nice because we didn't ask an initial spectrum and extra. So we just put the data and the model finds the best modeling. This is another case, which is the FSRQ, another CNN that we have developed, user to fit. This is an external Compton. You see what is interesting, that when you consider the all parameter space, there are two, this double structure here shows that there are two range of parameters which statistically give you good description of your data. So it means that it's not just you find one parameter space, this is enough. So you should be careful because maybe there are different states. So this one corresponds to the ACC case, the one is external Compton. So when you look globally, you have very, very different results. But of course, I mentioned to you that the idea is not to fit one period. So the idea is to really fit as many periods as you can. So this is the project that we are currently involved with. This is the first example that I want to show you. So this is the light curve on different bands. This is the ACD. So for this source, we selected 800 ACDs, 800, and we try to model them. So what means the modeling? It means that you see over time when you change the light curve. So when you move in the flux measurement flex, you see how the physical model is changing over time. So it means that somehow you are just transferring the observations to the physical model. And from here, you are trying to understand what, from physical point of view, what means these changes in the spectrum and the parameter, etc., etc. So you transfer the observations to the physics. So then you can understand from the physical point of view what this means. So, I mean, I'll just to demonstrate that we are able, we train the CNN also for the hadronic models. So to be honest, there is no way to fit the hadronic model because it's too long that usually people do by eye. So you were able to fit to train the CNN and to be able to fit this hadronic data. This is a one case of Texas of 5, and this is another case of this PKI 0735. So what I'm showing that this neural networks is really changing the way that we were doing things. So this is the conclusion of my first presentation. So blazars are complex, but the current data is unlocking some new insights. So these multi-wavelength and multi-messenger observations are really key. They're providing a lot of information. We should really be able to extract as maximum as we can. These traditional modeling methods are computationally very expensive. So if you keep in that direction, it will be very slow because the data is coming every minute, every day. But with the models that we want to really apply, they are slower because they require time. Instead, these deep learning method is really changing the way that we can make the modeling. And I personally believe that the future is AI-driven astronomy and multi-messenger synergy. So it is, you have the observation model and with the help of AI, and this is the answer of the question of Michele from this morning. And I think that really this AI is going to change the field completely, and we should be prepared because we should work on this direction. Well, thank you. This was the end of the first presentation.
So one of the things that's most striking in the last video that you showed is that there is clearly a very different temporal resolution on the different bands. And can you comment a little bit about how this affects the modeling or? Yes.
In the second presentation, I will show you how we separate the data. I can shortly say that we select the Bayesian block of gamma ray data because we do the analysis. We build the Lie curve, adaptive binary Lie curve. Then we do the Bayesian blocks. So Bayesian, you select the period when the gamma ray data should be constant. And for that period, we do the adaptive time binning to search to split the contemporaneous data. Of course, ideal case, I should take the Fermi sweet observation 2,000 seconds, 3,000 seconds, whatever, and use the analogous period for Fermi. But with the current sensitivity of the Fermi, this will be a little bit difficult because in short times you don't have enough statistic. But there is a way to solve that one, and it is this forward folding method. So basically, you do the Fermi analysis not by assuming some model, then getting the data, but directly implementing the physical model in the analysis. I know that there are some people that they are doing that, which is quite powerful, it's quite good. So then you don't need to care to have accumulation of the time for the Fermi. So you basically directly fit your physical model with the counts that you are observing in the gamma ray band. And that will be very, very helpful. The chairman.
Thank you. I just have a question about the synchrotron self-Compton model. Do you have on top of your head, what is the center of momentum energy squared for the self-Compton scattering? So basically in the synchrotron self-Compton, there are electrons being accelerated and then losing the energy via synchrotron, and there is a background photon field from this exactly. No, I mean the background photon is coming from the synchrotron, the same synchrotron, and then the same electrons are interacting with these photons, and then shooting them to the high energy. I want to know the center of momentum energy squared of this Compton scattering, the interaction between them. GB.
Yeah, but if you go the other type of the blazars where you move the peak at lower energies, it means that the energy of these electrons is going to lower also. So everything depends on the type of the source that you study. So this value that I provide you is the maximum acceleration energy. Okay, so maximum energy of electrons, the gamma factor of electrons, let's say. So, but so it's important the distribution of these particles, no, the index of the electrons. So I mean, you could have like very steep spectrum, but you could have also the very soft spectrum. No, this is changing a lot of things.
What I'm thinking is that if the energy, let me tell you what I'm thinking. If the energy is squared, a center of momentum energy is squared, the Mandelstam variable S in the Compton scattering is beyond 10 to the 14, let's say 100 TeV squared. S larger than 100 TeV squared. So basically,
I can tell you if you have electron in the TeV range of energy, if you have the photon background in 100 electron volts, so you are basically in this region. Then there are other interactions that are becoming dominant over the inverse Compton scattering. No,
you are in the Klein-Ishiner regime for the cross section. So in the classical Thomson regime, no, you give the square of the Lorentz factor of the electrons to the photons, and you boost the energy. But in Klein-Ishiner, the connection is non-linear and is less than the square of the energy. So that regime, Klein-Ishiner, is becoming important for us. This triple pi projection also could be, but the cross section of triple pi projection, if you compare still with the cross, okay, we cannot go to very high energies because the problem is there is the synchrotron burn-off limit. Okay, so if you increase too much the electron luminosity energy, then you cannot accelerate them because the magnetic field also is cooling. So triple, I mean, in the soprano, triple pi production is considered, but compared with other processes, it's super inefficient at these energies that we are interested. Yes, but what my point is, like, if you have the distribution of the electrons, which is a cutoff, and you have only very few electrons which have this high energy, your dominant part of the energies is at lower energies. This is why, imagine you have the cutoff, exponential cutoff. So if you are in the tail of the cutoff, so even if the triple pi production is important, then its contribution is few because the number of the electrons is less. If you have some distribution of the electrons which is shifted to the very high energies, which we don't have because of the synchrotron burn-off limit, so you cannot really accelerate electrons very efficiently to the very high energies. Yeah, in soprano is there, but it never gives the contribution because the distribution of the particles that we are looking at that energies is cutting.
When you mentioned the temporal evolution of these parameters, I have a curiosity. Is there any well-established constraints on how they can evolve through time? I mean, to judge if the fits, they make sense. For instance, if some parameter has a very high variation rate and should be rejected.
I see what you mean, but I think we should differentiate something. So the parameters that we provided here are, this is the CNN is doing the fitting. So the initial, the parameters, the ranges, we don't have unrealistic parameters, so we cannot reject them. Well, the only constraint that we can have here is from the observations. So for example, if you observe that there is a variability of your emission and you can observe the minimal time of the variability, then you can say that one of the parameters, I have 7 parameters, no? You can say that the emission region size is fixed. So this way you can reduce the number of the free parameters and you can try to do better fitting. But the point is, like, if you do the fit, there are sometimes you could have some. Here with soprano, it doesn't happen because we are taking into account the cooling. But if you have other tools where you are assuming some distribution of the electrons, like a function, then you can arrive like break that the power law index is changing from 2 to 5. These kind of things you can really reject. But here we don't have these kind of things, but because we do everything based on the physical. So you have the injection, then you see how it is evolving in time. We don't get this kind of unrealistic distribution of the particles because we are considering the cooling or etc. Everything is taken into account, the physics, I mean. So maybe we can move to the second presentation, but can I just 1 minute of my computer and then I continue, okay? Sorry, I forgot about the microphone. So if I put these two together, so one is MMDC, another one is Firmamento. So these are not two competing to each other data centers, but these are two different data centers, but they have the same goal. So the first one is to build the multi-wavelength SEDs plus to make a modeling. And the second one is to build the multi-wavelength SEDs and discover new blazars. So these are just collaborating together, these two data centers, and with the main aim to find so there are two different data centers, but there is one mission is to study blazars. Okay, so these are not against each other. Let me put it in this way. So if you remember this slide that I presented, it was like I was speaking about the modeling. So I was speaking which model you should use or etc. But now I would like to speak more about the data and which data we provide and where you can find the good quality data. So this is the let's say the structure of our multi-wavelength data center. So this is the back end, this is the front end, so this is what you see. So this is the user. So there are two main functionalities. This is what is happening in the back. So this is the main structure. So there are two main functionalities. So the first functionality is to retrieve the multi-wavelength data. And the second functionality is to model this data. And now I will explain each of them and try to show you how you can use this data center. So MMDC is, first of all, the name is called Markarian Multi-Wavelength Data Center. Why Markarian? Because one of two most famous blazars that I think, in my opinion, contributed a lot in understanding of the blazars by theoretical modeling or from the data point of view, were Markarian 501 and Markarian 421, because historically they were very crucial for static blazars. And the guy Benjamin Markarian, who discovered these galaxies, was in Armenia in Vilyakan Observatory. And this is why we thought that it could be good to highlight the contribution of this guy. So the name is Markarian Multi-Wavelength Data Center. So here there are some basic information of which kind of data you have, which why and how you can use this data, or etc. So just to demonstrate how the core functionality of the data center is, if you look for any blazar, so these are the spectrum of two different type of blazar. So as soon as you type the name of the blazar, so there is some search engine which is view blazar, which is the same like in Firmamento. So it goes to the all archival files and try to retrieve the data that is available. So all historical files that exist for your source, it is retrieved. But on top of these things, there are this number of different observations, which are these bands, optical, infrared, X-ray and gamma ray band that we provide to the community. So to just give you the feeling, we have analyzed all the Swift data that have been observed for blazars, all the new star data from observation of the blazars, and very different, more detailed gamma ray data analysis, and everything is available from Arcadian data center. So not only historical data we provide, but we provide very new data that is daily analyzed in our data center in Yerevan, and this is very accessible, so easily someone can get it. So just give you the feeling what you have. So the blue one is the historical archival data that you see here. I mean, this is also in the blue, but I mean the open circles here, which is not very visible. So all of this data is the one that you can get from the most of the data centers. The color data that we show is the additional data that you can get from the observation from the Marker and multi-wavelength data center. So this is really completely more quality, more data for all the bands from optical, X-ray, and gamma ray bands. So just to demonstrate in the gamma ray band how much data we provide and how we generate this data, and this is the kind of the answer of the question of the Ulysses. So if you use any traditional data center and you try to access any data, you can retrieve the gamma ray data, which is the time average data. So in the 10-year of Fermi catalog, you get the data which is averaged in 10 years. In 12 years is when it is averaged 12 years, and so on. So this is a light curve of blazar in the gamma ray band, and you see that over time is changing, extremely changing. So there is a very active bright state. This is in logarithmic states. You see the 3 order of magnitude on change. So if you get this time average data, it means that you are drawing some line over here and you are trying to get this data, which from the modeling point of view of blazars is meaningless, because if the source has very strong variability, very strong changes on the flux, or etc. If you average, you don't get any information. So for example, Ulysses looked here. This is the time average data that we have from the gamma ray observation. And with the color now, I show you which data you provide in MDC. So each color provides different time. So you see that we have a very nice time resolve the data. So basically how we do that, we generate this light curve. We split in Bayesian intervals, and for each interval, we perform detailed spectral analysis of Fermi. So it means that these data are not extrapolation or anything else, just real analysis that gives you this answer. So basically, you have for all the periods that is you see in red here, for all of these periods, I mean, whoever does the Fermi analysis knows that this is an extremely heavy and extremely long process, because for each period you do likelihood analysis for 5 or 7 energy intervals. So this is huge amount of work that is done automatically in our servers every day to increase this number of the data, which is so good because it provides new data for the users. So this is the main, okay, so on the page where you want to retrieve the data, so this is the main page. Now I will show you in real time as well how it works. So this is where you come to search for the data. Here there are some list of blazars. So this is the list of blazars that we know up to now. Instead here, this is the list of the gamma ray blazars. So you can either select blazar from this list, or this list, or you can type the name of the blazar here. It will automatically fill in and you can find. So what was the vision behind this? I didn't want to make something which would be very static, but I wanted to create something that people can play with it, so people can use it. So there are a number of different panels here that you can filter. For example, you don't want to have all the data, you want to change the time of the period of the data, you can just put different filters, it appears. You don't want to have these units, you can change the units. This is interactive. Now I'll show you everything, but this is interactive. You can zoom in, zoom out, or whatever. So you can play with this thing. And if you don't like to have X-ray data, you can exclude X-ray data and so on. So this is fully interactive and allows you to play with the data. So you can really zoom to see what is happening with data, or etc. So now I just go to in my laptop. Whoever wants to follow can follow with me, but I show how you can retrieve this data and what you do with this data. there is an information for what is this data center about, some facts about blazars, how it works, and of course there is this nice image movie that you see how the data is changing over time. So this is the first page. So this data access panel is the main place where if you want, you can search for the data. So as I mentioned that there are two lists. So the first one is, I don't know why my laptop, okay. This is the list of known blazars. So if you open, you see different blazars that up to now we know, the number of 6,000. So there is this list of bright blazars, which are the blazars which are sorted by their brightness in the gamma ray band. Because if it is bright in the gamma ray band, it means that we have more data in the gamma ray. So very likely there is more X-ray observation. So if you want to have something, sources which have a very rich data set, it's better to use this list of bright gamma ray sources. So just to demonstrate, so I can open this part and anything that I'm interested. So if I click this source, it automatically appears here. So I can just make a plot, and now all the data, what I explained, so it looks all the catalog data that exists, plus all the data that we have analyzed it, and it appears for the user. So this image that you see here is not static. So it is, you can, if you like to see this part of the spectrum, so if you want to see, you can just zoom. I don't see that again, there is not, okay. Process again, there is difference between the laptop and the synchronization. I don't know. So you okay, you see some delays because of internet. So if you want, you can just zoom this part and you can see only this part of the spectrum if you are interested. So otherwise, if you can go back. So there is this energy band which is provided here. So everything has, so you can open, and there are the names of the instruments which data is retrieved. So let's say you are not interested to have NeoWise data, you can just simply take out the NeoWise data from here, you can take out WISE data, and they will disappearing from the protozoa. So you can really add, remove different data sets so that you can play with this data thing. So you get something. If you like to use all of them, you can download all of them. No, you can put also some time filter. No, so there is this time filtering options here. You can just, either you can use the MHD data. So just give you an example. So this is randomly, I select random MHDs from this slide bar. So okay, so if I select some random MHDs, what will happen? So from the entire data sets, it will filter out all the data that are out of from my time range. So it allows you to play with your data. So if you are interested to have a specific day, specific data, you can easily filter it out and you can get whatever you want. And of course, this all data is on the top. Yeah, there is a download the CSV, so you can download all of the data in your laptop, and you can, with the full reference of the part of the data which were taken or etc., and you can use it for your study. So you can plot, you can filter yourself the data or etc. But this is not the only thing that is available for this source. So as soon as you search the object, there is this nice animation also. So it shows how in time your data is changing. So you can also not only see the data that is appearing, but also you can look how in time everything is changing. You see that in sometimes you have observation in different beds. And gray, you see the historical data, everything. So you can see the amplitude of the variability. You can see how the things are changing in time. You can see sometimes there are observation in X-ray bands, sometimes there are not. So this is, I mean, in time you see how the components of your source is changing, so which is good. There is this panel which was shown also by Paolo Giomia Aladdin, so you can look in the sky where is the location of your source, etc. You can play with this thing. And there is also this panel called related articles. So in article database, it makes the search and brings back to all the articles about your object. So you come to this database. If you are interested to do something, you get the data. You can play with this data, or you can also look the articles that have been published about, not by our group, but generally all the articles that has been published by this about this paper. So this is automatically search done in the database. It brings you back the articles, but the important here is this data that is time sample data. If you have some difficulties to follow. There is this user guide which very details to explain how you can use or how you can play with the data or whatever do. So there is a full list of the steps that you need to do, and you can understand better this data center. So as I mentioned, this is the small part, which is the data access. So now I go back to the presentation and I try to continue from there about the modeling, which is so I mentioned that the second functionality is about the modeling. So the network that I described in my presentation, this neural network that we developed, they are accessible by this web page also. So you can go there and you can play with these models. So you can understand how this model works and what they are producing, but there are two different ways. So either you can just go there. Now I will demonstrate this how it works. No, so either you can go there, you put the parameters that you are interested, and you generate for that parameter space. No, so you can see for different parameters how your model change, what is their behavior, etc. For both synchrotron Compton or external Compton, and of course so this is the panel where it is done. So you see that there are the names of the parameters. So you can come to the web page, you fill these parameters, whatever you want, you push the button, it generates you the model. So you can understand how the spectrum behaves in different beds or etc. But of course, the main functionality here is not the to generate data, is to perform the fit. Now I show you how you can make the fit. So okay, so this is again the same database where you are in this theoretical modeling section. So you see data access. Now you are in theoretical modeling section. So here you can simply fill the parameters that you are interested. For example, I just give you an example. No, yes, 30 parameters for electrons that are emitting, the magnetic field, the emission region size, okay, the luminosity of the jet that you are interested in, log scale, the redshift of your object, let's see. And there is a run model. So as soon as you do this generates the parameters for which you fill in there. So if you want to see how your parameters are changing, if you have different distribution of electrons, etc., you can play with this tool and you can generate different spectrum, and again, this spectrum that appears here is interactive. So you can simply zoom this part to see how the model behaves or etc. So you can play again with this block. So, but the main functionality of this tool is not to play with the parameters, but is actually to perform the fit. So I would like to demonstrate to you how it works. So yeah, now is the modeling part. Yes. Now you are, this is modeling part. So here there is upload a file. No, there is this button that you can upload the file. So I have some files. If someone wants, I can share. This is your data that you want to model. For example, this is the data of a blazar observed for some period. No, if you want to make the fit here, so basically what you do, you just upload your data, you provide the distance of your source. So you fill this part of here. You mention if the extragalactic background light should be taken into account or not, and you fill your email address. Okay. And you push the button fit. So then you get a message saying successful, we received your data, and now everything is happening in the background. So this goes through the neural network that I explained to you. So at the same time, you get an email on the address that you fill that you get your fit request is now being processed. Okay, so it's you get this message. Then you do whatever you want. You can go to take a coffee or do whatever you want. So the in the background, everything is in Dockers. So we have this Dockerized everything. So it will be easy to move from one server to another server. So if now we decide to change a server, we easily can go from here to other place because everything we build it is inside the Docker. So these Dockers are very, very powerful because you don't care about the environment. You just copy paste the Docker in another place, you set up the ports and it works. So now what is happening, this data is passing to the neural networks. This is done everything inside the Docker is now automatically. And the network is doing the fits. It's trying to find the different models, calculating every time they see this, and is producing the fit. So as soon as this is done, and it could be done in 1 minute, so we need to wait 1 minute. So you get another email, and this email informs you that your fit is ready. So basically, you do whatever you want in that time. The fit produces you. The network is producing the fit. Then the system communicates with you, providing you the data. So there is more functionality that here, for example, no. You see, for example, if you don't want to have the minimum energy of electrons that is changing over time, you want to have fixed value, you can fix this value. In near future, all the parameters that you want to fix, you can fix. And so there are 7 parameters. You don't want to have like this parameter free during the fit, you can fix that value also. So we try to keep it as simple as possible that people can very easily use, but also to provide the most, how to say, all the whatever you would do with your own code, you can do it here. So you want to fix some parameters, you can fix. You want to change the data, so you are not restricted by anything. You have all the freedom to do anything that you want. So you can come here, you can download the data, and using this data, you can make your own research and the results that you are obtaining. So let me see if it's right at the just a second. I want to show you what means. Okay, so then you get the email saying your fit results is ready. So you see there is so now it's the same saying your fit result is ready. So if you want to look, you can just go here. So if you click here, then it brings back to you, redirects you to the data center web page where is this model, and shows you your data and your model. So you have the modeling of your results. Again, this is interactive. So you want to see how in X-ray band the model explains your data, you can zoom it and you can see here. Not only you have the information about the parameter that it obtains the fit, but there are also some additional things here. So there are these best parameters that you can download. You can download the model, this red curve here, or you can also look this corner plots, which in this case is the posterior distribution of the parameters. So just to show you, okay, sorry, but there is, okay, maybe you can see from my laptop. So you can see how the posterior distribution of your parameter is changing. So it provides you the full information. So if you want to do a fit, you see it, plus you can download and you can do your own plot or etc. etc. So this is a very powerful because you can submit your data and the networks are performing the fit and it provides you the answer. So to submit the data is relatively simple because it just requires a text file with 3 columns. Flux, frequency, flux error. You provide, and the fit is done and communicates you back to result. So I think this is a kind of, I mean, no other place you can find that the fit is done in this way. I mean, so this is very unique, and it's the only data center that is based on the neural networks. So basically, this neural networks provides you the fitting, and the fit that is done is fully physical. It means that you have the injection, cooling of the particles. It's not just an assumption of the distribution of the particles or etc. So from that point of view, this is very unique web page. So we have a very broad user. So more than 35 countries are using. So by estimates, every day we have a very different countries. The people are using the data of the modeling. It's becoming kind of very popular. Unfortunately, I don't have the user map to show, but very interestingly that we cover some big countries like China, USA, some from Brazil, we have some users, so Russia, Europe, and all the countries. It means that the places where there are very good data centers, but still the people from these countries, they prefer to use our data center, which makes me beautiful. So in the last, when we finish, I mean, I have like 10 minutes. Even a bit more. Now we finished 3 something, no? Yeah. So the last part of my presentation, I want to show you something very new. This is where we want to change the concept of the data center. So this is where we want to transform this data center with AI. So this is, I think, in my opinion, more interesting because whatever I show you in a 2 or 3 months, it will be totally useless because then you will have someone that assistant that you can ask to do whatever I just explained, told you, and I showed you tutorial. So in some months, you can forget what I said to you, and you can just open this chatbot, and you can interact with this chatbot, and you can get it. So let me to start from here. So if you have an AI in research, it's actively used. No, you can simply group in 2 large categories. So one is this traditional methods like classification, finding patterns, etc., but which were very heavily used in research. For many years they are used, and they prove to be very efficient. So these are, you can have a massive data sets, you can find some patterns that human beings cannot find, but these tools are very effective to find it. But very recently there is this generative AI, which is progressing very fast. By generative AI, I mean these are this ChatGPT style of the tools. So what is the idea behind this? That this generates new data and text based on the prediction from the pattern observed in their trained data sets. So you train on large number of data sets, then it can generate new data based on your queries or etc. So my question is, can this generative AI help in the research or not? I mean, it's new, entering in all the fields, even in everyday life. So even in your smartphones, in your mobile phones, you have the Gemini, ChatGPT, whatever you have, so can help you with everyday tasks. So the question, can it help for the research or not? So to do that, we need to define what research. So research is like ecosystem of the contribution. So you have experienced researcher, which knows the field. You have the young researchers, either young postdocs or PhD students, which are doing all the computations. No, the guy knows the field, knows all the information, provides some comments, defines the problem, and the young researchers are doing. So in this context, the generative AI, if you look that there is an exponential growth of the scientific papers. So in arXiv, every day we see the new papers are coming. So even if the experienced guy, they cannot keep really the track of everything what is happening. Plus the students or the young researchers, when they do the coding, it takes time. But in this context, this generative AI could be really very helpful because it can contribute in all the aspects that I mentioned. It could contribute for the keeping up with the articles, plus it can help with the coding or etc. But this is not very trivial. It doesn't come very simple because there are challenges. So if you look all the current large language models, Gemini, ChatGPT, there is a very common problem. So you cannot use for very narrow field application. What the reason is very normal to understand because these are trained by billions, trillions of the parameters. So if you ask some specific, very terminology, they fail to produce you an accurate answer because they are trained on very large number of parameters. So they cannot provide you very deep answer about a very single blazar or neutron star or whatever you want because they are trained on very large number of parameters. So they know a lot of things to find the statistical coincidence with the text that you are asked becomes harder and harder because the number of the parameters is increasing very, very fast. They are trained, no? But for this, you need to find some solutions. There are some tools that are already used in the field of astrophysics. So this is like AstroBird, AstroLama, Pathfinder, or etc. The main functionality of these tools, they are trained on the abstract of the scientific papers. And they are great if you to help you to find the tools. So you want to find the tools about, not tools, sorry, articles. So you want to find some article about this object. These are great tools. You can ask, they have a very complicated searching engine, etc. They can find you your article that you want. But my question is, yeah, we have a very powerful tool, this ChatGPT stuff, etc. We want to use them only to search something, or we can have a better application. So this is just what we want to have something that is reviewing the papers, etc. Now, of course, the answer is no. You have a very, very complicated tool, and these are very nice, and you can have a way better application. So this is where comes the tool that we are developing called Astro LLM. So the main vision, the idea behind this, we want to have a research assistant. We want that someone sitting in your computer and helps you with everything. And this doesn't mean only to make a summary or etc. We want to have some tool that the main functionality will be should have a specialized knowledge. So you ask some specific information about astrophysics, it should be able to not give you the Wikipedia style answer, but should go very deep and provide you the answer. We should, I mean, any research assistant in astrophysics that does not have access to the data is useless. Because if you want to have an assistant, it should have access to the data. Similarly, any tool that does not able to make a modeling is useless, because these are two most important things for astrophysical research: data and modeling. And of course, this tool should help you to interpret the results that you obtain from the fitting or etc. And of course, the last thing that we want to put is the educational tool. So it should be very useful to attract young high school students, etc., to do astrophysics. So this is one of the tools of this thing. So of course, AstroLM is not very easy to build, and there are techniques behind it. And we used retrieval augmented generation. So this is a very powerful method that is very used in the private sector. So in the private sector, all these chatbots that you see in Lufthansa, whatever you go, are based on this method. So I can explain you what is this method. There is very simple example. So imagine that you have a chef that is preparing food in the restaurant, no? So if you go to this chef and you ask, make me an omelette, no? The very simple things, so he immediately makes these things, no? But if you ask a very specific dish, like, I don't know, some fancy dish that you want, even he knows how to do that because he learned that. But what he should do, he should go to the recipe book, read the ingredients, quantity of these ingredients, how much he is to use, etc. Then he should use his own skills to make this food for you, no? So this is how this RAG method works. So you have the recipe book is this retrieval, is the place where you store your data. And the skills of the chef is the large language model. So just to demonstrate how it works in a very specific case. For the first step, we use it to generate the tool for blazars, okay? Why blazars? Because I know the blazars, I can control whatever they are saying, but we are not going to be limited by blazars. We will include all the different types of the source. So just demonstrate how we did that. So from the NASA IDS database, we downloaded all the papers about blazars. Well, when I say all papers, it seems very easy, but it's 19,000 papers. So if you imagine that there is no single person that can read all the 19,000 articles and try to memorize them, no, this is impossible task, but they can, these large language models can do. So what we did, we generated this, we downloaded all of these PDF files. There are methods, you convert these PDFs to the text file, and from this text, you make chunks of the text. There are methods, you embed them in a vector space. So this vector space is a quite powerful thing that all the chunks of the text have a special direction, special coordinates, etc. And these are the most important ingredients here, because you can perform a search, very fast search here. So what is happening here? And you have on the other side, you have the large language model. In our case, it's ChatGPT, okay, paid version of ChatGPT, API access, etc. So what is happening when a user asks you the question about some specific problem? You don't go directly to the ChatGPT and get an answer, which will be like, very general answer. You come to this vector space. There are some techniques, etc. I don't go to details, etc. You come to the vector space, you extract all the information that user requested from the scientific articles. You collect all of this information, you pass this query plus the information that you collected from the vector space to the large language model. And you ask the large language model to generate the answer based on this information that you provided, not from the parameter that is trained, but from the information that you provided. In this way, you are avoiding to have this in AI, there is this word called hallucination. So what is hallucination? That AI gives you some answer which is wrong, but it insists that this is this is true. This is called hallucination. This way, you are able to avoid that AI is hallucinating, providing very wrong results, and the result that is providing to you is from scientific papers. You can do that with retraining. One of the most issue with retraining is called fine-tuning. So basically, you can fine-tune the model. But the problem with the fine-tuning is expensive first. And if in 1 week you want to update your database, you have to pay again. But this method, every day there are more papers in archive, you can every day add in your vector space. Why people are not doing the fine tuning? Because fine tuning, okay, if you have a one limited knowledge that you don't need to update it for the next 5 years, you can pay for the GPUs in OpenAI or etc. and you can fine tune. But once you fine tune and you add one more paper, you need to fine tune again. And this is, I mean, okay, it's not an enormous amount of money, but in science, every day we have more paper. So after 1 week, you want to update, okay, you go and you pay again the GPUs to make it, it's useless. So this is why fine tuning you can do in step by step, let's say. So you test this method, you accumulate a lot of things, then you do fine tuning, you wait another year, you do again fine tuning. But in the short scales, if you want to do because here, when I say it produces back to the server to user, this seems very easy, but there are a lot of things to do here. You need to test the prompting. You need to do this engineering to teach to do a good job, etc., etc. So it seems that this is super easy things, but believe me, like right now, three people all the time are working to improve these things, but which is not so easy to do. So this is just one example. So this was a very early version of the tool, but now it's more complicated, more better. So if you ask a question like, is this city 102 like a blazer, is a bright object or not? So it goes to this literature, bring back you the answer. Now we can see the answer. So it brings you back exact numbers saying that, okay, I don't know if you can read or not, but it says that the gamma ray flux is this value. Okay, this writing is changed now, is more beautiful, etc. It brings you the value, says the period when it was bright, or etc. ChatGPT will never give you this answer. If you ask if it is bright, ChatGPT say yes, it is bright because it's blazer. This gives you the general answer, but here you have a detail. So another thing you can ask about this, you see, it gives you the answer for all the bands or information or etc. So this is really very, very helpful and provides you a lot of information. But as I mentioned to you, I don't want to have only the tool that provides a summary from the articles. I want to have the tool that has an access to the data, has an access to the modeling, etc. And I can do that because I have the MMDC. So so these two are the most important ingredients for research: data and modeling. So if your tool has access to these things, it will be super powerful because it can do everything for you. No, so just this is we do using these agents. So there are these agents that you can build. So basically, we have the data from MMDC. Query goes to agents. The agent goes to the MMDC, generate the data for you, and bring back you the data. So to demonstrate these things, here is the video. So we transform how the data is retrieved. No, so okay, like in ChatGPT, you ask, get the ACD of PKS 2155. So this is the sort that Michele likes a lot. This is why I try to do something. So you ask this question, then the agents goes to the MMDC. What I showed you by hand that you should put the coordinates, you should do thing, the agent is doing it for you. As soon as it is done, it brings back you the data. This is whatever you get from the MMDC, it brings you back to here and says this is the data, what you want to do. Either you can ask to do more things, plot, blah, 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 or okay, I ask it to generate another data for another blazer. And the second he's doing, he's going to do MMDC again, bringing back to the results of your news sources and providing you the plot. Then you can play with this plot. You can ask, zoom this part. Like, I mean, when I started the things, in order to do a modeling with the necessity, I find a PhD student. We spend a time to build these things, etc. This is the best PhD student that you can have. So knows everything, knows all the data, knows the modeling. So okay, the second part of course is the modeling, and the same way we connect this with the modeling. So again, the user either gives the data or asks to the LLM to find the data and passes to the MMDC, chooses the models and perform the fit. So just to demonstrate, okay, here, okay, I already put the text not to type, blah, blah. So, okay, so this is not the fit. So plot the ACC for the following parameters. Like you will speak with your PhD student, no? You call and you say, can you plot for these parameters? So here I provide the parameters, no, magnetic field, electron density, all the parameters. How you would speak, you just type here. So what this does, it goes to the I don't know if it is stopped or is. So it goes to the CNNs, no? Okay, let's stop it. So it goes to CNN. Okay, let me to go back. So you ask this, so plot for these parameters, you provide the information. No, okay, sorry. Okay, you ask plot the ACC for the following parameters. No, you provide all the parameters, whatever you want. It just goes to the MMDC. It brings back to the plot. So it will come now, and then you can start to speak with it. So if you want, so this is for the parameters that you give. Now you can ask, okay, change the power law index of electrons to 2.5. So you plot it for 2, you can ask for 2.5. And it does the same. So it goes and plots it. So you want to interact with it. So can you do this? Can you increase magnetic field? Can you change the electron luminosity? Like you speak to you don't need to go in the coding. You don't need to go open any programming, any Python, etc. You can just simply speak. And you can ask, I want to have a 10 times higher magnetic field. And it does for you. But of course, the main functionality would be the modeling. So this is an example. You upload the data. Or you can ask, get me the data. No, you upload the data and you ask. Model the attached data with SCC, like you would speak. No? The source redshift, you provide redshift because we don't have redshift, it cannot make the fit. And you say, consider the EBL absorption. Get. So it goes to the, now I didn't ask about EBL, no, it asked, should the ABL consider it true or false? Should I use it or not? So it speaks interaction. So then you send this. I don't know if it is. Okay. I say yes, and it does the fit. It gives you back the parameters. All fit parameter when all can ask what means the polar index of 2, it explains you what it means. So this can really help you. So this is the implementation step. So it starts from blazars, but now we want to implement for other sources also. So here is written GRBs, but I don't know if we go first, second for the GRBs because there are. We might go to the TDL distribution events because which are also an interesting class of sources. But our final goal is to step by step include the new sources. But for this, we require a lot of collaboration. For the TDS, we have some people in MIT that we collaborate with them. For GRBs, there are some people in China that are simulating, etc. So this is not only in my group we've done these things, but this is a large collaboration that we try to collaborate with many people. And I think our final goal is to just have very broad application, a tool that everyone can use, independently if you do Blazar or you do Neutron Star or whatever you do. And this is my final slide, so I'm not going to read it. So just I showed you everything. So thank you for your attention.
Yes, so I imagine there are questions. I would like, nevertheless, to start with a comment. I mean, what you show really puts a big question mark of what is the future of tools or resources for citizen science. Because we cannot ignore the fact that, I mean, usually when you go to citizen science projects, what you see is people develop some applications in which the citizen can participate in doing science, but like doing the hard task of a data analyst or a data classifier. And artificial intelligence is changing that, is doing that much more efficiently. And with these large language models, it is allowing us to extract the information and actually enter a more meaningful knowledge dialogue with the citizen science. So that in principle, you could then bring the citizen scientist in to ask the questions and walking through the results. Although for this, you need some culture to understand the answer that is given. Yeah, so it's very easy to extract authoritative answer about a source from what you've shown. But if you don't have the scientific culture, you don't understand. You think you understand what you read. So it seems to point to a new way of doing citizen science, but also putting some challenge. So how do you see that?
Well, I mean, I think I can extrapolate your question to more broad because when we were in the school and now when the kids go to school are totally different because we didn't have the ChatGPT stuff, etc. In my group, I asked some young guys to hire someone. So there was a list of 6 people to interview. Okay. So they came by laughing because one of the guys who made an interview was reading the answer from ChatGPT. So they wanted to test, it was online interview. So they were asking the question. They said that we see by eyes that is reading and the answers that was giving were very ChatGPT style answers. So what I want to point to your question, I personally think with availability of these tools, we should rethink of a lot of things, not only citizen science, but also the education system, everything. This is unavoidable. We don't. I know that there are a lot of people that are very skeptical. They don't like AI, etc. But this will be the future. We like or we don't like. They are progressively developing, and I agree with you that we need to have the culture to follow these things. So I personally, what I do, I don't allow a wide, broad limits. So I always try to do the thing that I can understand the output. Because if right now we give to these large language models a lot of freedom. Let's say we go to raw data and everything, and we ask find something, they will find something. Whether it is trustable, what is correct, we don't know the answer. Maybe in the future, when we have like this 5th generation of self-thinking systems, maybe that time, but we are very far from this level to reach, no? But right now, we should not be afraid. We should say that there are these new tools. Let's make a best use of them. And I think personally, for citizen science, even for, look, I mean, the things that I showed to you, no, if you go to the traditional way, so if you want to find a PhD student that writes the code, performs the simulation, etc., could take like a few months, no, at least, even if it is very bright student. But with these tools, you can do it within 1 minute. So you are a researcher, you don't have anyone in your group that has the data or does not have the modeling, you can have it in 5 minutes. From the point of view of making your research faster, this is a way faster than what we would expect to do by humans. So I don't know the answer of your question, to be honest, because this is very new, all these things that we are doing. What I know that we need to progress in that direction, of course, always to take these measures of being very careful, or etc. But if we don't do these things, our development, our progress will be kind of limited, and we have to use the best way that we can these tools. And this is, many places I advocate the fact that I have been in many places where many people were really against AI. Like, no, let's don't do that. Let's don't do that. But first, if I don't do that, someone else will do. If I don't develop these things, maybe in 1 year, someone else will do that. I'm sure that they will do that. And you cannot really, the progress in that direction, you cannot limit the progress. I mean, like, I don't know, I'm using ChatGPT not only for science, but for everything else. So if I need to find answer or something, I just ask ChatGPT. Okay, sometimes it gives crazy answers. I have my own brain to judge what it's saying, but what my point is, like, they are entering everywhere. We like or we don't like. These are they are going to change all education, science, etc. No, to find a good balance. This is our duty as experts, as a scientists. We need to find a good balance as a citizen scientists or etc. But for sure, we should not be afraid of these new tools.
No, good answer. Just want to make a comment. So when we think about what Simonetta said in her presentation in the morning about the purpose of leaving no one behind and trying to reach most people, one interesting thing that these language models, these generative AIs provide, I think, is the fact that you can do education and citizen science with these things at many levels. So you can do kind of the top final information level very easily. And that was very hard in the past because you really needed someone producing, distilling the information. You need a teacher, basically. So now you can emulate the teacher to a certain level. And but you can also, of course, do the more kind of like skill transfer, training, capacity building that is under this. So an interesting thing is that perhaps this opens layers into a same structure, various layers of the kind of training that you can and capacity building you can do. for different publics.
Actually, you are right. This is not solving all of our problems, but it's opening new perspectives where we have to look. And I think from that point of view, this is good because this is a huge opportunities for everything and everyone. And I personally really think that we need to really consider how we can effectively use this AI in our research.
Hi, we've been using LLMs to create mind maps. We're working with the old school mind maps using the original AI to develop a program of thought that we could apply to education. Once we started using LLMs, the whole thing changes, the whole thing. You can develop a series. I've only got RAM-based LLMs, which is interesting because every time you talk to the LLM, it doesn't recognize you. So what we're missing is your database. Add one of those to LLM. It'd just be amazing because you can create through papers. It gets very close to consciousness, the way that consciousness works, because all you do is you augment the amount of RAM. You don't need a program anymore. You have collections of memory, which we can think of as the universe itself. And those memories read themselves in order to give you an idea. And it's up to us to understand how that idea works to tell the computer or the program, or exactly like you're saying, a PhD student, to reassess what it is that they've given you so that you can understand it and better reorganize it. So this, RAG, did you call it RAG? That's just outstanding. Can I work with you with that, please? Yes, please. I would love to work with that.
They are building these chatbots. And this is as I told you, this is cheaper and faster method to do. Fine tuning is good when your information has to be limited. So if you want to rate fine tune every week, you have to have a budget of a lot of money because depending on the number of the boards, etc., fine tuning could be not impossible because there are like models like Gemini, lots of things that you can download. You can little bit change and you can fine tune your model, but computational resources are required. GPUs, really very strong. Most of them, we don't have the GPUs. They have the GPUs. You have to pay them in their systems to fine tune your model, which is good. But if you like to pay this amount of money every time, do it. But you can get equally good answer from RAG, which is cheaper.
Hi, Narek. Thank you very much for such an inspiring talk and congratulations for putting AI in scientific work. It's surprisingly a modern tool that is not widespread. So as you said, it will change for sure at the time, right? So you showed lots of interesting things, and in a way, it's kind of part of what I do also at university. So first, I was about to talk about your background, but you already answered to Jamie, right? Your background on this, right? So yeah, yeah. Sure, which is the key of science. I mean, to be interdisciplinary. So good for this. And first, on the first part of your talk, you showed models based on CNN, right? So we know CNNs are mostly based on input being images, right? So you said time series. Are you, first question, converting time series to images in a way? Or you're using them, you're using 1D CNNs, or what kind of CNN is it?
The CNNs were, you are right, they were good for imaging, so they were in analysis. But very recently, there are many different applications of the CNNs for I mean time series analysis is like the data which are connected together. So like, and they, when we were developing these things, we were trying CNN, several other neural networks as well. I don't remember the names, but the best performance and the best results were provided by CNNs actually. This is why we concentrate with the CNNs. No, they are simple, but together with the simplicity, they provide very nice performance. The same is like if you work with the tabular data, you don't believe, but this random forest, this tree stuff, they like 50 years old methods, but they still provide a wonderful performance. You know, yeah, they are very efficient with the tabular data. So I think this division, which one to use, is like in our AI. You have to try to see which one is good, and apparently sometimes we end with some good models. Huh?
And related to this second part, you introduce RAG, right? So which is RAG is basically an architecture. So what Ulises was asking, of course you have fine tuning, but we don't want to do this because when you fine tune your architecture, you have encoder decoder thing, but then you end up on a classification problem, which is not the deal here. So you need to produce embeddings, which are these vector-based databases, what we call in DevOps or MLOps nowadays. And then you extract information from this. So it's a vector database, which is the technical name is a vector database. So that's the point of building a RAG, right? Haven't you seen such a thing in, I don't know, conference in the United States? I mean, people is not using this kind of, and the thing is, have you published this architecture? Have it this on a paper? It would be interesting to check it out. Thank you.
Well, we are publishing it, but before coming here, I have the call with the people in MIT. So there is an interest from MIT and Caltech. They want to do a joint project on these things exactly. So I think in a very near future, the paper will come out within 1 or 2 months. So the paper is, I mean, the work is very advanced with but for USA, we are going to start very good collaboration with them, and which I am very positive, and I think it will be very nice because MIT and Caltech are the strongest contributor in the field.
Yeah. Hi, Narek. Very nice tool, the Astro LLM. My name is Bernardo. I'm from CPPF. I'm a professor. I have one is a quick question. You're using ChatGPT, but you're processing in the OpenAI servers. Okay. No, yeah, I understand. It's just okay. Yeah. Change to German. Okay, but your vector is also the embeddings are also there. It's local. Yeah. Okay. I know. Yeah. Okay. Yeah. Okay. And my question, which is actually the question is, are you planning to do RAG for a whole astrophysics? Because I think you hit the wall. Are you planning to do the same thing? You're planning to expand from blazars to GRBs to astrophysics in general. If you're doing RAG, you will hit a wall because you cannot do RAG with 1 million documents. It will take a day for the answer to come. So what's the plan?
The plan, I understand the question. First, the plan is we don't want to put all the paper like GRBs, blazars in the same RAG in the same vector space. First of all, we separate these things. Second, we are implementing these graph search methods, which will initially based on the abstract. So now what we do is so if you end up with a RAG, the time will be very long. So now what we do first, we do search in abstracts. We find all the relevant papers which are also connected to each other. Then we make the search in the vector only on that papers to avoid to be faster. Even with the blazars, 90,000 papers, you will have a problem with the timing. But if you implement the search based on the abstract as a first step, so you search on the abstract, you find the key papers, then you select only that papers from your vector space, you see. So this is speeding up the thing. And my idea is that when we build for different type of astrophysical sources, it will not be one RAG for everything. So basically there will be these smart agents that decide the question is about TDE, goes to the TDA vector space and gets from the TDA vector space. The interdisciplinary, I think this is coming to this prompt engineering where you have to work there and you can implement different ways to check. the difficulty here, you need to try a lot of things to have this better prompt engineering, and which is taking actually the most of the time. But I think you are right. If you combine everything in one place, you might face a problem, but there are solutions. Hopefully there are solutions, which we know. Uh, Thank you, Narek. I would actually have hundreds of questions, but maybe you can do it later. I will just do one. Okay, so my question is like, okay, you feed like all the papers from Blazers, for instance, right? But do you add some weights, like if some? You are right. I mean, first of all, do you need to put weights of different parameters? No, like time. You have to have one most recent. Another ways that you could put is by citation. So if there is one paper with 0 citation about one blazer, and there is another one which has 1,000 paper, somehow you have to put more weight on the. Okay, this will be some kind of biased, but the good thing that we want to build the prompt such that it provides you the answer and says there are alternative this, and giving the reference that you can go and check yourself. So it will be your responsibility as a scientist to understand which one is good. But for sure, if you don't put the weights, then you end up on the jungle where you cannot do it. But we are introducing some weights. So for the connections, so the question is, one important question is we drop out all the introductions from the papers, first of all, because introduction is useless information. It repeats for all the blazars. Always there is a reference to the Uru Padovani paper, for example, which is a wonderful paper, but it repeats 19,000 times. So it doesn't make sense to to keep it in the vector database because the paper itself is already there. So there are ways that you need to work. When I presented, maybe I presented too simple. You do this, but this is like lot of work. Even to download 19,000 papers is not very easy. I'm not going to say how we did, but it's not easy. No?
Good. So we overshoot time, but I think it was an interesting discussion. Thanks, Narek. Let's go for coffee and be back. Basically, try to be quick in 10 to 15 minutes to the last session. Okay, good. Thank you. So first talk is by Marcela, and it's very interesting because it's a work that was done using the Firmamento tool together with various colleagues that are listed there to produce a catalog of sources from Fermi-LAT and another satellite observations. So Marcela, it's a pleasure to listen to.
So good afternoon, everyone. As Ulysses has said, my name is Marcela Gouveia. I am a master's student here at CBPF, and I'm going to present a little bit about this work that was developed last year along with this group, WNF-LACA, Firmamento-based catalog of AGN, and Fermi-LAT high galactic latitude gamma ray sources. This work was a follow-up for the work developed with the high school student, which was presented on Monday by Michele with the Firmamento platform. Well, first of all, the main object of study for this work were blazars, but I think all of you are tired to know what blazars are right now. I'm going to be very quick about this. So everyone knows right now that blazars are AGNs whose jets are aligned towards us. Blazars exhibit this specific kind of spectrum, which exhibit these two peaks. The first peak is between the infrared and the X-ray band, and it's attributed to synchrotron radiation. And the second peak is from soft to hard gamma rays and is attributed to inverse quantum scattering or hadronic processes. We can classify these blazars according to emission lines as BL-LACs or flat spectrum radio quasars. And also we can classify them according to the position of this first synchrotron peak. It can be an LSP, an ISP, or HSP, which means low synchrotron peak, intermediate synchrotron peak, and high synchrotron peak, according to the position which is related to the energy of these blazars. Blazars are the most abundant type of gamma ray sources, of extragalactic gamma ray sources. And this is evidence in the all-sky surveys in the gamma ray band, such as the Fermi-LAT Space Telescope. This survey resulted in catalogs, very important catalogs, such as the Fermi 4FGL DR4, and which is the fourth data release of the 4FGL catalog, and the Fermi catalog of AGNs for LAC. However, so the importance of blazars is the preeminence of blazars in these catalogs underscores the importance of accurately classifying and identifying these sources. However, still approximately 25% of these gamma ray sources in the 4FGL catalog are not yet appropriately associated with a known source. And these sources, these unidentified sources, represent potential new blazar candidates. So what is it that we did? We have used Firmamento to perform a search in the catalog, in the high galactic latitude sources of the catalog, which is B larger than 10 degrees. Firmamento, as you all know by now, is a platform developed in the open universe context focused on blazar discovery. Here I just say a little bit about what happened with the high school students, but we all heard from them on Monday, so I'm not going to go into a lot of detail from that. But I myself was during my bachelor's degree when I started this work, so it shows that you don't need to be a fully trained researcher to participate in scientific activity. And that's a very big deal when we're talking about citizen science, right? So what is the Firmamento platform? We all heard about a lot about today, so I'll be brief about it. But the main tools we have used were the ERSI, which is the Error Region Counterpart Identifier, which is a tool that gathers information from over 50 remote catalogs. And in an area region, you give an area region to ERSI, and it's going to gather this data and locate sources and identify possible counterparts in an area larger than 20%, 20% larger than the area region you have given to it. And it builds SEDs, SEDs actually is build spectrum for each and every counterpart it identifies for the radio and X-ray sources. And it determines whether this source it can be a blazer, it can be a galactic source, a radio source, whatsoever. Also, what was used was the set building tool of Firmamento. We used the VOU blazers, which gathers data from 90 remote catalogs to obtain these plots such as this, which you have seen a lot today, in which we can characterize the sources properly according to the position of the synchrotron peak using BLAST, which is a machine learning tool to localizate this peak, and WPeak, which is a tool based on infrared data to classify, to find the position of the synchrotron peak. This here is the results, for example, for this blazer over here. And we have used this to to accurately classify the sets. So what exactly is that we do? We created a table. We ran see through for the 4FGL sources for high galactic latitude. We have originated a table in which we uploaded it to Firmamento, and one by one, with obviously a large team because there were 5,060 sources, we have checked each and every one of them for the possible counterparts, the possible candidates, and we have selected the candidates which made more sense, let's say. For example, this source over here, we ran URSI. It's a random one. I picked it because I don't know, because I felt like it. And it gives us only one possible candidate, which URSI lists as an HBL, and it gives us the galactic coordinates and the redshift of the source. As you can see here, it is the it's made with Aladdin. Here you can see the image, and the error regions for radio is in red, and blue is the X-ray error region. So we have several data for this specific source. And here we have the SED for this source, which is characterized by the new peak obtained with BLAST and with WPeak. So this is the only possible counterpart for that 4FGL source. Okay, so that's our blazer. But however, not all of the sources are like that. For example, in this case, we had two possible counterparts in which that URSI has identified. The first one here is listed as an X-ray, and the second one is listed as an HPL. So we think, okay, so probably the second one is the most likely. So what we do, we inspect it in all of the energy bands to take a look at the behavior of each and every candidate, and we build SEDs for each candidate. So as we can see, this second source here shows radio emissions. This is the NVSS survey, and for X-ray emissions as well. And these are the SEDs, the SEDs for both sources, and we can see that this is most likely what resembles a blazer. That shows approximately the two peaked profile I've shown you before, and we characterize it. So then we take note of every single thing I told you about. So we take note whether this source is a blazer, a galaxy, a pulsar, the set type. So we see what's the position of the synchrotron peak and classify it as an LBL, IBL, or HBL. The synchrotron peak estimated by BLAST, and the most importantly, whether we agree or not with the 4FGL association. So if we see, okay, 4FGL chose this counterpart, and we agree that it is the same blazer. So, okay, same blazer. However, there are some cases of disagreement. Sometimes 4FGL does not identify any sources. So a new blazer, and we found one, so a new blazer is identified. So finally, the results. These are the main numbers. We have agreed 86% of our sample. We have agreed with Fermi. However, we had 12.6% of disagreement, which is not a lot, but is very relevant. In this, we have found 415 blazers, new blazers, which represents a good number for because before we had 25% of previously unassociated sources. Now this lowers our number to approximately 17.2%. We also had cases in which 4FGL associated with one source, and we switched our association to an alternative blazer. We have cases that for FGL does not find a counterpart, a possible counterpart, and we do not confirm the for FGL one. And we had cases in which Firmamento fails to find the for FGL counterpart, possibly because ERSI relies on radio and X-ray data, and sometimes we don't have enough of it. So this is an example of a case in which we have chosen an alternative blazer. These are the sources that ERSI has given us. These are the candidates. And this is the FGL's counterpart, for example. Here, ERSI does not recognize it as a possible counterpart. However, as you can see, it has radio emission, but in X-ray, this one, I don't know the name of it, but it's much more prominent. So it's much brighter. And when we take a look at both of the sets, this is the set of the counterpart we have chosen, and this is the set of the counterpart that was proposed for FGL. So we feel that it's way more, how can I say, interesting. And for the cases of new blazer association, for example, this source over here didn't have any counterparts associated. And we found one which has this profile and it is compatible to the one expected for this specific gamma ray region. And these differences arise probably from the use by Firmamento for multi-frequency data sets such as the ERAS survey, Swift blazer analysis, which are very recent. We have new identification criteria, and we included potential counterparts beyond the 95% error region, which is okay because we know that by definition, 5% of the sources are outside of the 95% confidence error region. And beyond that, we have accepted counterparts in sparsely radio or X-ray regions through advanced modeling, multi-wavelength modeling. And this is the profile of the distribution of the new blazer associations we had, in which we can see that there's a large number of HSPs, which is very interesting because most of the sources we have in the FGL catalog are LSPs and ISPs. So with that, we have built a new blazer catalog in which we called 1FLAC. This is the catalog. Is the face of the catalog, let's say. It's going to be uploaded into Firmamento. You can, sooner or later, it will be available. In which we have the catalog name, the coordinates, the type which we found, and the position of the synchrotron peak. This is the distribution of our associations. Altogether, we show that mostly we have LSPs, a dominance of LSPs, and this has a very similar distribution to what we expect from the FORLAC list of blazers. However, for the newly associated blazers, which are these guys in orange over here, we have a greater prevalence of ISPs and HSPs in comparison, so that's interesting. Beyond that, we also can analyze, we also plotted the position of the synchrotron peak obtained with Firmamento and the position of the synchrotron peak for FORLAC. This line over here represents the values which are equal. Obviously, it's going to have some scatters over here because of the differences in the data sets. However, in this case, we have three regions of main difference for 1 and 2 over here. Firmamento estimates a much higher new peak than FORLAC. And this is probably exactly because of the availability of X-ray data sets, of X-ray data, and high quality X-ray measurements, let's say. And in this case, it is the opposite. So FORLAC estimates a higher new peak than Firmamento. And this is most likely because of limited X-ray data in FORLAC or a potential misinterpretation of X-ray data as the end of the synchrotron component rather than the IC component for Firmamento. So basically, that's it. We have developed a new catalog based on the FGL using the tools by Firmamento. This is very interesting because it had the involvement of undergraduate students. I myself was one of them. The former high school students who were also participating in this work as well. We found 415 sources which were previously unassociated, and that reduced the fraction of unassociated sources to 17.2%. And we anticipate that this number can be even more reduced with more data from such as Rosetta or others. We also have used machine learning and infrared-based methods to estimate the synchrotron peak frequency. So that's minimum human interference, and help classify these blazars accordingly. And one FLAC will be available in Firmamento. So these are, oh, sorry, that's the paper that's been submitted. And we hope that it will be published soon. And that's it. Thank you. This is my reference. Thank you very much.
Thank you. So I just want to make a comment. Marcela was an undergrad student in my group, work with me. And well, when we started working together remotely because we were in another state, it was what, 3 years ago. So a long time. And we did all the studies of introduction to blazars, play with some modeling tools, etc. But it's amazing how a tool like this, where you can get a lot of data in an easy way, put them together and do some analysis, really boosts the capability of doing research. So I think this was really the experience that we had to really get a young student involved in the doing of a scientific work, preparation of data, data analysis, data curation, writing of the paper. So real contribution. I think this was really a great experience, and it's part of the power of these tools. I wouldn't call this citizen science exactly because it was studying the field, but it represents a big boost. And it's impossible to do a work like this in the short time scale that it was done without all these data gathering platforms that are being developed. So, I don't know if.
Hi, how long did it take you to create that entire research paper?
So actually, when I entered the group, it was already being done. So I think Michele would be probably the best to answer that. But from the time I started working on this, I think it was like August last year. So we ended the work on December, around December. So, but it was already being done. So it had already like 50% of the work done.
I don't think that exactly knowing how long did it take, it's very relevant because it depends, on what do you mean. The issues that we found, at least that I learned out of it, is that if you want to include a larger group of people with less experience, well, it also happens if with people with experience, but even more, you have to define very, very clearly at the beginning all the rules. This project was made more complex because at the end, we ourselves started to change the question that we were asking ourselves. And then at the end, we have to do, Paolo and I, a lot of checks on what was done before. Okay. So that's what I also said at the beginning. If you think about projects for the larger, for the broader science, you have to define, if you want to go a little bit more, the obvious things, you have to think about it very carefully because then you cannot go back and ask people to do it again. Okay. But I would say that this is few months. Actually, I am about to start another project related to this, like a second step, and it should be finished in few months. So a few months, 1 year from idea to papers. Okay?
But what I meant with my comment on timescale is that there is years of data gathering before it that enabled this. So, and this is, I mean, the amount of data, it's not banal that you have all the data integrated, no, at easy reach.
Thank you for the presentation. It's a very good work. I have like a naive question because I've never worked with astronomy. but how the classification is made, like it's like a qualitative classification according to the images, right? Or is like a statistical test or something like that. And the second question that I have is, I saw that there's a lot of people involved. So this number of people, it's because like it's a lot of blazars that you analyze it. So each people analyze a little bit of the catalog, or it's for the cross-checking. So how the group is organized in the analysis.
No, because she arrived later, so this part she doesn't know probably. So at the beginning, we were just contacting people from different points, people that I knew that we received interest. But then I put the rule because everybody has a lot of things to do, but it appears as high school students are more busy than myself. Okay, and so yeah, and so at the beginning we said, okay, let's start doing this. There are 6,000. Okay, we have everybody can do whatever they want. But then at the end, I said, okay, if you want to sign the paper, then it's at least 200. Okay, or 300. I don't remember. You were there, no? Exactly, 200. So we decided to set this. 200 is maybe 5 minutes per source. Okay, 5 minutes per source. So to be able to put some commitment, okay? And this I actually checked because online there are some other citizen science project like tossing a coin, okay, with some rules. And there was also this idea, no, I don't know, if you want to participate really, then it's an effort. So 1,000 times. If you want to do just 50 times, then you go into the acknowledgement, no? But at the end, I always want to reach to the publication. For me, it's not only the game of doing this, but is bringing the guys up to the publication, discussing the publication, as was said by the students yesterday. It's an important problem because it's totally different. Then you have to decide exactly how to say, what to say. So I like to think about any project toward a publication in a scientific publication. Okay.
And in fact, the step of classifying, producing the SED, verifying the classification, the position of the peak, this could be a kind of a Zooniverse style citizen science project. But then there was all the science around that, with the paper, the discussion, the scientific question, the analysis. But yes, a part of that could have been done over Zooniverse, for example. No, we don't have time for. So now there is one very anxious man in the room, so you can come. It's the time for a talk. Thank you, Marcelo. He's jumping on his chair. So Marcos is another student from the DPF that works on blazars as well, on AGNs, and he's going to present his work.
So, hello everyone, my name is Marcos. I'm a master's student here at CBPF, and I'm supervised by Professor Ulisses too. And my project is about optical polarimetry modeling of blazar jets. Here's some table of contents. And firstly, I'm going to talk about AGNs, that stands for active galactic nuclei. An AGN is basically a supermassive black hole in the center of a galaxy. And it accretes large quantities of matter all the time. And from its accretion processes, it can produce a collimated jet of relativistic particles. And depending on the viewing angle, of this jet in relation to us here on Earth, we can classify these objects as many types, such as radio galaxies, quasars, blazars. And in the case of this work, we work with the blazars. Blazars happen when the jet is pointing towards Earth, more specifically in an angle smaller than 15-20 degrees. And they're so important objects because they are potential cosmic rays accelerators. And when we study the blazars, we are basically looking at the jet. So we can look at the photometric data or the polarimetric data. And in this work, we studied the polarimetric data. So basically, the polarimetric data, we are looking to 4 parameters. There are the Stokes parameters. The first one is I, that is the total flux. Q, that is the polarized flux in the direction. U, that is the polarized flux 45 degrees rotated direction for Q. And V, that is the circular polarization flux. So we can build this Stokes sphere that is in this 3D graph in which S1, S2, and S3 are the Q, U, and V parameters. And I is there is the total flux is the surface of this sphere. So here we can get this first trigonometrical relationship. And the second relation is the relation between Q and U and I with the polarization degree and polarization angle of this jet. There's P and theta. And this last relation is basically to show you that these Stokes parameters have an additive property, which means that the observed flux, the observed parameter Stokes can be the sum of various components. And I'm telling you this because in this work, we are working with the 2 components model. So we suppose that the observed parameters of the jet that we observed in the jet are basically the sum of these 2 components that have the physical meaning of 2 population of particles that passes through radiative processes, and one population generates a polarized flux radiation that is constant in time, and another one produces a polarized flux that is variable in time. So there is various scenarios that we can consider this model. This is one of the scenarios that this is the graph of a campaign of the Blazer PKS 2155 of this data were taken in the Pico dos Dias Observatory at LNA. And this is the photometric flux, the polarization degree flux, the polarization degree and the polarization angle. And here we can see that the polarization angle have a quasi-linear increase. And this can be explained by the 2 components model. So in this work, we basically we replicated 2 methods to separate these components, which means from the observed parameters, we could find the polarization degree and polarization angle for each one of the components, constant and variable components. And we have applied to artificial data from a simulation of turbulent jet. So firstly, I'm going to talk about the simulation. There is a turbulent extreme multi-zone model that is basically a simulation of turbulent jet. It creates a jet by merging several cells with cylindric symmetry, and in which each of these cells have its own turbulent magnetic field. And this is a largely used code in the community, and it's very powerful. You can consider up to 16 cells. But here in this work, we only consider 2 because the more cells you put the model to run, the more turbulent it stays, so it will be difficult to study. And use that simulation to obtain artificial polarimetric data based on the real physics of the jet. So here's the result for the simulation. We get 300 days, temporal evolution of the jet for 300 days. And this is the same graph that from that campaign that I showed you. That is the photometric flux, polarization degree, and polarization angle. So the first method for component separation is the components addition method. From that relations that I showed you, we can do some mathematical manipulations and get into these 2 equations. That is the relation between Q, U, and I, and the polarization degree and polarization angle for each component separately. And when we plot this data, Q against I and U against I, sometimes the data sets have a linear behavior. So when this happens, we can just do a linear regression and get the variable component directly from the slopes of these lines. So we can do some more mathematical manipulations, and we can get into these 2 equations that are the polarization degree and polarization angle, observed polarization degree and angle, against the same parameters for the constant and variable components. So we can basically do a fit because we have the observed one, the variable ones that we got. So we can fit these two equations to obtain the constant component. So we did the component separation. The second method is the Bayesian model that basically uses the Bayesian statistics to find these two components. So we basically have here the probability, and we assume likelihoods in prior functions to calculate this probability. So we basically set this this y, that is a q and u, the Stokes parameters from one of the components. So in this case, the constant component. We have x, that is the observed component, the observed data. So we basically generate random y and calculate the probability and saw if it will converge to some point. Here's the Markov chain Monte Carlo that we used to converge the probability. That is basically telling you this: it generates a random y, calculate the probability, and saw if it will converge to some point. So the results. The first method, the components addition, we applied this to the same blazer as the paper that we got this method. So we got this, we could do this component separation. Here I just put the constant component because the variable components there are many variable components for each point. So I didn't think that it will be visually easy to see. So I decided to just put the constant component, and it was compatible with the paper. And here in the left, in the right, we applied to the artificial data. And here is the constant component for this artificial data set. And here is the results for the Bayesian model. Here we applied to the same blazer as the paper from the Bayesian model. That is the blazer OJ287. And we got this constant component and a lot of variable components. But again, it was compatible with the paper. And in the right, the same for the same method applied to the artificial data. So we basically replicated the methods for two papers for separate the components of the blazer and applied these methods to the artificial data from that simulation that I told you. And we are looking basically to improve, for a way to improve or to create a new method that without the restrictions imposed by these other methods. So here is the references, and thank you.
So, any questions? This has nothing to do with citizen science. Yes.
Hello, Mateus. Thank you very much, and congratulations for this nice work. Nowadays, there is a trend in science that we try to spread it to the broader audience. So there is initiatives like open science and reproducibility of data and methods, especially. Have you, because it was written on the conclusion, so I also felt that it was like you put your heart on trying to replicate, replicating papers, it's a challenge always, right? But have you found such documentation of people trying to put the methods and not only data, but also repositories, GitHub and that kind of stuff open, or it this conclusion as a replication of the methods, your contribution, was your own work? Thank you.
Actually, maybe I can answer to that because he was also an undergraduate student, and the idea was to put him to redo some work that had been done by me and the group in the past, so that he could learn the procedures and get into the topic and making sure that he had a point of comparison. So Well, to some extent, yes. Sometimes we do try to reproduce, even when you are a referee on a paper, try to reproduce the results if you have the tools to do it. Yes, reproducibility is a serious issue in science. Not always people look deep into it, but it's something that all papers and results should be reproducible. That should be a standard, but it's not easy.
Hello, thank you so much for presentation, very good work. I didn't understand very well your likelihood analysis. Could you explain more what are the hypotheses that you are testing?
Well, basically, there is a uh, basically this is if I remember well, this is a very standard likelihood used for a Bayesian model. Uh, so I guess in another works using this same the same Bayesian model use uh the same configuration of the likelihood. So it's the observed parameters, the what we infer, that is the variable component here, and the standard deviation of the observed ones. So I think it's the just the standard likelihood that we used when we are using the Bayesian model. Yeah, I did have to find the exactly way that it was in the paper to reproduce this model. So we are trying to improve those models or try to create a new one so that we can do this component separation without the restrictions that these methods. Yeah.
Good. Okay. So thank you very much, Marcos. And now we go to the last presentation of the workshop. Aldo Diaz from Goiás, Federal University of Goiás. So if you can have the last set of slides. Yes. But we're not there. Wait, you're just a second.
Okay, so thank you very much. My name is Aldo. I'm professor in robotics and AI at the School of Informatics in Federal University in Goiânia, right, in Goiás. So my talk will be slightly different from what we have heard until now, which was interesting talks. But I will put a little bit more the discussion in the last 15 minutes on what I can show to you that it's an initiative of a new group. We started in the aerospace area in a broader sense. Okay. Yeah, so this is a little of my background. So I'm a researcher in robotics and image processing mainly, right? Which now is considered part of AI. So I've been working during the last 4 years in these three topics that here in Brazil educators do at the university level. So teaching, research, and community also, which maybe is not that common in other cases. But I will try to discuss about more on this field, right? So what we do as community as part of our job is to put science to the broad audience, right, to society, right? So what was the initiative? So we started this so-called Núcleo de Pesquisas Aeroespaciales, or our aerospace research group. It was formed by a motivation that was the first Brazilian Olympics in satellites, right? So-called OBSAT, right? OBSAT. So I joined the challenge and put there two groups, and then later found one of my colleagues was also participating, Professor Marco Asfalk, and then we collaborate together after finishing the competition. We two passed, and then we end up with these first two groups. So this was the beginning and the origins of MPA, right? So we have the Millennium Project, which is a group that started by students mainly from computer science or computer engineering, and then Goyasat, which were students from the School of Mechanical Engineering, okay? So this is part of the crew. These are some slides created by the people that were working there. So it's slightly has grown a bit more than this. So there are about 20 or about 30 people now interested in this kind of discussions, right? Yeah, but the thing is, the thing was new. I mean, the motivation of having an Olympics, as we will have tomorrow, right? The Sciathon was a hidden demand here in Brazil. And why can I say this? Because I experienced this, right? So lots of students trying to hear interesting topics as we have here, trying to join some research group, trying to put some collaboration, explore data, and go farther, right? From the limits of the university areas, university walls, right? So that's the thing. So then we end up participating in these Olympics, and then at the third stage, we held a launch, a suborbital launch, and despite we were like newcomers to this initiative that started by the Ministry of Science and Technology, which was from the previous administration, right? We end up being organizers of this regional event. So what you saw here are pictures from the first launch of this suborbital launch, so on a balloon, right? And we put two missions already there. So the first edition was in Guyana, and the second one was also in Guyana. It was interesting. We had like broader results. On the first one, we launched just one payload of a satellite. It was not recoverable. People used to say that it ended up lying on the shoulders of a ball, and then the ball just ran away. And the second mission, we had two payloads, and then they were recoverable. Okay, and then this nice picture at the end of the presentation the competition and then pricing, right? So students were winning prizes. So these are like the 4 steps. So conception, it was the first part of the Olympics. It was done remotely, right? Right at the beginning of pandemics, so everybody was in lockdown, but it was a step that was based more on a proposal of a project. So you need to build on a mission of what your satellite would be, right? On the second step, we had this project stage that involved us more abilities on developing this proposal and then having a specific payload for your satellite, also done remotely. And on the third phase, that was what I just showed on the pictures, we have this testing part, right? So the testing part was done physically. So then you build your satellite. There were some modules predefined for this, and then you pass some tests like mechanical stress, vibration, interference, radioelectric or radiomagnetic interference, and so on and so forth, right? And on the fourth stage of the Olympics, then it's expected to be a launch, right? A suborbital launch on a rocket, right? But this is to be done still, okay? So the first project is this Millennium Project, where I was helping the students there. They had this mission of mapping the South Atlantic magnetic anomaly, right? We know that there are lots of anomalies related to magnetic field. So this one was of interest of the students because it affects Brazil, right? So it's exactly this. It's a picture from ESA, right? From the European Space Agency. So it produces a deflection of the magnetic field that we know works as a protection layer against radiation, right? So whenever we have this depression, so it means we have less protection. So it's a matter of worry from a scientific matter, okay? So as things were passing by, at the third stage already, we started collaborating in what is called the super chimmy, right? So super team was from the top 10 projects or groups that were classified by the Olympics. And then we were supporting the building of the payload of the mission. So what was the mission? So sensing magnetic field, right? On a satellite, which is a nanosat. So the students developed this board, right? This payload board, which is a board that specifically have some instruments like dedicated magnetometers or an array of magnetometers actually on a 3-axis array. So they are 3D, right? And then they were doing this on an applied basis, right? So the first one is on the left side is the first version of this implementation of this board. On the second one, there are some noticeable improvements as these Faraday cages that are having some extra magnetic field protection, okay? Good. And another thing I would like to show is an ongoing development, which is related to our first ground station, right? That we are implementing also as a part of the group activities. So this is work made by Mateus Aparecido from MPA. So they started to develop a known ground station in order to be able to train students and people in abilities involving reception of satellite signals, decoding and processing of this information, okay? So the goal here was to produce a setup, a framework that is open source, so everybody can take a look at it and discover things on their own. That was the point, right? And also serve as a training platform for people. So here there are these 3 parts that are the basic of this setup. So a transition antenna, of course, for reception of signals, of satellite signals, a radio, which was a programmable radio, so an SDR, on a, low cost or inexpensive processor, which is an Orange Pi board, right? And then the final mount, right, of this setup, which is um, yeah, you can take it wherever you want, right? So easy to transport. Okay. Oops. No, was slightly too fast. Yes. Okay. So here there is an example of the data that Mateus was able to decode as a proof of concepts, right? So this is an spectrogram of some satellite signals that we managed to observe in different arrays of configuration, right? So this is basically geometric data, right? That we are looking at it at the spectrum, right? Okay. And then some characteristics, some technical characteristics of this second mission from the group is that it's a SatNOX satellite ground station, right? So what means SatNOX? So it means that it's part of this new initiative where people is trying to develop capacity on a wider sense to what to do with what to do exactly this. So downloading signals from satellites that are observable and trying to communicate with them, right? Try to check at the data to do analysis, okay? So surprisingly, here in Brazil, there are only 5 stations that are part of SatNOX today. And ours is just one of them, right? What Mateus did, it was just the first one, at least in Goiás, and one of the 5 ones we just have in Brazil by today. Characteristics of the detection, it's was able to detect satellites at 30 up to almost 90 degrees of elevation, which was quite good and steady results, and lots of the modulations that work with CubeSats missions, okay? Yeah, and then some examples of what were the observable data or what were the observable satellites that you show in the previous picture, right? Good. So this is it basically. This is the end up of the second round of the Obesachi Olympics, right? There in Goiânia also. We managed to help this catch the attention of lots of people, lots of students from all the levels, from schools up to undergrad level. Okay, so it's interesting to see how, at least here in Brazil, this demand of looking at the space, looking at their space, it's also it's always a curiosity, right? I mean, it's nice to see young people, right, children and kids interested in that kind of science. I mean, if you make it fun, why not, right? Okay, so this is the message. This is part of my job, right? So this is the connection we do on this community topic, right? So if you feel to drop me a message, this is my contact, and thank you very much for this.
Thank you very much. Any questions to Aldo? If not, I have one. So you do kind of outreach with hardware, which it presupposes much more resources somehow, and also engage different skills and many skills. So how do you see this compare in terms of the efforts with what you have seen from us?
Yeah, I mean, for sure, definitely there are lots of connections with this because the goal, as I said, is to connect this to community and to a broader audience, right? So it would be interesting, for instance, to check things like there in Goiânia we have a recent school on AI where we have managed to build already a capacity which is quite impressive for Brazil. So we have huge clusters of AI, dedicated AI servers, which are A800 from NVIDIA, and constantly improving this. So, but this is a different thing. I didn't show and didn't talk about it. This was more part of the research side that I conduct there. And on this, we have people interested and skilled on looking at data, doing analysis, processing, and what was discussed. So this is like an interesting connection to join the initiative, Open Universe, and also divulgation, scientific divulgation, right? So what we are also interested in. So many ways.
Good. So I guess we should stay in touch. Okay, so I think that's it. It was long 3 days. It's not the complete end because we have 2 days of kind of hands-on activities with those of you who will stay Thursday and Friday. But this is closed for remote connection, so it's just hands-on activities here. The next 2 days are not going to be in this room. They are going to be in another room called RNP room, which is on the other building. So when you enter tomorrow from the main entrance where you have come, you ask for the auditorium building and you go there, and there will be plaques for you to go to the 3rd floor where there is going to be a computer room. So each of you will have one computer to do the tasks. So this will help. So you don't have to bring a laptop or anything, and everything is installed, pre-installed for you. So the idea is that this will help the work to develop. And we'll have people with like monitors following and introducing the work. And we're going to have a few talks in the beginning to introduce the work, 2 or 3 talks. So in the morning, we'll have some lectures, but in the afternoon and on Friday, the idea is that you develop this work, which will result in this catalog or the start of this catalog with the Swift XRT and a sky map that will be left as a resource produced by Citizen Science. The idea is that you're not going to finish it in 2 days, but you're going to start. And I hope that's not only you who are going to finish it, because there are a lot of data. So the idea is that the tools that we created for this be made available to the Open Universe website, and other people can download and do the work and help compose this sky map done by citizen scientists. So I hope you enjoyed the next 2 days. I hope you took profit from the last 3 days. Certainly for us, there was a lot of learning. I enjoyed it. Learned many lessons. I hope that we can continue this work, improving more and more from your feedback. So do not hesitate to give your feedback to us. And those of you who want to continue in closer contact, let's do it. Let's keep in touch. Okay. So see most of you tomorrow, I guess. And for those who are online or watching the video later, thank you for attending. Bye-bye.